Welcome to this machine learning course for beginners taught by Ayush Singh. He is a data scientist and popular instructor. This course is your gateway to mastering the intricacies of regression analysis in the realm of machine learning. Ayush has designed this course to provide you with in-depth knowledge, practical examples, and hands-on projects that will set you up for success. With a curriculum that covers everything from the basics to advanced techniques, this course offers a unique opportunity to not only learn the fundamentals of machine learning, but also explore the often overlooked power of regression analysis. So get ready for a deep dive into the world of machine learning.
What if I told you that there's a core machine learning course that does not have only detailed explanation of regression analysis, but also have detailed lecture notes as well as assignments with personalized feedback on that and a scheduled learning plan for you? Well, guess what? I'm offering all of this for absolutely free. Hi, I'm Ayush and I'm currently working as a data scientist at Replik and has demonstrated working experience as an MLOps engineer at ZenML and a data scientist at RFI. And I'm founder of Anthem as well. And I welcome you to our core comprehensive machine learning course out here. The course is designed to give you a solid foundation of machine learning and regression analysis, which is often overlooked in most of the courses available right now. We begin by laying the groundwork for machine learning, so even if you're a beginner, you're able to understand it. We talk about what is learning, we talk about generalization, we talk about inductive bias, and a lot of things initially. And then we gradually move on to regression analysis, and we cover as much as we go in depth. And to ensure that we are quite equipped with the practical applications as well, I'm going to introduce 2 projects by the end of the course, which you have never seen like that project before as well, because I have worked personally at several companies and I know how we deliver data science projects to them, and the same way I'm going to do it in this course as well. But that's not all. If you want to maximize your learning opportunity from this course, then we are offering free updates to the course, regular assignments with personalized feedback to you, and a tailored learning plan for you to complete this course in just 1 month. You can simply go on a GitHub page for the course and then get access to the LMS directly from there. And all of this for absolutely free. One of the major issues which I want to highlight, you might be asking, yeah, it was just for regression. Most of the instructor takes around only 1 hour. You're taking freaking so much of hours to teach it. I tell you that people forget the foundation, people forget the basics of it, and they just strictly goes on advanced topics like deep learning, and then they are not able to secure the job. And then they complain me that, hey, Ayush, data science has no jobs. But actually, if you think in a way that the talent is less than the actual jobs, because they are not going to pay you thousands of dollars for just 3 lines of code which you write in scikit-learn. Anyone can do it. And then crowd is increasing, but the talent is decreasing. They're forgetting what's the base of machine learning, what's the base of data science. They're forgetting the solid foundation which was used to be given in 90s and all. So that's what the course focuses on. We make sure that we emphasize the core concept of machine learning and regression analysis so that you can even learn further things on your own. Our course is designed to put emphasis on core concept of machine learning and regression analysis so that you can tackle critical business problem and solve it the way real data scientists solve. So that's enough of it. Now let's get started with the course. You can directly go to the LMS and then start from there by seeing the tailored learning plan, or you can get started from here. Let me know if you have any doubts in the comment section, and if you find any errors or errata in this course, please feel free to make an issue on the GitHub page for the course.
Hey everyone, so let's get started with our machine learning content, and actually we'll get started with a bit of discussion on learning the machines, learning intelligence, and give you some of the concepts which is required eventually to build up your ideas, right? So let's get started now. So I would suggest you to open up your notes if you have got it. So once you have the notes that you can see on the front of the screen, so we're going to start off with what is learning, right? So let's eventually talk about what is learning, and slowly we'll get into the concepts of, very good examples of learning and intelligence and etc. So the first one is that what is learning? So I suggest you to write your answer in the comment box if you know. So according to what exactly you know about. In terms of machine learning, we have the training data. We take some sort of, the data. Don't worry what data looks like and everything. We'll cover that. So we have the data, right? And then we feed to a sort of a black box, and then we get a trained algo that is trained on that data. For example, assume that you have a man, right? You trained that man with that particular skill, and then whatever output after 6 or 7 months, you will be getting a trained man specialized in that skill, right? So this is how your model gets trained. Your model gets the data, gets the training from the data, and then it gets trained by some instructor, right? Assume that in this case it's an algorithm, and then after some time we get a trained algorithm. Right, that in terms of a very simple and very mind understanding behind any algorithm. But let's talk about a very nice example, which is known as rats learning to avoid poisonous baits. So what is baits? Baits are some sort of food or etc. So the formal definition of baits is that it is some sort of it is a type of a prey that is used to attract when hunting. So sometimes we use that baits to attract poisonous thing. Yeah, it is a poisonous thing that we use to attract food, right? Mouses or any other things. For example, fish, we also have the baits, right? So in this way we have the bait. So basically the problem statement is that the rats are learning to avoid the poisonous baits. So how do rats learn to avoid that poisonous baits, right? So rats assume that rat came, and then and then they given there was a food available where this was a bait, right? So they gone, and then they it was like smelling good and etc. Rat ate this food, and there's an ill effect on rat came, right? There's an ill effect of rat came. There's ill effect of rat came when they ate this food, and then rats will not eat this food, because this is the learning mechanism which happened right now, where according to the past experience, according to the history or the mistakes in the past this rat did, rats will no more going to repeat this step again. This is one sort of a learning mechanism. Another learning mechanism which you can think of is assume that you have done some sort of mistake in your past, or a very simple example, assume that you go for someone for guidance, right? Why they are capable of giving guidance? Because they have gone through the problems. They have already gone through the problems. So you go to them so that you get an easy path, so that you get an easy guidance from them. So to achieve something in your career, right? So in that way, I'm saying that they already have an experience of something. Now they're capable of you to guide, right? Just like I guide so many people, right? So I guide so many of folks right now. So I am capable because I've already gone through those problems. Now I'm capable because of my past experiences. So whole point to take out right now, I have learned what mistakes and what things I did that led me to success and failure, right? That I've eventually learned that. So now that's a learning mechanism. For example, you learn, you study some maths concept, right? You study quadratic equations or maybe some calculus concept. So when you study that, what eventually happens is that you take a look at the particular concept, and once you take a look at the particular concept, now you understand with the help of examples, and then you do a problem. And if you did any sort of mistakes, you change it according to like ask for help or see the solution. But when you when you solve similar questions, you will be able to answer that. Why? Because you have learned from the past mistakes which you did, right? Because you're not going to repeat the mistakes which you did in the past, even while solving problems. Sometimes it happens as well, sometimes it does not, right? So that's called the learning mechanism. That's why we say the failure is a part of success, because it gives you the learning phases, the learning opportunities to actually grow forward, right? So there are several types of approaches which we go through. The first approach is learning by memorization approach. So this is something is very interesting where we say in Indian language it's ratification. And in ratification, what we do, we memorize things, whatever we want to study. So for example, I've seen students to literally memorize, science answers, SST answers, even computer science answers, because they literally memorize code and they just go and write in the sheet of paper and then they memorize literally like even mathematical questions. However, it's so obvious that they'll not will perform well. But But over here, assume that if you memorize each and every concept, each and every line of your answers, will you be able to perform good in examination? So even if one line you forget, you'll mess up with all the answers. You'll start integrating first answer to second answer to first, right? So you have to apply. So over here, memorization literally fails in your daily life. You cannot literally memorize everything and then go and sit in examination and you expect that you'll score good. It works till class 6 or 7, but it doesn't work when you actually grow, right? So you can't literally memorize each and everything, whether it be answers, whether it be mathematical solutions, or literally anything. So I hope that given you a good sense about what exactly I want to talk on is learning by memorization approach, where we learn some things by memorizing that sort of thing, right? So now what exactly I'm going to do is talk about some of the examples which we have listed out here for you to better understand things. Cool. So assume that you want to build a system. So you might have seen in your email, Gmail, where you have several folders: promotions folder, social folder, spam folders, and updates folder, etc. So you have these folders, and there's one folder called spam where all your spam goes in. Right, where all the spam goes in. So what are those spams, right? That's a question. So now we're gonna build a system. That, given the past data, right? First of all, if you're learning something to identify a spam, you need to have the data. You need to have some sort of content to understand from, right? So in this case, if you want to build a system, that given an email, it classifies that email is a spam or not spam. Okay, that given an email, it classifies whether that email is a spam or not spam, right? So now that's a question, right? So so now what you will do is that the first step is for learning literally anything, you need content for this. So we need the data for it, right? So we are going to collect the data. We want to collect the data, which is where we have the spam emails, right? So we will collect the data which is spam emails out here. So we collected the data which is spam emails out here. Now we have the content. Now we want our machine to learn from this content. So there will be two types of guys. First, who will memorize this. So we'll talk about the first guy. The first guy who will memorize this will memorize each and every email. So machine will memorize each and every spam email, right? And now that machine is capable. Now that machine is, even if that is 100% correct, even if that memorized very 100% correctly, right? So machine will be able to will be able to memorize each and everything. Now, if an email comes through this machine, and now this machine is told to classify this email to be as a spam or to be as a not spam, right? Whether that email is a spam or not spam. So you got a new email and you classify it. So how machine will classify? Machine will search this email into its memory, whether this email is available into its memory or not. Right? Whether the words of this email is available to in my memory or not, right? But if not, then we say that it is non-spam. But because the content which we learned is about spam, right? So if this is not available in that in his memory, what the model has memorized from the data, then the model will be able to say that it is non-spam. But if that email is available, then it will be spam. So what's the problem with this approach? Right? That's a good question. What exactly the problem with this approach? That's a good question to actually go forward to. The problem with this approach, it is not generalizable. So why it is not generalizable? So let's talk about a very instance example. Assume that you have got a new email, you have got a completely new email, where your model has not memorized. For example, you sat in your mathematics, let's say science examination, you got your questions which was in a textbook, which you memorized, but you also got a tweaked question, but you also got a very different set of questions. So where you have to apply logic and apply several skills in that. So there you will fail, right? Because you memorized only the questions which came, but you're not able to answer the questions which are new, which are unseen by you, right? So in this case as well, model will fail to predict for examples or predict for emails which are unseen by the model, which are not seen by the model. Right. So that's the problem with the approach right now. Right. So that's one of the approach. The problem is that the machine which we have does not have the ability to email any unseen emails, to predict for any unseen email. So for example, if any email comes, and let's assume that it is a spam, but this is not available in this memory content, so that will be flagged as non-spam, but actually it was a spam. Right. So this is one of the problem. So we need to, what we need to do, we need to figure out a solution to further generalize it. Further make to generalize means to give this machine an ability to further classify even unseen emails by logical thinking. So we're going to make this guy to the second number of guy where it also understands, analyzes the data, and applies logical thinking in further to predict emails. So that's we have to generalize, and this is called something known as inductive inference. Okay, this is nothing but called inductive inference. So let's talk about inductive inference in detail in the next lecture. So now we'll talk about something known as a generalization, which we had a talk, and then we'll talk about and what's the issue in this as well, right? So we'll talk about that. So we call that generalizing our model is known as inductive inference, right? Please read if you want to know more examples and all. I've linked the very nice book, the chapters, and every chapters is also included in the LMS. So please go over there. You will be able to see everything, each and everything with the resources and everything, and the reading materials regarding if you want more examples. But that's it. You can stay here if you have understood it. So generalization is it's an ability to add the feature in your machine to actually improve, right? To actually work on even unseen examples, but to apply logical thinking. So now let's take an example over here. Is that the problem which we had, the very basic problem which we had. So I'm just going to take a very nice example right now. So now over here, this rat. So in this example, this rat, if we have the generalization available, where your rat will be able to decide whether to eat this food or not, based on its smell, right? So rat will be able to decide to eat this food or not with the help of its smell. Right. So generalization, how does this help? How does this generalization help this rat? It helps it to decide an unseen examples which is similar to the bad food. So what is it saying? That rat may have seen the similar food, right? So rat may have seen the similar food. So generalization is that even a similar something comes in, rat will be able to refuse. Okay, this is a bad food or this is a good food, right? So generalization gives an ability to even rat to decide on this particular food which he has never eaten before, based on the similar things which he has eaten in the past. Another example which we have seen, that we have a machine which scans the emails. It extracts the words that appears to be spammy words, and then it says spam or not by seeing the spammy words. So basically that email comes and then see what proportion of the spammy words is in that email and then classify it based on that. But there's an issue. So now by this, if we have the words that is spammy, and then we check the proportion in that, or we give the machine the ability to even classify based on the logical understanding of that, and or a generalized understanding of, okay, this is how the spam email looks like, right? So your model is able to generalize according to the things, right? That's one of them. But here your system might be able to perform very well, right? So in this case, you might be thinking that your system will be able to perform OMG, right? But actually, it's not true. You give the ability to the model that to identify even unseen examples, and then you think, okay, it's over, right? It's not over. So inductive inference might lead us to false predictions, misleading predictions. Let us see how. So this pigeon superstition is an example. Pigeon superstition is an example which I've read in a machine learning theory book from algorithms theory. And also this is a very famous example on learning conducted by some sort of, university, which I don't remember. They have written it very nicely, is about how this inductive inference might lead us to bad inference. How this inductive inference might lead us to bad inference. So let's talk about the very nice stuff as of now is this particular thing, pigeon superstition. So you will be seeing you'll be seeing a very nice I'll be linking a very nice video which I suggest you to go over there and watch that video first, right? So go over there, watch that video first, or I'll be giving a short experience on what exactly is going on. So you can actually pause the video right now, go over there and understand what exactly is going in that video. But I'll be explaining you in simple English terms, so you can actually go over there and understand it by your own terms. But I'll be explaining you in a very simple English terms. So you have what the experiment was. Experiment was now you have set of pigeons. You have set of pigeons which was contained in a cage. So you taken a set of pigeons, and what they did, they've kept it in a cage, right? And that cage had a small hole. Had a small hole where the food was coming and going at a certain interval of a time. Assume that every 3 seconds, 4 seconds, 5 seconds, 10 seconds, 12 seconds, 14 seconds, and all these pigeons are super hungry. Okay, so we have a cage, in that we have a pigeons which is super hungry, and then there's a hole where the food is coming at a certain interval of a time. Okay, at a certain interval of a time. Now, when food is delivered, now they are angry, right? So the pigeons are hungry, right? So if the pigeons are hungry, they'll keep on doing some things. They'll try to peek, no? They'll try to peek and try to find some sort of foods, so they try to peek, or they try to wings spread their feathers and then try to go from here to the peak, right? So in this case, as an experiment, I'm taking example, if one of the pigeons, if two, three are peaking, right? So they're searching for the food. They're active, okay? They're active and they're peaking like this, which is like searching for food. They're peaking now. So when food is delivered at every interval of a time, they are engaged in some sort of activity. That activity can be peeking, or that can be feathering up, right? Anything, literally anything. So if you see the video, you'll be seeing that some birds are peeking, some birds are there's only one bird which the video which answers. The bird is peeking, or maybe the pigeon is maybe doing some sort of activity, right? Going from here to there and here to there. So this is some sort of they're engaged in some activities. Now, when the food was delivered, they were engaged in some activity, right? So when food is delivered, they go on and eaten that, right? And then again started doing the same action. In a hope that food will deliver it once again, right? So if they were like, pigeon is doing some peeking and the food is delivered by doing that action. So he gone and eat and again started peeking. So he thought that if I peek, I'll be getting food to me, right? So basically, pigeons started doing the same action in a hope of food arrival. But I'll come to that but later on. So the pigeon association of the delivery of the food with whatever actions they do, peeking, feathering, flying, literally anything, actions, with whatever chance actions they had been performing when it was first delivered. So the first time it was delivered, so they were peeking, so they continued to do peeking in order for the food arrival. Because they hope for it. So what's the problem in this, right? Right? So let's talk about what exactly the problem which comes. So basically, pigeon built an association of the delivery of the food with whatever chance or actions they had been performing, right? So they built the association between delivery of food with the actions like peeking or flying. They did. So they tend to do peeking in hope of food arrival. right? So very interesting. So your pigeon learned that they learned this, right? They learned it. But what exactly? But now let's try to figure out what exactly the problem in this. Problem is that human learners, the we, can rely on common sense filter, right? To filter out meaningless sense. For example, assume that every time I throw this pen over here, every time I throw this pen over here, right? Every time I throw this pen over here, my food will be coming, right? Like it is at a certain interval of time, in the morning, in the afternoon, in the night. It does not matter how much I do this, I'll be getting that interval of time. In this case as well, it was delivered on an interval of seconds. It was not dependent on what actions pigeons are doing. It was just intervals. 3 seconds, 4 seconds, 3 seconds, 6 seconds, 8, 9 seconds, 12 seconds, 12 seconds, and then it is going on at a certain interval of time. It is not associated with what actions pigeons are doing. Doesn't really matter. So now we can rely on it. Is a meaningless, right? Whatever pigeon has understood, it is a meaningless, right? This is a meaningless, and this is something which is not. So human learners can filter out meaningless things. We can filter out that's a coincidence, or that's something super meaningless, meaningless learning conclusions. By doing this, if I get money, like one time, assume that you are throwing this pen out here, right? You're throwing this pen out here, and you got money on your bank. Now you cannot keep on doing this to get money in a hope of money arrival. Money will come at a certain interval of time, right? So this is something this is meaningless conclusion. But there are some humans who cannot apply the common sense filters to not take out the meaningless. That's controversial, but never mind. So now over here, pigeon also learned a very bad meaningless conclusion where he thought that peeking will get me a food. Right? That's a bad. So we also have to give this filter to our machines, right? So in this generalization approach, the problem was that your model may end up learning a meaningless learning conclusions. So we must give the well-defined, crisp principles. Again, I'm repeating. We must give well-defined, crisp principles that will protect our program from reaching senseless like what pigeon reached. That will protect our machines to reach that, to reach that conclusion. This excerpt is taken from Understanding ML from Theory to Algorithm. This is very nice. That's why I've taken it from there. What exactly it tells? It tells that we need to give filters to our model so that our model is able to identify the meaningless conclusions like this, right? Meaningless conclusions. So we have to give the well-defined crisp principles to our model, and those principles are only called, and those well-defined crisp principles are called what? That are called nothing but development. That's what we learn. That's what the theory of ML comes in. Theory of ML. That's what the theory of ML, where we give the well-defined principles to our model. I hope that makes sense to you. That gives you a very nice understanding about whatever we want to have a talk on. Now, there is a very interesting concept which is known as inductive bias. Inductive bias. So let's talk about that, and then we can end this video, and then we can go to the next step, which is exactly learning about what is machine learning. And then now we know about learning, and then we can go on a bit of, learnings. So, no, cool. So assume that, so sometimes you might be noticing that a new rat, a new rat might refrain from eating a food because they think that this food is poisonous. Why? Because of the prior knowledge inherited from the previous generations. So they have some sort of genes that tells us don't eat this food, this is poisonous, because of the past generations, because of the habitual understanding. If you've studied biology, then you've studied that their evolution or the evolution is necessary for human beings. If there is no evolution, if there is no, chain of, whole food chain, so assume that you have lots of humans and they died from the disease, but there might be some newborn humans or babies which later develop in humans, where they are capable of fighting with those diseases. They are capable of that, right? They have built a very nice combinations of fighting with the diseases, right? So in this case, this rat has inherited from the previous generations of the rats to further say that, okay, I'm not going to eat this food. I'm not going to eat this food because it gives some sort of sense. So you might be thinking, why rat? Why rat was able to successfully classify to not eat that food, whether pigeons was reaching to a meaningless conclusion? Because rats were having the prior knowledge, and prior knowledge is super important, where the rats were having the prior knowledge. So pigeons learning was not more successful as compared to what rats did because of the prior knowledge. And prior knowledge is also called inductive bias. Prior knowledge is also called inductive bias. I hope that makes sense. Now I hope that given a very nice introduction to learning. In the next lecture, what I eventually going to try to achieve is talk about a very nice introduction to machine learning with applications, and we'll also do several examples as well. That's something is necessary for you. Right? So let's go to the next lecture and then try to understand machine learning with a very nice definition, with a very nice set of examples. So now what I'm going to do is actually start talking about, machine learning stuff. And that's something which is super important for you to actually go forward with it, right? So let's talk about that. So now what we're going to do, we're going to actually talk about what is machine learning, and we're going to talk about some of the applications of it, and then we'll see some of the formal definition which comes in machine learning. Now you know what exactly learning is, right? Now you know exactly what learning is, and then you'll start referring that we have solved some of the problem. Now just to connect the dots, the dots, how we're going to connect it. The dot is where we learned about learning mechanism, where our rats were learning to further classify whether to eat this food or not, right? So we've gone through memorization approach, where by taking a simple spam or ham examples, and for memorization we thought that generalization, that we have to generalize it, so that is inductive inference. So we've got another issue which we see in inductive inference, which is the misleading or reaching to a senseless conclusions. And for defining that senseless and for refraining or protecting our programs for senseless conclusions or the principal conclusions, we have something known as machine learning, where in this machine learning we define our well-defined crisp principles so that our model does not reach senseless conclusions. Cool. So let's get started. So I suggest you to maybe have a coffee with you, because that's something is super important to refrain from. So correctly, I'm recording at 3 a.m. because I have boards as well, and I have to prepare. I know how I'm managing this, because I have a class 10 examination in 24 days, I guess, and I have to prepare a lot, and I'm devoting my day and night on that. But eventually I have to also do for community, and I'm doing it because I like it, not something who's forcing me to do this. But coming back to what exactly I want to do, it is, what is machine learning? Question. So whatever you know about machine learning, write that in a comment box. Add your comment or whatever you can do, just write that in a comment box. What is machine learning? Right? So what is machine learning? It's an artificial intelligence domain. An artificial intelligence domain where we extract patterns from the data and analyzes the data and make intelligent predictions on the new data according to the pattern your machine has learned. A very nice and influential statements. So let's try to talk about the very highlighted statement. It's an artificial intelligence domain where we extract patterns from the data, analyze the data, make intelligent predictions on the new data. This new is very nice keyword, according to the pattern your machine has learned. So these keywords, if you understand, you know machine learning. So let's try and understand each and every keyword. First, it's a domain of artificial intelligence. So if anyone calls ML as AI, say ML is AI. Of course it is, but it is a domain of an AI. It is a subset of an AI domain, right? Where we extract patterns from the data. So I want to explain this to you with a very nice, practical example. Let's forget, bookish examples. So assume that you are doing something like, so you're studying some sort of mathematical concepts. Assume that you're studying quadratic equations. So you're studying about quadratic equations, and in that quadratic equations, you have something known as taking out the, you have some sort of quadratic equation form. There's a formula for taking out using, which is like the concept, right? So there are so many word problems regarding ages, distance and speed, etc. So now when you actually solve those problems, you learn some sort of patterns that this is how I should solve it. When you learn those chapters, when you practice those chapters, when you actually understand those chapters, you learn how to what patterns are there, what patterns of questions are there, and how the solutions are framed. Right. So in this way, we have to figure out. In this way, you are learning patterns from the chapter, and by learning that, you're able to reach to a conclusion, right? So once you have the pattern, now if the new question comes, you apply that whatever patterns which you have learned or analyzed your content. Now you use that analyzer, whatever you learned, to answer those or predict the MCQs, right? So answer those new questions, right? And from whatever you have learned till now. So if you didn't find the pattern well, you will be not able to answer that well. But if you know, you will be able to answer very well, right? Cool. So that's exactly machine learning works. So we're going to understand in that way. So it extracts patterns from the data. So for example, if you take an example of a spam or ham example, it extracts pattern from the data. It extracts pattern from the data where how spam email looks like, how ham email looks like. It learns, analyzes that whole data. Data means the collection of information. In this case, you have a spam and ham emails. That's a collection of information. You extract the patterns, you understand that how spam looks like, how ham looks like. Now, once you have that analyzed it, now when new spam email comes in, the model uses that analyzed or patterns to make intelligent predictions on the data which you have, right? According to the question, according to the pattern which your machine has learned. That's what exactly machine knows. So now you might have several questions by now. I know it. First is again, how to extract patterns, how machine extract patterns from the data, how machines analyzes the data, how machines make intelligent predictions from the data, and etc. Right? So these are questions. And in the whole course, we'll answer this. We'll answer this question, answer this, how machines extract patterns, how we analyze the data, how machines make predictions from your data. Right? So there are a set of mathematical, as of now the answer is, there are a set of mathematical algorithms that helps us to extract patterns, mathematical or statistical algorithms from the data, which we'll study throughout the course. Okay. So that's an answer. So let's go to a more formal definition, which I really like, by Tom Michel, and he has a nice book. I recommend you to read that book. Very nice book. If Tom Michel is seeing this, I don't expect him to be seeing this, but hi to him. I'm just kidding. He's one of my big inspiration in machine learning field to get started with. His books on machine learning is really, really influential, and his lectures as well. So nice. A computer program is said to learn from the experience A with respect to some class of a task T and some performance P if its performance P on task T as measured by P improves with experience E. If you got this, very nice. If you know, if you don't, that's totally all right, because I was also the one, even in my middle of the phases, I was not able to understand this definition. This is by Tom Michel. Okay, so let's understand this definition by this flowchart which I prepared for you. So you have a computer program. Assume that this is your machine learning machine learning, whatever you computer program. What is model? I've been taking model name, right? So assume that model is your machines as of now, okay? Machines, assume that as of now. I'm just taking model, just assume that as a machines, just as not having so much of jargons. So you have this computer program, that computer program learns from the experience E, and in this case experience E is your data. Your computer program, they learn or analyze, extract patterns from the data for some task. The data is for some task, right? So for example, if you have a spam or ham data, which is a collection of information of the spam emails and ham emails, so that's the experience is available. Now the task was to identify spam, so that for that task, and that performance on the task is measured by P. So we measure the performance, and once we have the performance, we improve, and that performance is being improved by adding more data or adding more experiences in that. So that's what exactly it says. Highlighting the important terms, it's said to the learn from the experience E with respect to some task T and some performance measured P. If the performance on T, the task spam and ham, measured by performance, if they're measured by this, it improves with the experience. If we increase the experience, it will also it is going to be improved. So this is a definition by Tom Mitchell. I hope that makes sense. Another example is Indian house price prediction system. So here a task is to predict the house prices of Indian states where you want to build any ML system. You need one of the key ingredients, which is data, which is in this case, we have experience. So you train your model, which is your computer program on the experience, and this is on the past data, which is experience, because past is experience, right? And here past data is your experience. So the performance P is measured how well your model is performing on that particular task. And if you add more experience, the performance will be improved. That's it. That's the definition. Very easy. Now I hope that you understood. Do it for other applications. Very, very, very nice practice. However, if you want to do the practice all along, please enroll in our official ML course as well as you can also go and review some of our courses available, or the free LMS which we ask you to enroll in. Good. So what are the steps done by your machine learning system? So that's something. What are the steps your machine learning follows to actually do this? I know this is early phase to talk about that. That's something is super important, which I want to have a heart-to-heart talk with my viewers on this. However, if it's okay if you don't understand it, but I just want to have a heart-to-heart talk with a very detailed explanation of everything, and then we'll talk about data, and then and after that we'll talk about some of the applications, and then we'll talk about a very nice application or the type of machine learning, which is supervised learning. We'll talk about unsupervised later on, but as of now I'll talk on supervised only. So hey folks, welcome to this video. In this video, what I'm going to do is to talk about some of the steps which is usually done by machine learning system. So what is the procedure, what is the process for going through for building a good machine learning system? What is machine learning system? The system in which we give an ability, we give an ability to a machine to be able to learn from the data, which means to be able to learn from the data or extract patterns from the data and make intelligent predictions. So we're going to make a system. What is the process of that system where we extract the data, we analyze the data and make intelligent predictions according to what it has learned. So what the like everything, for example, while creation of Maggies or any sort of foods, you have a processes. So just like that, while creation of machine learning system, there is a processes created or recommended processes, which I really want to talk to you guys. So let's get started actually with that. So it may happen some of you may not understand the fully thing. That's totally all right if you don't understand it, because I feel like it's something which you might focus on things like definitions and the understanding the core and the crux of what exactly each step is doing, as there is a section in CS01 course, so the course which I teach on Anton. So there is a section called MLOps where I cover these things in great detail and talking about several case studies. And also, if you're interested in something, learning in depth and all, I recommend CS01 if you want to learn something fully. So now coming back to this, you have something known as scoping. So you have something known as scoping, and what does this scoping means? Scoping is something like the first step in your machine learning system is scope out the problem you're trying to solve. Scope out the problem you're trying to solve. The first step is scoping, where what you do, you understand the problem statement and write down or jot down the key requirements for your ML project. So basically, whenever you start off with any sort of project or machine learning project, any sort of machine learning project, so what you do over there, you simply first of all understand the problem statement, right? You understand for example, let's say you're building a spam or a ham classifier. So you have a system, they have a machine M, you want to build a machine M that classifies whether that is a spam or a ham, right? So the first step is scoping, where you understand what exactly this problem statement is, what sort of data which you have, right? What sort of data which you have, what are the key requirements, like key requirements, what is useful analysis. You understand the problem statement according to given by the stakeholders. And the second step is you understand key requirements, like do I require how many data scientists to work in this, what should be the compute power of this, what should be the infrastructure required for this, etc. So scoping out means getting a brief understanding what this project will be about and creating a brief plan of go-to strategy for working on this project. Then after you have a brief plan and everything, now what you do, you simply go to the data part, where you do where the examples of the steps is now once you have the data, you have to eventually clean it. We'll talk about data cleaning and all in one of our projects. So when you have the data, you have to clean this data, you have to clean the data, you have to process this, you have to process the data in a good way, and etc. So basically what I'm trying to tell over here, that given the data, you want to understand it, you wanna to clean it, etc. So I think and then you have the data, and then you collect and validate the data accordingly, right? And then you clean the data where you have removing of missing values, etc. So I know that this will not make sense if you're a beginner. So it is something like you have the very bad data, you convert that to a good data by data cleaning and etc. You validate the data, whether that data is from truthful resources or not, whether we can trust the data information or not. Now we have the data. Now what we need to do, we need to extract patterns from the data. And for extracting patterns from the data, we have something like modeling. Not something which actors do on a ramp walk, but I think on this, modeling requires something like, something like your system tries to extract patterns from the cleaned data which you have, right? And then once you have once you're done with modeling, you want to put this so that your users can make predictions from this model M. So once you have the trained model where it learn to extract patterns, so now we want to make predictions for it. For example, if this machine is of spam and ham classifier, so we're going to put this in production so that it is able to classify, so that every email can get to this and the model is able to classify in a couple of stuffs, which is spam or ham. So we're going to put this in production so that it can be used by folks in real time. And also we monitor and maintain our system. We see like how our system is performing, what is the whether our performance of a system is degrading or what is the possible errors which are coming, what is the etc. So what is the wrong predictions which are coming, etc. So we have to monitor our system as well. So there's 4 steps for any there's 4 to 5 steps of recipes of machine learning, where you first of all plan out what exactly you need to do by understanding the problem statement, and then you get the data, and while getting the data you have to validate whether that data is from truthful resources and clean the data in a good data. And once you have that good data, now you model it, which means that you learn to extract patterns from the data, and now you have the model which has the patterns from the data. It should be able to successfully use it in the production, right? And then you have to continuously monitor it. So these are the steps for your machine learning applications. Now Now let's talk about, I hope that this makes sense, but now let's talk about something known as data. So what is data? So data is information contained in a structured or unstructured format. So data is set of records. So you might have seen in your machine learning lectures, or in your class 8 or 9 lectures of computer science, where you might have gone through a data is a set of records, right? It's a records or set of information available for the particular product. So for example, you have Amazon listing. You have an Amazon listing. Let's say you have mouse, right? You have mouse. So that mouse might have several data, right? Several data, like what is the title, what is the description, what is the price. So these are the set of records for the particular product. So just like that, data is an information which is in structured and unstructured format. Okay. And we'll talk about what is structured and unstructured in a bit, but here's an example of a data where this is an example of a structured data where it is contained in a table, where this data contains it is the data of house price prediction, where we are given some of the information about the house prices, housing price data, where we given some of the information about house prices, which is first one is floor, what is the floor space, how many number of rooms in that apartment, what is the lot size, is there any other apartment attached to it, right? Row house, corner house, detached. So these are the information for a particular house, right? And this is the price in $1,000, right? So this is the price for this feature. This is the price for that particular house. Then we have the second data point. This is the record for the second house. This is the record for the third house. The record for this first house, second house, third house, fourth house, fifth house, sixth house, seventh house, 6, 8, and 9 house. So you have the 9 houses, where for every houses you have your own infos, using including pricing, floor space, rooms, etc. So these are nothing but these are nothing but your data, where we actually have something information contained, right? Cool. So now what we gonna do is talk about a bit of application in machine learning, right? The first application which we really want to talk on is loan prediction system. So it is an application. So loan prediction system is an application of machine learning. So assume that you are in a banking sector. You're in a banking sector, and bank provides loans to the customers, right? So you might have visited loans, and also your bank might provide loans and also the customers who require right. So now you assume that you are working in a bank, and then that bank gives loans to the customers who requires the loans. So when providing loans, there is a high risk that the person may or may not return the loan. So the risk is that the person will not return the loan back with the interest, right? It may return loan back, but are they going to return back with interest or not? So given the background information about the particular customer, what is the history of them, like what salary, etc., we've given those infos. We wanna predict whether we should give loan to that person or not. This is one example. Another example is the spam ham detection system, where you given an email, classify whether that email is a spam or ham. Recommendation engine, you might have searches something like this, which you're seeing in front of you. So this is a recommendation engine in Google searches, or maybe recommendation engine in your YouTube. So these are a couple of applications which you might have already seen. I don't intend to, just to give you a feel about it. So I hope that you understood in a nice way about very good processes of machine learning. What I want to achieve in the next set of video is talk about the last thing of this lecture is to talk about supervised learning, and we'll try to learn supervised learning with a very visual and very storyline of examples, so that anyone, even if you're class 5, you will be able to understand very easily. Hello everyone. So now we'll talk about something known as supervised learning. And hello everyone, we'll talk about supervised. So now we'll talk about supervised learning, and we don't want to directly get started with definitions and all. I want to tell you a very nice storyline or very nice example relating it to the practical stuff. So let's get started with that. The first is to understand the concept. So now whatever you're seeing in front of me is to understand the concept. For example, you have assumed that you are studying a mathematics book, right? So you're studying a mathematics book, and there you understand some concept, you understand some examples. Right, so you understand some, so you have a mathematics book, you understand some concept, for example, you have a quadratic equation as a chapter, so you do some examples, you analyze some formulas, you analyze some patterns for solving a particular questions, and etc. So now you once have the questions. Now what you do, you're trained with the tricks, you're trained. So now you understand the concepts, you're trained with from the examples and trained for the exercise questions with the help of supervisors. So when doing exercise, you are doing examples, you're analyzing the patterns. So you're getting trained with the examples and the exercise questions with the help of our supervisors. So of course you have a question, and this, you're also seeing the solution if you're not knowing, if you're getting error in that question, right? You're not able to solve that question, so you seek help from supervisors or whoever the instructor is out there. So by now our storyline is that you understand some concept, you get trained from that examples, you also do the back exercise questions with the help of your instructor and whoever. Now once you're trained with everything, now you sit for an examination, and in that examination you don't have any help of supervisors, you don't have any help of exercise solutions, you don't have any help of answer sheets, etc. Right? So you sit for an examination, and if you were trained well, then you will be performing well, otherwise you'll be not performing well. Okay, so this was your this will be conditioned after giving the examination. So if you were trained well with the help of your supervisors and everything, you will be able to answer it very well. So now you can see that how you were trained. You were trained with examples questions where you're given question as well as the answer to it, so that you can understand the pattern, right? In exercise questions, you have a question as well as the help of supervisors, which is question and answer. You have a possibility to see the answer, right? So just like this, you're trained with examples and the questions. Now you sit for an examination, you sit and give the examination, and then that will predict whether you're going to really pass the examination or not. If you were trained well, analyze the question well, you will be able to pass. And the whole concept is nothing but called supervised learning. So let's talk about what exactly supervised learning is. So in supervised learning, you're given the question as well as the answer, so that your model learns from it and get trained from that. Right. So in supervised learning, you're given the question just like this, just like in this case, for training for this particular child, you were given the examples, and in that example, there are the questions as well as the answers, right? To understand the pattern. So in supervised learning as well, you're given the question as well as the answer, so that your model learns to analyze pattern from it. And then whenever you sit for an examination, which is the new examples, if you were analyzed well, or if you're trained well, you'll be able to solve it, right? But now what I want to do, what I really want to talk is on something which you might notice is that assume that you have an example over here for house price prediction system. So you have an example of housing price prediction system where you want to predict the house prices based on the given feature. So you invest in real estate and you predict the house prices in the coming 10 years by giving the following requirements for that reports for that particular house. So this is house number 1, this is house number 2, this is house number 3. So given these characteristics of the house, we want to predict the price of the house, right? Given the characteristics of this house, we want to predict the price of the house. Characteristics means what is the floor space, rooms and all. Given all of this, we want to predict what is the possible price if we have this. So now, first of all, we have to analyze it, right? So before sitting in an examination, you have to learn it, right? So in supervised learning, we are given the question, which is a predict, as well as the target, which is the solution, which from where we have to learn it. So your model sees the question. Okay, this is the question. This is the information given in a question. So any problems has their own information, right? And they ask us to predict something. And also we are given the solutions as well. So your model will find the relationship between the price, floors, relationship between solutions and problems, and analyze patterns from the data, right? And then get trained. So over here, this solution is acting as a supervisor for this model, for this question. So basically, this is helping your model to learn, right? If you don't have solutions, for example, if you sit for a mathematics examination and you want to prepare for it, if you don't have the solutions, how will you understand the pattern, right? So over here, you should have the solution. You should that is called target variable, right? So you give some features based on that target, which is price, and then algorithms learns from this, and then you give new examples which will be without target. So now your model trained on this. Now you want your model to sit in an examination where you only give this information, you only give this particular question, and then say, okay, predict the house prices based on the given info. Say for example this. Now your model will predict this price. You don't have to give this, because now it's something will introduce to evaluation system where it will check yes or wrong, right? Which is the task of an examiner or a test checker. But as of now, once the model is trained, we can give only this question. We'll have the answer later on where the algorithm tries to predict the answer. So supervised learning is the type of machine learning in which models are trained using well-labeled training data. So labeled means every data is labeled well, right? So this particular information is labeled well out here. This particular information is labeled well out here, right? So you have the question as well as the solution, and machine learning tries to predict the output. So here we mean labeled means, what does labeled means? It means that, let's say you're working on spam or ham prediction system. So for every email, for example, email number 1, you have the label related so that your model learns, right? So you have the data, you have something like this data, and for every email you have the whether for the model to learn, first of all you have to make it learn by the historical data. So you have the email number 2, it is ham, email number 3 is spam. So the label or the thing which you have to predict is given over here. So this is what the label is in machine learning, where it is label means that for every given input feature, in this case email, we have the correct label for that, whether that email was that, and then we ask our model to learn from this data, right? And then after our model learned, we just say we just only give emails, and then tries to predict what will the possible output from that. Okay, so supervised learning problems can be classified into 2 ways. So first ways is regression, and second ways is classification. So we'll talk about classification, regression in detail. This course focuses on regression, but if you want to learn more about complete ML with earning opportunities, I recommend CS01. You can go and watch that. But in regression, supervised learning problems can be classified into 2 set of problems. The first problem is that your target variable which you will predict is continuous values. So assume that applications like prediction of house prices. So in this house prices, you have your target variable. You have a target variable which is the house prices, which are continuous value. So if you don't know what is continuous, discrete, etc., you can skip to the data fundamentals lecture where I'll be talking about data fundamentals in detail. Right. So over here a target variable which you want to predict is continuous. So for example, the house price, your pricing example is continuous, right? A revenue prediction, sales prediction, etc. So these are the examples of your regression values, right? The problems where we want to predict are when we predict where our target variable is of continuous value. But in classification, our target value is in discrete. Whether the person has a cancer, yes or no. Whether the answer is correct or not, yes or no. Whether this is true or not, yes or no. So this is sort of classification problems. In this course, we'll only deal with regression problems. If you want to know more about things in detail, you can go to classification problems. However, we'll talk about each things in detail as we go. Now, I think this is something which we are done with whole machine learning. Now you may think, hey Ayush, where is unsupervised learning? Where is reinforcement learning? This course is intended to make you inclined towards the learning the core stuff of it. So I'll just give you the idea what is unsupervised learning is. Unsupervised learning in which you don't have this solution. You only have to make this any sort of sense of logic from out of the data, and then get the prediction anyway. So in unsupervised learning, you don't have any sort of supervisor. In this case, you don't get any examples, you don't get any questions, you don't get any help of supervisors, you just strictly sit in examination. And then you have to learn from it. You have to analyze the questions and then make a pattern sort of it. Right, so that's what unsupervised, which is the most challenging today, and most of the work is being done in supervised learning, but unsupervised learning is very challenging. But that's something we'll take a look at later on, right? That's something which we'll take a look at later on at the end of this course. But I want you to stick with, as of now, is with supervised learning, and let's try to learn the core of supervised learning and master it. Hey everyone, welcome to the another module, which is linear regression. So what we'll try to achieve in this module is we'll try to learn in depth about linear regression. We'll try to understand each and every concept. So the table of contents and everything is already introduced to you. So I hope that you know what you're going to learn. So before starting of this video, I would like to talk about the two terms right now. So talk about linear and then talk about regression, as this course is only based out of machine learning core and linear regression. So we'll talk about only these two terms, which is linear and regression, separately. So what is linear? Linear is something which is like a straight line, so you might have seen linear graphs where it is just a straight line, right? And then what is regression? Regression is a sub problem of your machine learning. It's a sub problem of your supervised machine learning task, where your output variable is output variable of your the output variable or the target variable which you want to predict is continuous. What is continuous? We have already seen in our previous lecture on data fundamentals. So continuous means the height of the person. If you want to predict the height of a person, to predict the stock of the particular company, or if you want to predict anything which is uncountable, or I would say non-finite, or something which is continuous, like height, age, etc. But there's discrete, where if your target variable is discrete, where you have a finite number of possible outcomes over there, then that's a classification problem. So we are going to approach regression problem out here, using one of the algorithms called linear regression. So now you might have seen in our definition of machine learning that we use how we extract patterns from the data. So this is one of the ways we are going to study, one of the ways for extracting patterns from our data, and then this sets a very nice base. So once you have this, you'll be easily able to learn logistic regression and other things. But if you fully want to learn, I suggest CS01 course for you, which is the best for you maybe. Yes, so let's get started eventually, and let's try to talk about what are the things which is needed out here. Cool. So over here, you're seeing something known as we use ML for estimating or establishing relationships between two variables. So that's something is very confusing. So I would like to take a time to make you understand what exactly I mean by that. So over here, what I exactly mean by that is that assume that you have that you're working on something like, let's take an example that you are working on cancer. You predict whether the person has a cancer or not, right? So predict whether the person has a cancer or not. So you're given some of the information about the person. So you're given about the BMI of a person, which is blood, which is BMI, and then you're given the weight of the person, you're given the height of the person. So you're given these three features. You want to predict whether the person has a cancer or not. I know these features are not enough, but assume that based on this hypothetical situation, based on these given features, you're going to predict whether that person has a cancer or not. Okay, so how we are going to approach this, and how exactly we are going to take up from here. So one thing which I just want to tell you is how we are going to approach this. Like, how can we relate this to establishing relationships? So you have these feature, you want to predict whether the person has a cancer or not. So over here, you want to establish a relationship between every feature you have. So you want to establish a relationship between these two things. Whether there is any relationship between BMI and cancer, whether BMI has any effect on the person is having cancer. So if BMI is high, whether the person is having cancer, BMI is low, the person is having a cancer. So we want to identify the relationships out of it. Identify the relationships or something like identify any sort of any sort of any sort of relationship between over there. Out there. So you want to establish the relationships in variables like the BMI and the cancer, or maybe establish a relationship between feature number 2, which is weight of the person and the cancer. So does weight of the person affect whether the person has a cancer or not? Does this particular info affect whether the person is going to have a cancer? So over here, what exactly we use ML for exactly identifying that, exactly the same thing. We use ML for establishing the relationship whether this particular feature is going to affect my output variable. In this case, where my age or weight or BMI will affect whether I have a cancer or not. Okay, individually, like this feature affects or not, this feature affects, if yes, then how? Right, by what units, etc. So these questions are answered. So we'll take a very nice problem statement to make you understand this particular statement, which will be easy for you. So let's take an example. You're a marketing strategist, a data scientist for a company, and basically this is what the data scientists do. Eventually help the marketing team or help the decision team to take certain decisions, or marketing team to take some certain marketing steps. So you prepare a marketing plan for a car company. So you have a car company, and then you want to prepare the marketing plan, how the marketing plan should be there for car company. You have to help the marketing strategies out there with your data-driven decisions. So the first is manufacturer of the car. So you're given these particular infos about the car, the features about the car, right? So you're given these 1, 2, 3, 4 information about the car, 4 features of the cars, and based on this you have to make a marketing plan. Okay, so you have to make a marketing plan. So in what way? The marketing strategist asked you, as a data scientist, asked you that tell me which info we should highlight out of all these infos in our main ad. So when we make our main ad, which info out of all of this we should highlight so that we make maximum of sales for that car. Understanding what I'm trying to say. What I'm trying to say that there is a marketing team sitting out there, you're a data scientist out there, they ask you that out of all these features, can you recommend me which info I should take and show it in the ad so that I have a most of the market, most of the sales. Okay. And just I don't want the prediction, I also want to know the following questions. So marketing team is sitting and asking these questions. So what are those questions? Questions is there any relationship between that particular information in the car? So is there any relationship between the manufacturer of the cars and the sales? So of course, as we think that, let's assume that manufacturer is BMW, brand is high, right? But it may have, like, there might be a very nice relation. It may happen that the brand manufacturer of the car is high, but the sales might be low because the brand is super high and expensive, right? But if you have something Wagoner or low budget, the brand is Tata, Tata Motors and all, so they produce less expensive, so the sales will be also very high. So the manufacturer of the so you have to understand, is there a relationship? If yes, then what relationship is available between both of them? And that answer is, how strong is your relationship between that particular manufacturer and the sales? You do for every model of the car, engine size, horsepower, right? So identify what is the relationship between a horsepower and the sales. So if horsepower is high, what is the sales? If horsepower is low, what is the sales? Right? If engine size is high, what is the sales? If the engine size is low, what is the sales, etc. Which info contributes to the sale? So which information, sometimes it may happen that that any particular information may not contribute, may not have any effect. That does not really make sense. Just like in pigeon example, which is senseless, right? How accurately can we estimate the effect? How accurate we are in estimating the effect of each individual features, each individual features on our output variable Y. And is the relationship linear between both of them? And what exactly we say that the relationship is linear, which means do they follow the linearity or do they follow the straight line convention? So what is linear? Things which are in straight line or something in any straight line. It should be linear. It should not be like this, right? It should be linear. So you might have studied in lower classes about that. So I hope that this gives you a very nice sense about, we use ML for estimating the relationships. In the next video, what I'll try to achieve is what I want to do is to work about geometrical understanding, right? So we're going to work about geometrical understanding of our regression. So we'll actually go ahead and then talk about how we can estimate the relationship between features and the outcome variables in an easy way. So let's go ahead and talk about that. So now we'll talk about something which is we have studied about, this is what we have to do. This is what ML is about, estimating relationships. So let's start talking about how we estimate relationships between variables. Right. So let's get started and actually talk about that, right? So over here, before going on that, let's talk about what does it means to say that data is linear, right? Data is linear. What does it mean? So data that can be represented on a live line graph, right? It's a data which can be represented on a line graph, and there's a clear relationship between two variables. There's a clear relationship between two variables that the graph can be shown on a straight line. So there's a clear relationship which you're saying, and one unit increase in x is showing a constant increase in y, right? That's what the data is said to be linear. You might have studied in lower classes. Just for those who just want to recap, I just told about that. This is an example of a linear data. This is an example of a linear data. This is an example of a linear. Ignore the lines as of now, okay? Ignore the lines as of now. Just go about the data which you have out here. Just go about the data. So you see that the data is linear. If the data would have something like this, very random, there's not showing any clear relationship. There's not showing any clear relationships between variables, then it might have not been. This is called a non-linear data. So data is linear over here, and over here, assume that this is your data. So now assume that this is your data. Where on x-axis you have something like the number of years of experience. So you're gonna build a system. So let's formulate a problem right now. You're gonna build a system that predicts the salary of a person given the years of experience of a person. So given the years of experience of a person, you're gonna predict what will be the possible salary. So if the person has a 2 years of experience, you have such number of salary. So you are given a data in a CSV file, or you given a data in an Excel sheet, and in that data you have something like this record, and you have one information available, which is the years of experience, and so assume 3, and there is the label, a target variable, which is going to predict the salary, which is in, let's say, 5, right, which is in $5,000, $10,000, whatever per year, according to Indian market. So over here you have years experience and the salary of that person, right? And this is in 5k. Okay, so if there's 5 over here, then that means 5,000. Okay, so and then you have the data, and then you plot this data over here. Now you plot this particular data over here, because you have only x variable, and then you have y. So you're given x, you're gonna predict y out here, right? You're given x, you're gonna predict y, right? So I just want to talk about one of the thing which is super important right now is this something known as functions, concept of functions. So in functions, what we do, say for example that this is a function which squares the number, So this function takes the input value of x, and outputs y, which is a square of x, right? So when you plot this function, this looks like a parabola. This looks like a this is a parabola, right? So x, and then f of x, then it takes the input value, does some processing, and returns the square of it. Which is a square, right? So in this case, we wanna build a function f. So we wanna build a function f. That takes up years experience of a person, and map this, which we call this x in this case, the input value, the thing which you're going to input to the model, like give this input. For example, in cancer prediction, we're going to give the input like BMI, weight, age, and to give input. And then as output, we want to predict what will the salary of the person. That's the output out there. Which is the salary of a person. So this does something. So this does something with this input value and then returns you the salary. So now we're gonna build a function. Now we're gonna build this black box thing, this thing out here, this particular whatever processing that does with the years experience. So we're gonna build that. For building that, we wanted to learn a algorithm called linear regression, where it helps us to building that particular processing that takes up your input feature x and does some processing and returns some values y. Okay, so how do we learn that function f that takes the value y, years experience, and returns the y? So let's start off with a geometrical understanding. So assume that you have the data plotted over here. On x-axis you have years experience, and on y-axis you have salary of the person. So this is the data which you plotted. I hope so that you know data plotting, at least given the tables, tables out there. You should be able to plot data out here very easily, right? So when you plot this data out here, now you look the ignore the black line as of now. You plot this data. Now what you do, you find a straight line. That best fits the data. You're trying to find the line that best fits the data. So why do we find the line that best fits the data, right? That's a good question, right? So assume that you have 4 years of experience. You have 4 years of experience. So what will be the possible salary of yours? So if you have the 4 years of experience, the actual value states that you will be having somewhat like, I think $8,000 for a year, right? But your model, so basically the intersection from x and in the intersection point. So basically the intersection point is this point. So this is the intersection point, and this intersection point is your model approximation. So let's talk about what exactly this model approximation means. Model approximation is something like your model approximated. So as we say, for example, assume that you have your examination, and in the examination similar questions comes or exactly same question comes, right? So it might happen that your approach might be different from the book's approach. It may be similar question, so you answer differently, right? So you over here don't exactly answer the same thing, you written differently. For example, in science exam, you don't write exact the same question, exact the same answer. There is some of course you have approximate answer, right? Not exactly similar to the original answer, not exactly similar to the bookish answer, but similar to that. So if someone asks what is photosynthesis is, you might write your answer in different language, but the original may be different. So there should be some difference between both of the answers, right? So in the same way, if someone asks a question, what is the salary of person with the years experience 4, where they give the years of 4, we have some processing done, and then it results in some values. Okay, and as of now, we are trying to understand geometrically how it should work. If someone asks what is the salary if the person has the 4 years of experience, that says that if I ask what is the years experience when the years experience is 4, it says that the actual answer is this. Actual answer is this with the original, but there's of course the difference. But there's of course the actually model approximated this straight line. As of now, this is straight line. So this is straight line. So we found the straight line that best fits the data. Okay, so we found a straight line, and then we gone and see, okay, this is the point of intersection, and this is your model prediction. This is your function approximated value. Not exactly same, but similar to that. There's small difference between both of them, right? Right. So now you may have several questions. Please don't worry. We'll tackle each and every question in detail. Okay. So let's start tackling each and every question in detail. Now over here, what you're seeing is that assume that this particular information and this particular information. So there is of course the difference. There's a model approximation and your actual value. So what is the difference between model approximation and actual value? As I again told, in science examination for a particular question, there might be different answer, but concept is same but different answer, right? In their own words, in bookish language, but you might have different answer in your own language. So there's of course a difference. So if the difference is high, that means the concept is not same. So it will, so your examiner will match your answer with the original answer, and if the difference is similar, then that's good. But if the difference is high, the dissimilarity is high, then the answer is wrong, because you might have written in when you were told to write the photosynthesis, you came and written something like respiration, right? So that will be wrong, right? So I think that's a very good example to state over here. So now the actual answer, though someone asked about photosynthesis, so actual answer is the bookish answer, which is so correct, which is 100% correct. We call that thing as a ground truth, and then you written that is a student approximated answer. That student might have written some answer. So we match both of them, but take out the difference, how similar they are. If the similarity is less, that means that the answer is correct. But if the similarity is high, that means that something is away, right? That something is wrong. That you've written a respiration instead of photosynthesis. Chemistry is something. Never mind. So this is what the difference between model approximation. So in this case only, your model says that for this much of experience, this is the particular value of this particular salary, but your actual value states that this. But there's a difference. So higher the difference, bad your line is. But why did I say that best fit line? But why did I say this best fit line? So why did I say this best fit line? Because, for example, assume that your line is like this, which does not best fits the data, which does not fits the data well. So now, if you have 4 years of experience, if you have 4 years of experience, the model approximate is that intersection point, which is nothing but $4,000. But actually it was 6, right? So the difference is high. So the difference is super high, right? But actually, if you see that this is your actual value, so this is your actual value, right? This is your correct answer, but this is your model approximated value. This is a model approximated value, right? So there's a difference between. So over here there is a small difference, but over here it is a bit large difference. So that's why we want to find the line which best fits the data. So now, for example. So now for example, assume that we go to this line this is the best fit line which is out there, which is over here. But assume this line. We have 4 years of experience. This is, but actually the correct is this one. So of course there's difference, but this particular line which best fits the data, right? Which best fits the data, we are using that to make prediction, right? So now I think you got a way to approximate your values. Now let's talk about in detail. Okay, let's talk about in detail what exactly I'm trying to tell is how exactly we got to our answer. So what our problem was that we wanted to extract patterns from the data. Basically, you want to learn from the data and make intelligent predictions. So we're going to find the best fit line. That means learning that best fits the data. For example, you want to learn, you want to train your mind that best fits the concept, best fits the concept, and around that concept you utilize that concept, and that's called hypothesis. You utilize that step to further make predictions or to further solve the question. So in this way only, it first of all makes the best fits the data by a straight line. It should be linear, right? It should be linear in a straight line, and then it best fits the data, and then we can use this best fit to see, okay, if you have, currently we have only one input value. If there's more, then there's several things, but you have only years experience on to predict. Based on years experience on predict salary. So given that, you can just go and then this is the point of intersection. So this is your y value, which is in this case the y value is on y-axis. So we simply predict that. I hope that it makes sense. If it does not, please review the lecture again and again. And if you still don't, please go and review the concepts of class 8 and 9. Okay, why to find the best fit line? That's a good question about why exactly we want to find the best fit line. So I have given a very nice example out here, which I have just described to you. So now you might have question on how do we find this best fit line? How do we find this best fit line? So let's go ahead and let's try to find this, how exactly we go ahead and find the best fit line. So now you might have question, okay, now we have the data, like how can we find the best fit line? The first solution in your mind might come that we can plot our data on x and y axis and then use our drawing skills to draw a best fit line. So you can simply say and draw like this and then draw a best fit line. But the major defect is we cannot really make predictions from that. So how can you make exact predictions from it? Tell me. This one defect. How can you give me the exact prediction? You cannot give me the first of all exact prediction. You can just tell I've just told over here approximated, right? Not exactly the same what model approximate. Just approximated. That's the first effect. And the second effect is what if you have more than one features in information. For example, currently it's x and y only, where you have years experience to predict the salary. But what if you have years experience, the designation, the skills, the ratings, etc. So 4 axes, 4 input values, you want to predict one salary. So this is a multi-dimensional thing. You cannot really plot a straight line. That's the first solution cut, where you cannot use your drawing skills to draw a straight line, which the best fits the data. So how can we get this straight line? So the second solution is that as of now, let's go ahead and talk about only one thing, which is you're only given only one information, which is x, which is the year's experience. You want to predict the salary. That is only one. So how can we do this? So second solution might arise that you might have seen this in your early classes. Y is equals to mx plus b. This is the equation for any straight line. So y equals to mx plus b is the mathematical equation for a straight line, where m indicates the slope of the line and b indicates the intercept of that line. Slope means how much y changes when x changes, and intercept b, which is the y-intercept, where your line cuts at y. Right. If you don't know about the concept, don't worry. I'll just recapitulate a little bit on this. So what exactly slope in this example? So slope in this example states that how much my salary will change. How much my salary will change if my years of experience will change. That's the slope. Which says how much your y changes, the salary changes when x changes. That's the slope. So m over here is your slope, and m is also the coefficient of your x, and x in this case is a years experience, plus the y-intercept, where at exactly your y intersects. And y-intercept is one of the major thing, because we'll talk about bias term later on. But over here, if you have this y-intercept over here, then y-intercept also plays a very nice role. So over here, this is the y-intercept where your y cuts on the y-axis. So now there's one interpretation which we can get from this, that if we are able, so this particular line is fully dependent on this in these two parameters. Only these two parameters can change this line, right? One is slope, because x will be anything, right? But m and b determines how this line should be. So slope and the y-intercept. So if y-intercept is different, it should be like this. It should be like this. And slope is different. It should be like different shapes. So that your straight line, your best fit line, depends on the slope and the b, which is the bias term. So a straight line is dependent upon slope and the y-intercept. So if you're able to find the slope and the best intercept that best fits the data, we got a new line. So very interesting an analogy is why I'm saying that they are dependent, why I'm saying that that our straight line is dependent. For example, so you have this data where I plotted the very small amount of data, and in this example assume that we have this particular assume that we have three different best fits lines. Let's go with the first one. This over here, our slope is different and y-intercept is different. That's why it is not perfectly fitting our data. So now we tweaked in a way that we changed the slope and the intercept. We got to this. It okay fits the data. But over here, which again changed and seen, then it fits the data very well. Right. So your straight line is dependent upon M and B. So if you're able to find the best slope and the best y-intercept for the particular data which you have, you will be able to have the very good line. Right? That's a nice analogy. I hope so that you're getting what I'm trying to tell. Is I'm just trying to tell you that you want to get the best M, which is the slope, and the best B, because it determines your values. It determines your X values. Right. So I hope that this gives you sense that so if you're able to find M and B, we'll be easily able to get the best fit line. I hope that this makes sense. Okay. I don't need to again repeat it again and again. So this is a very dummy example which you're seeing in front of me. Is about horsepower and sales. So you're given the horsepower of a car. You're given only one information. As of now, as I said, we'll only go with one information. So you're given the horsepower of the car. Your RFI based on horsepower, what is the sales for the car? Right? You identify that. So to find the best fit line that best fits this data. So if you plot this data, it should look something like this. So if you plot the data, we have to best fit the data. So sometimes you don't need to really draw, make your graph. Find the equation. You find a straight line or linear equation. Not linear equation. Yeah. So the straight line equation that best fits the data. Okay. So you build this function f. That takes in horsepower, and then multiply, and then you have the straight line equation, which is used for making predictions. So we need to build a function f that maps your x, which is the horsepower, to the sales. Establish a relationship between both of them. So here we are multiplying with m with x, so that we can say that m is somewhere. So we'll come to that. But over here, we want to give the function horsepower and multiply horsepower with the slope, which is how much sales changes when horsepower changes, plus y, which is your y-intercept, where it intersects on y-axis. So now you might have question that why we multiply and how does this affect the output. So when we multiply, what effects does it goes on output variable? What effect this y-intercept gives to the output variable? That's something we should talk about in interpretation of our coefficients later on. But as of now, you can get that this is the equation where you put in the values of x, you'll get the particular value. Okay, you can see over here that let us assume your slope is 3 and intercept is 4, which is dummy as of now. So we take a function. So now this is a function like this. Now you have built your function. So you simply give the value of x and then get your answer. And then you get your prediction, which is number of sales which you'll get. Okay. So now you might have several questions right now, like how can we find our best M and B? Like currently we have just taken a dummy example. So how can we find best M and B? What exactly this M and B contributes to the sales? Why exactly we use it? First of all, at first place, why exactly we use it, etc. That will be answered in later phases as you go. But as of now, what I just want to tell you, you have got to know that very nice geometrical understanding of linear regression, and I hope that you will really utilize this to recapitulate the concept. So if you want this notes, you can get that from my website. You can also enroll in the course which I'm teaching in fully ML Pro, which is from teaching from very basics to earning opportunities, etc. So I hope that you will enroll in that. Let's catch up in the next video. Tab tak ke liye, bye bye. So, folks, we are going to continue our journey on regression analysis. So, in the previous lecture, we had a talk on this dummy example, and we have shown that how each, we have M and B, and how this how horsepower has its own weight, and then we have an intercept. We have talked about this. If you haven't seen my previous video, please go and see about that. So, our main idea was how can we find this main M and this intercept, which we usually call as B. Okay, so my question was how to find these two terms, because your best fit line depends on this M and B only, right? So basically that was the basic question, that your best fit line depends on this. So if you want to get the good fit line, then you need to find this M and intercept, which is a slope of the particular variable, how horsepower and the intercept of that particular variable. So I hope that makes sense. Now what we're exactly going to do, we're going to study about how can we find best M and B for your data, which is eventually, in other words, best fit straight line in your data, right? So what is the sum of the possible way which we can think of? So over here, what is one of the possible way is to hit and trial different values of M and B and see what works well, right? So for example, in this example, you're gonna use build a function f that takes the horsepower as an input, and predicts the number of assails. So if you want to promote your car with that horsepower, what is the possible number of assails you're gonna get, right? So build a function f that establishes the relationship between your horsepower of a car and the sales, right? So predict how much sales would be done if we actually use the horsepower as an or how much sales are based on horsepower. What is the relationship between them, right? That is the one question out there. But what I want to convey is that over here for building, let's assume that X is a horsepower. You have MX plus B and M for finding the relationship, right? So over here, M and B, we need to find out. So over here, you cannot just plug anything. Like we have seen that if you plug anything, we're not going to get a best fit line. So what can we do? We can try out several values of M and B. So we can try out 1.1 and then some 1.2, and then with these values, given the X value, we can test how well these values are by plotting it on a straight line like this. So we plot on a straight line and see how it performs by hit and trial, right? We first of all perform like this. And then the next what we do is we try another value and see if you're getting the best fit line. So what eventually you will do, you will try several set of M and B, right? And then you'll try to plot the best fit line or plot that equation. And once you plot it, you will be able to see, okay, this is the best fit line or this is not. So you'll plot and see how is it the best fit line, right? So hit and trial different values and see what works well. But it has several problems. The first problem is it will be very hectic. And time consuming. Okay. First thing. Second is what if you have a 3D or 4D in higher dimension of data, right? You might have higher dimension of data and you may not be able to plot every time and then see, right? So in that real world data will not look like this. It will have a millions of examples, millions of input features, right? So we exactly want to talk on that. So we cannot really plot and then see against, right? So that second one is it will be very hard for us to eventually plot the data and see every time. So eventually hectic and time consuming. So we need to cut that approach out. What's the next approach? We have an optimization algorithm, which is based on this hit and trial only, but we do it very strategically. You learn how we do it very strategically using mathematical process, right? So I hope that will make more sense when I actually go into this. Now, so let's see how to see what works well, right? So how to see what works really well. So over here, as of now, we have seen that we can use optimization algorithm to come up with that. So, but before that, we need to see what works well and what not. Then we can come to this optimization problem. So if we want to see the graphical problem, like over here, we have two sets of data. So the first set of data has this data, and then you plot the best fit line, and this is the best fit line available for your data. And over here, you don't have the best fit line. So this particular equation is wrong, but this particular equation is correct, right? Why? because this particular equation has a best fit line, or this particular line fits the data best, and this particular line does not fits the data well, right? So that is one of them. Now, over here, you can see that it is not fitting the best fit line. So what is the conclusion which I want to make is, if you want to see the best fit line, which I've already seen, is will be this. But by now we are only seeing, or we are only telling by seeing the data. We are only telling how is this the best fit line, is the best fit line by only seeing the data. But data will be, you have only the horsepower as of now. There will be a lot of input variables. For example, you may want to establish relationships. You may want to establish a relationship between maybe horsepower and then, another one, which is the brand of the car, the social media, engagement of the car, and blah, blah, blah. I mean, to find the relationship where all of these three to a particular variable sales. So we have to find, you will be getting 3D. You will learn about this multiple linear regression soon, but you will see that we will have 3 dimension of data, even 4 dimension or 5 dimension of data, right? But it's not always possible to plot. It will always not get only some 100, 200, 300. You'll get millions of data points, right? You cannot plot everything, right? You cannot plot and then see that how it's performing. That is a graphical method for general understanding. It's not for something which you have to do in real world, but sometimes it also comes in handy if you have a small amount of data, but eventually you'll have to deal with numerical way, right? So for example, when you plot the line, you can, for example, assume that you have a equation f of x is equals to x squared. So the graphical will look like this. The graphical is parabola, but you cannot eventually use this parabola nicely to get your answers. For larger values, for subset you can do, for 2 or 3 you can do. But what if 1, 2, 5, 9, 9, and 9? So you cannot even do that. You cannot even try to use this parabola to do that. You can eventually do that, but it's very hectic and very not possible. Sometimes it's also not possible, right? So in that case, what you will do, you'll utilize its numerical way, x squared. F of x is equals to the function numerical. This is the function, this is f of x graphical way, and this is the numerical way. This is the numerical way, right? So you'll go with the numerical way. You plug in 12599, and then you just 12599 times 12599. You just square this, and then you get it exact value, and then you'll get it exact value, right? So just in the case of linear regression, okay, we have the graphical best fit line at our data, but this graphical line is represented by a numerical value, which is mx plus b. We need to utilize the numerical as well. I hope that you understood why the importance of numerical is given over graphical for understanding as well. So now let's come to numerical representation. That works really, really well. Over here, which you're seeing in front of me, is that you have some data points out here. So assume that this is your one data point, this is another, this is another, this is another, this is another. So you have some data points out here, right? You have this blue points are data points with labeled examples. So this data point has x value, this, and y value, this data point. So it has the labeled example y as well. Please note that we're dealing with supervised learning algorithm, and we should know that this is the y. This has y. Right? Cool. So over here, assume that your x is equals to 24. Okay, your x is equals to 24. Your predicted would be, assume that this is a straight line. You plotted the best fit line. So this is the best fit line which you have in your data, right? And then x is equals to 24. This x is equals to 24. If you go above, this is actually the ground truth. This is actually your labeled value. But over here, this is what your model predicted, because model will predict at the point of intersection. The point of intersection is your model prediction, right? For example, if we say x equals to 20, x equals to 20 would be gone. And here it intersects, right? Because we don't have any example. We don't have any x equals to 20 label in or data point in your data, but over here the reason why we best fit line, so that we can predict like this, and then if we see the y value, we have 45 as the prediction, right? This is how we make sense. But over here, but let us assume that this value 24. For 24, your true value, your ground truth means true value. For example, what is ground truth? You have scored 45 out of 15 years test scores. This is the 45, which is the correct value, which is the truth. But your model
predicts that you have scored 57 out of 50. So this is your predicted value or approximated value, and that was your 45 out of 50 is your ground truth. 45 is the ground truth. So over here as well, for this particular x1, for this particular data point, x equals to 24. X is equals to 24. So x is equals to 24. X is equals to 24. Your predicted value, your ground truth is 38. Right, for x equals to 24, but the model prediction lies over here at the point of intersection. So when you just go above, you see the point of intersection over here, and the model predicted value is nothing but 47. Right. So actually, the correct value for x is equals to 24 is 38, but your model approximated or predicted 47. So of course, there's some sort of errors, you know. For example, you might have noticed that when you're actually that in class 10 DNA, you know, when actually DNA copying is done, there are variations, right? There are some errors. So when model approximates, it comes with errors as well, right? So those errors between approximated and correct value, 38 is the correct value and 47 is the approximated or the model predicted value. The model, what model thinks x equals to 24, and what model thinks decided by the straight line, right? So that's why we say that best fit line really works. For best fit line, we need to have a best fit in the data. Then it will perform very well, right? So the difference between the predicted, which is approximated, and the actual value, the correct value, which you call as a ground truth, is called nothing but residual or difference of errors, right? So it's called residual or difference of errors. Let's take a look at another example by taking a look over here. So assume that you have this particular data point. Assume that this one. So over here, you have x is equals to maybe 12. And when x is equals to 12, your correct value, as well as your correct value, the blue point is ground truth, as well as your model prediction lie on the same point, which means yi, which is your ground truth, for x equals to 12, and y hat I, which is your model predicted value, are on the same point, which means that they both are equal. And assume that your model says that you will have 1200 samples, 1200 sales. Your model predicted 1200 sales, and actually 1200 sales was done, which means that your model was perfectly accurate. Your model is perfectly accurate, right? So in this case, the error will be equals to 0. Right. So I'll take one example to make you understand. Assume that you're working as a data scientist in Ashram shop, and over there you're gonna predict based on past data. You're gonna predict what will be the number of sales in the next day. So your model says that there will be 200 sales next day, right? But actually 200 sales was done, which means they are on the same point. So over here, with x equals to 12, then a y hat is equals to 37. And when yi is equal to 37 and y hat I also is equal to 37, which means both are equal and the residual between them is equal to 0. Let's take a look at another example. When your x is equals to 24, over here, the blue point as well as the predicted value is on the same point, which means that your predicted as well as approximated are equal. Let's take a look at another example. When your x is equals to, let's take 29, you have this as the predicted value. This as a correct value, which is the ground truth, and this as your approximated value. This has your approximated value. This has a correct value, and so the difference between both of them is residual. So your correct value is little bit more than the actual predicted value. So what predicted value is nothing but the point of intersection when we draw from the x-axis. I hope you are getting what I'm trying to say. I'm just trying to justify that the difference between the ground truth as well as the approximated value. Nothing else I'm doing. I'm just trying to justify that. Okay, let's read something. For x equals to 24, approximated model predicted is 47, but the ground truth is 38. So the error term on error between y and y hat, which is y hat means which is approximated and the ground truth is nothing but 9. So the error term is 9. Higher your error is, bad your approximation is. What does this mean? Higher your error is and bad the approximation is. For example, assume that you are in an ice cream shop and then and your model predicted 1200 sales, which will happen the next day. Says that 1200 sales will happen, but actually only 400 sales happened. So the difference between, for example, you're giving a maths test, right? You write a very different steps, write a different answer, very different answer rather than the actual answer. So you're absolutely wrong, right? You should be at least close to it. When you're giving a science examination, you written some text, which is your answer, which you think is the answer, and there is a correct answer in a marking scheme, right? There's a correct answer. So what your teacher will do, your teacher will match with this. If the error is so much in this, is so much, the difference between so much, then the error is bad. So the difference between the yi and y hat I and yi, which is the actual value, and there's a model predicted value. If the error between them is high, then bad your approximation is. Why? I have given you a very simple example. One example was ice cream shop, which is 1300 and 400. So error between them is very, very high. Right. That's why the higher the error will be, bad your approximation will be. Right. So I hope that makes sense about this higher error and bad approximation is. But what we can do, for evaluating how well our line. So, but why are we learning all of these things? The reason why we are learning, we want to identify how well this line is based on numerical representation. By seeing, we can tell, okay, this is good, but numerically we also be verified, right? So what we do for every sample which you have in your data. Right. So what you do for all these blue points, you take out the difference of errors for all these data points. For example, y1, which is this y hat 1 minus y1, which is equals to 9, right? Which is equals to 9. So you take it out for the first one, and then you do for the second one, y2. So if you see over here, y2, where is y2? Yeah, this is y2. So this is your predicted value. And this is your ground truth. So the difference between them is 44, which is the predicted value, minus 45. You get minus 1, right? So this is the difference between predicted and the actual value, right? And then you have for y3. For y3, you have difference of errors, where you have y3, which is the actual value, and the predicted value, which is minus 4. And then you have y4, and where the predicted and actual value are on the same point, you have 0. And you do for all the data points away. These blue lines and blue points are nothing but the data points. These blue points are nothing but the data points, right? So you calculate for example, what you do eventually. So let's take a scenario to make it a little bit more easy to understand, right? When you actually, let us assume you have 10 problems in an exercise. 10 problems, you have the problems 1, 2, 3, 4, 5, 6, as well as you have the solutions. So what do you do? You make your own 10 solutions. You make your own 10 solutions based on the questions what you have learned. You make your own 10 solutions, right? And these solutions, let us assume that this is your name is model, and you approximated this or predicted these solutions. Now what you do? You match it with this. You match with the correct solutions given in your book, right? So higher the difference is, bad your answer is, right? Well, that's what we are doing over here to evaluate how well our paper gone is we match each and every predicted value with that respective correct value. For example, question number 4, we match the question number 4 with question number 4, the correct answer as well as the so we just match and check how well it is, and we give our marks based on that. So just like this, for evaluating how well the straight line are, we just have the straight line, and given that straight line, we evaluate model predictions minus the correct value for all data points available in your data, right? We do not do for data points which you don't have any label for that. For example, we cannot do for assume that we cannot do for, let's say, 2. We cannot do for, let's say, 2, right? We cannot, because we do not have data point for that. But we can do for the maybe 7, right? We can do this because we have the prediction over here, and then we have the model correct value over here. Okay. I hope that makes sense. And then you take out and then you have a n number of errors, or we can say e number of errors, ei's. So you have e number of errors. E will be equal to the number of data points which you have in your data, right? So it will have the e number of errors. How? N1 minus N2. N1 denotes y hat I, and N2 denotes yi.
and then you have negative values as well somewhere. So there are two issues which we come. We have several number of errors. How can we combine all of this into one single number to better describe our model? And then second one is some of our error terms are negative. So you can see that some are negative, right? So what we do to take care of this? So we can solve the problem. We have the negative sign we can get rid of by two processes, by squaring the number or by taking out the absolute of that number. Absolute of that. So for example, we could simply take out the absolute of this, whatever the answer, which you can take out the absolute or the square. Absolute or the square. So square will just cancel out, as well as absolute will just cancel out. So we have two approaches, either square the differences or absolute the differences. So what we will usually do is we are going to use the square of the number. I'll talk about why we are not using absolute, but there is we also use absolute as well, but I'll tell you later on. We'll just wait for my confirmation for some maybe next set of sections. And then the first problem is solved. Negative. We can either use any of the approach to fix the negative sign, but even after fix it, we have several number of errors. M is nothing but equals to the number of data points, and as I said, your error should be equals to number of data points, because the difference is because you only ask your model to take out the answer. You ask your model to take out the answer as for the questions which we already have the correct answers, so that we can match and test how a model performs. So what we can do, we can take out the average of M terms. We can take out the average of all the errors, E1, E2, all the way around to EM. But then what we can do, we can put that in a summation format so that we come up with the formula. So formula is this: 1 by M summation I equals to 0 all the way around to the M for every EI. So we take out the every EI errors. Here's the expanded formula: 1 by M I is equals to 0 all the way around to the M. So you go from I equals to 0 all the way around to the M, right? Y hat I minus yi squared. So over here, you're taking out the differences, and differences, you're squaring that up and adding the another I equals to 1, then I equals to 2, and then I equals to 3. So please note that you have already studied this summation format, right? So how it will perform? For example, assume that you have a data point, something like this, where you have 1, 2, 3, 4, 5, right? You have 1, 2, 3, 4, 5. So I equals to 1 is equals to I equals to 0, I equals to 1, all the way around the M, right? So you have y1 minus y1 squared, right? So you do for I equals to 1, I is equals to 2, I is equals to 3, I is equals to 4, I is equals to 5. So you do for every data point for all the data points in your data. You add a square to remove the negative sign, and then you have the approximation value by the difference of errors. This is called the residuals, which you will get, and we divide the value by all the summation, all the sum by M, right? I hope that this makes sense. This formula makes sense. So this formula should make sense to you. You know, people usually learn these type of formulas, but it's eventually what you're doing. You're just taking out the differences of the model predicted value and the actual value, is squaring it up to remove the negative sign, and then you're taking the average of all of them. And this comes up with the name of cost function, or we can say mean squared error, for evaluating how well our best fit line is. We will work on a worked example. So why is it useful? First, it is way to evaluate the best fit line. It measures the performance of our model. So higher the MSE is, bad your model is. Why? Because higher the MSE will indicate that differences are also higher. As I said, that if the differences are higher, then it's not a good model, right? We had a talk on that, right? So this is one of them. This is one of the key criteria which you should know. So it is way to evaluate the best fit line, and it is way to measure the performance how well. So higher the error is, bad. So you have to make sure that your cost function is approximately or around 0. So now we come up with the more conventional formula, which is J of M and B. So basically we're evaluating our M and B is equals to 1 by 2M, I is equals to 0 all the way down to the M, yi hat minus yi, which is the difference of errors. We square it up, we take the average. But what is 2 over here? It's because of the convention. But usually people say because of convention. But eventually, when you learn about this optimization algorithm, which I was talking about, this too really helps in getting it in when you actually do the calculation stuff. Sometimes researchers find out easy method too easy to calculations, and these two really helps in that optimization algorithm. We'll see how this helps when you actually derive the formula, but as of now, you can just remember it. Okay? Now, to recapitulate what we have studied, recapitulate what we have studied, is what we can eventually do is that we can take out the differences between model predicted and actual value, and then square it up to get rid of negative sign. And we have several values now. Now we have to simply divide the term by the number of values in your data set, which is take out the average of them. Higher the error is, better your model is, because higher the difference, it will showcase the higher the differences is, right? But there are two questions now. Why we don't use absolute, and what is 2? What is the 2 over here? Or what is the use of 2 over here? And we will talk about the real reason of why we don't take out absolute and why we don't use 2 over here. Right? Why we are not using in gradient descent or optimization section. Cool. So let's quickly work on a worked example of mean square error. That will make more sense. So you have your height over here, and then you have your weight over here. So basically, given height of a person, you're going to establish a function f that takes the height of person and then predicts what's the weight of that person. Right? So given this height, you're going to predict the weight. Right? So now over here, you came up with 0.8x, which is m, plus 9.2, which is b. So you came up with these formula. So as I told that you have your, now what you will do, you will put in the values of x for the known for the only x's for which you have the known label, right? Or the data points only. And you may figure how we came up with this 0.8 is 9.2. It's because I just randomly written it, because I want to show you not how we get this, but how we evaluate its performance. Okay. So what we do, we have 0.8, we have 0.8, which is over here, multiplied by this 43 plus 9.2, which is, you just exchange the value of x every time, 43.6, 44.5 for every x's values. Now what we do, we compare the correct value and the model approximated value, correct value and model. We take out the differences, errors. Okay. We have these errors out here. Now what we do, first of all, we square all the terms and then we sum it all up and then divide by m, which is 1, 2, 3, 4, 5, 5. And then 6.08 is your square error. So when you apply this formula, you will get that. Okay. So basically what we are doing over here is nothing but taking out the answer for every axis and then comparing with the actual answer. Okay. Cool. I hope that this worked example of MS really helped and everything is pretty much crystal clear. Let me know if you have any questions in the Discord community or in the comment box. I'll try to answer each and every question. Now, what we're eventually going to do is talk about the relationships. Talk about the relationships in terms of mathematics, not in terms of life, because I'm pretty much dash up in relationships and life. So please ignore. I'm not good advisor on relationship in life, but I'm good advisor on how can we establish relationships. Okay, we'll talk about the definition of relationships. We'll talk about some notational changes, and then we talk about how to find that beta 0 and beta 1, which I've been waiting for a long time. We have several ideas. We build from a plain English language, and then we go to a level. But prior to this, I would suggest that you're pretty much comfortable with derivatives, the geometrical understanding of derivatives, as well as a bit of, formula and rules of derivatives. It will really, really help. Cool. So now what we need to do is get started with a bit of next sections about relationships. Till then, I'll talk to you later.
So now what we're going to do is talk a bit about relationships. Relationships is one of the most important thing to talk about, because usually people tell you, establish a relationship, and blah, blah, blah. And eventually you get confused what exactly this term relationships means. So we weren't just clear about that, what exactly this relationship means, so that it makes much more sense out of it, right? So over here, what I'll try to do is tell you what exactly relationships are, and then I'll tell about two types of relationships, which is the deterministic relationship and second is a statistical relationship, and why we're going to focus only on statistical relationship over the course, right? So let's talk about what exactly the current thing which is studying right now. The current thing which is studying right now is a linear regression, which is a statistical method that allows us to summarize data and study relationships between two quantitative, which is the quantitative variables, which is that type of continuous variables. So we have seen that supervised learning has two types of problems. One is regression problems and another one is classification problem. So we have two types of problem, classification and regression problem. In terms of regression problem, how can we identify a problem is regression problem? If the target variable or the thing which you want to predict, is continuous data or some sort of a non-countable or non-finite or something which is continuous, like the age of a person, the height of a person, the salary of a person. They are example for continuous values. So if the target variable is of continuous data, then it's known as the regression problems. Then it's known as the regression problem, right? Cool. So linear regression is a statistical method. We'll talk about what exactly the statistical method means, that helps us to summarize data and study relationship between two variables. Now, you may ask, hey Ayush, what do you mean by study relationships and summarize data? So you'll understand more practically later on, but assume that you have a function f of x, that tells you about the price of a house in a certain area given its size, right? So you're given the size of the house. So you're given the size of the house. It will predict the price of the house. This is the output variable which you're gonna get, right? So given the size, you're gonna predict the price of the house, right? So what does this f tells? F will establish the relationship. As f will tell you about what is the relationship between these two, right? It will tell you what is the relationship between these two, right? That's the first thing which the linear regression tries to answer this. And second, it will summarize by how, if we increase size by this much, by some unit, then what will be increase in price? So if we make price, if we increase size by 10 units, what will be the increase in price, right? That's what it tells. It tells you about the relationship. It tells you about if one increases, what will happen to another, right? We'll study about interpreting the coefficients soon. But that's what it conveys, that you have relationship between two quantitative variables, where you have a particular over here, which is it tells you about the two quantitative continuous variables or features. Okay. So assume that you want to predict the sales of a particular car given these particular features. So build a function f that takes the manufacturer, that takes the model, that takes the engine size, and that takes the horsepower, that takes all these four input features and predicts the sales of a particular car. It predicts the sales of a particular car. So basically we tell, okay, this is the manufacturer, this is the model of the car, this is the engine size, this is the horsepower, and predicts the sales. So how this function f, which will eventually help us, the function f will tell that how this manufacturer is affecting the sales, how this model car is affecting the sales, how this engine size is affecting the sales, and horsepower is affecting the sales. So we can figure out which of the following is affecting more of the sales. Like if we focus more on manufacturer, then for example, assume that model of the car affects the sales the most. So we can focus on model of the car to brand it up to get more sales, right? Because this is generating most of the sales for us. Or if this is generating, then we can focus on showcasing engine size, or we can focus on showcasing horsepower, or we can focus on showcasing manufacturer according to our analysis. That's why I say it helps us to summarize and study relations between these variable and output variable y. Okay. So these variable which we give as an input are called explanatory variable or independent or predictor variable, okay, or value. So why we call this as an independent or predictor or explanatory? First of all, each individual feature or variable are independent of each other. For example, this particular variable is not dependent on this. Manufacturers is not dependent on this for its own existence. Model of the car is not dependent on the engine size for its existence. Horsepower is not dependent on the engine size for its existence. That's why you call it independent. But this particular sales variable is called the dependent because this is something which you're trying to predict. We cannot predict sales if any of these variables are not here. Right? So sales is dependent on manufacturers. Sales is dependent on model of the car for its own existence. Right? I hope so that is clear. There's something to be removed over here, that this is not the predictor. Let me just remove this. Maybe it makes more sense. Yeah. So now this is a response or dependent variable. This is a response or dependent variable. Explanatory variable means it self-explains it. Like it is explanatory by itself. Manufacturers, we know that. Model of the car, that's why it calls explanatory variable, right? Or independent. I hope so that it makes clear. You can see our data fundamentals lecture for more info. Cool. So the algorithm, let's first talk about what is an algorithm. Algorithm is a step-by-step procedure. To solve a particular problem. And we have an algorithm in machine learning to study relationships and summarize data. So I hope that this gives you a good sense about these various examples we have a talk. Okay. So there are several types of relationships which you come across. First type is deterministic relationship. So you might have coded in Python that you have coded a function in Python that converts Fahrenheit in. So you have coded a function that converts Fahrenheit to Celsius, right? So you have coded in Python that converts Fahrenheit to Celsius, right? So that is the deterministic relationship. Why I'm saying that is a deterministic relationship? The formula for converting your Celsius to Fahrenheit, so we can build a function f that takes in the value of that function f is a Fahrenheit that takes in the value of C and 9 by 5 C plus 32. So this is an example of a deterministic. Why it is deterministic? Because you can simply plug any value of C, you will get it will just be converted into Fahrenheit. So there is a defined relationship already there for F and C. So if Celsius is this much, then it will just calculate things up and get you the F. If you know the value of C, if you get the value of C, you can easily get the value of F exactly. Okay? Because this is already defined formula which we have. This is already defined relationship which we already have. And it is linear sort of thing. For example, if your Celsius is 0, then your Fahrenheit will be this. If your Celsius is 10, then your value will be also on y-axis, which is the Fahrenheit. So if you know the value of C, you plug in the value of C and then you get exact F. Other examples are, if you want to calculate the area of a circle, which is pi r squared, right, or pi d, right? So this is the area. This is a defined. You plug in the value of pi and diameter, you get the area, right? 1 by 2 times bh. Defined relationship. You plug in the value of b and h, you get the value. So these are defined relationships, right? This equation exactly describes these equations exactly describes the relationships, right? Plug in the value, it will multiply with some factor, and then it will multiply that c with some factor 9 by 5 and then add 32 to it, right? And is the exact or defined relationship between the two variables. And this is also defined relationship between the two variables, right? But in machine learning, we are interested in a statistical relationship, right? In statistical relationship, where the relationship between two variables are not perfect. Please note that deterministic and statistical. In deterministic, your relationships perfectly defines the particular variable between two variables, but the statistical, it does not perfectly defines it. Okay. I hope that that is much more clear. So one such example is find a relationship between skin cancer mortality and latitude, right? So you want to find what is the relationships what is the ratio between latitude of a particular country and skin cancer mortality. So if latitude increases, whether skin cancer decreases or increases. This is a question, right? This is a question. So this is the data which we have. On x-axis, we have the latitude at the center of a state. On a y-axis, we have mortality. That's per 10 million. This is the mortality rate. And this is your latitude. and all the blue points are the data points. Now, what you did, you modeled the your straight line on this, which best fits the data, and that straight line is of this, where your intercept is 389.2 minus I think that this particular thing is bit wrong over here. This should be so which is 3.389.2 minus 5.98x, where this is assume that this is your straight line. This is your straight line. Okay, this is your straight line out there. This is your equation for this straight line. This equation for this straight line. I hope that it makes sense. And this is the negative relationship. This is a negative relationship. First of all, we'll talk about the positive negative relationship and further on later on. But as of now, you can see that this equation is defined by this straight line defined by this particular equation. Now, how can we interpret what is going on over here? Well, how can we interpret what is going on over here? So assume that you can see the higher altitudes of northern US, the less exposed you did be to the harmful rays of the sun. Therefore, the less risk. So let's figure out. It is saying the higher latitudes of the northern US. Higher latitude means over here. Higher latitude which are going to the right of the side. Then this 45 to 50. So higher latitudes means you are less exposed to the harmful rays of the sun. So when you go this side in higher latitude, so if you see, there is no data which suggests that any values of cancer mortality, right? Cancer mortality there's a less, or even on 45 there is a less, not too much. On 50 there is nothing, but so if you go to the right side or the more higher the altitude is, less the mortality, therefore less the risk. Okay. But if you go over here on 35, there is a lot, there's a whole chunk of information out there, or the mortality rate out here. Okay. So I hope that this gives you a good sense about it. So, but over here you can see that relationships are not perfect. Sometimes over here there is this much, right? But the relationships are not perfect because we don't get exact value. We get approximated value, but will not get exact value. So if you have seen over here, that we were getting some sort of residuals, right? So your model has approximated but didn't got the exact value. This is called the exact value, but your model has approximated it. The model has approximated it. Okay. So I hope that this gives you a good sense about why exactly it's not perfect. It shows some trend. It is showing some trend as we increase the latitude, your cancer mortality rate is decreasing. Okay. And it also shows the scattering relationships. You can see that all the data is scattered, and it's the scattered relationships. So as you can see that this is what the statistical, and over here over the course we are going to talk about modeling the statistical relationships. Okay, cool. So we are interested in finding the statistical relationships. So now we'll summarize what exactly we studied after changing some rotational changes so that it makes sense. In the next lecture, what exactly we are going to do? If we are going to talk about how can we estimate the coefficient, how can we estimate that m and b in that equation. So you have y equals to mx plus b. How can we estimate m and b? By giving you some notational changes. And then we'll talk about what is the interpretation of that m and b in different terms, and then we'll just recapitulate whatever we have studied so that it makes much more sense, and then we finally go on understanding how we can get that in simplest terms. So everyone, now what we're going to do is we're going to talk about a bit about how can we estimate m and b, what are its interpretation, what is this interpretation, like what exactly it means, and etc. after some notational changes. So first of all, what are we given with? So you're given the data. So you're given the data x1, then you have y1. So basically it is a supervised learning problem. So you have input value as well as its label y1, x2, y2, x3, y3, all the way down to the xm, yn. So you have particular input value according with these labels, x2 with this label, x3 with this label. So you're given the data, and we try to find the best fit line based on the given data which we have that best fits the data. That's our end goal. So
why best fit line? A very nice question to tackle. Why do we want the best fit line, right? So line which best fits the data have n errors and they're small as possible in overall sense. Okay. So we want to find a line which have n number of errors, and they're small as much as possible in overall sense. So what does this mean overall sense? In overall sense means that we have n number of errors, n1, n2, n3, n4, n5, n6, n7, n8, n9, right? So over here you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a 12 number of 12 errors. So 12 means when we take an average, it should be very small. So overall means average. So it should be as small as possible. And then we can simply approximate by going up from the x-axis at the point of intersection. That is the y. That is the coordinate which contains y as well. And then we get a prediction y. Okay. So we have a way to achieve it by least squares criteria. So least squares criteria is something which we'll study as well later on. But we have a way to achieve it which we'll study later on. But you can ignore this as of now. So this forms the best fit line. So our equation for best fit line x1 is mxi plus b. So let me just make sure that this is something which we should ignore. Yeah. So which is h of x is equals to mx plus b. Mx plus b. This is an equation. You plug in the value of x and then you get a prediction, and then you get your prediction for the straight line. So our goal is to find that m and b, right? Right. So we can evaluate our best fit line using our MSE or least square criteria. So we can simply evaluate our best fit line 1 by 2m, I equals to 0, all the way out to the m, h of x minus y squared. Why are we squaring? Because to avoid the negative, as if we are taking the average and adding 2 as a convention, but we'll see why this 2 really helps while in later stages of gradient descent. We'll talk about that, but you can assume that as a convention, but we will talk about that why is that 2, because I think this is important to talk. So you can simply use this equation to take out some errors, and higher the error is, bad your model is. So you use MSE to calculate how you're perform. So how you're good at errors if error is small. So errors depends on the straight line. So if the straight line is bad, this is something straight line. Assume that this is your data and this is your straight line. So this straight line is bad, right? So your errors depends on straight line, and your straight line depends on two values, m and b, right? Because this particular value has its own y-intercept and has its own m. So b and m, right? It has own. So it is dependent on m, which is the slope, and a y-intercept b, the slope and an intercept. So what we want to do, we want to reduce our errors, right? So if you want to reduce our errors, what we should work on? We should work on straight line. We should work on getting a good straight line. And if you want to get a good straight line, we should work on what? We should work on in getting the good values of m and b. You should find good slope and intercept in order to minimize m and b. In order to minimize your cost function to find m and b. So find m and b that minimizes your cost function, which is you have a cost function j of m comma b, which is equals to 1 by 2m, I equals to 0, all the way to so j of m comma b, 1 by 2m, I equals 0, all the way down to the m, h of x minus y squared. So square for negative sign, average it out, and 2 for as a convention. So now find m and b that minimizes the cost function. So what are its notational changes? So again, to repeat your summary, we have an hypothesis. Hypothesis gives some error. Now we said how the hypothesis is. We get some error, and then the error depends on straight line. The straight line depends on m and b. So to find a good slope m and b, to get this good straight line, if we get the good straight line, it will automatically reduce the error. A whole story represented on your screen. I hope that this gives you a good sense about whatever I'm talking about. So let's do, our goal is to minimize this particular thing, which is j. It should be j. I'm so sorry. I'm very sorry. I'm very sorry about this. About sometimes you have a bit of, errors and all. You can definitely report in our errata page. We can fix this up, right? It will be much more helpful if you help us to complete it. Okay. So what are some of the notational changes? So over here right now, we are using mx plus b as of now. h of x equals to mx plus b as of now for our prediction function. What we can do, we can assume b to be beta 0 and m to beta 1. Okay, these are the parameters. So why are we doing this? The reason why we are doing this in industry, you will see mostly this beta 1 and beta 0, and also it will help us to be a bit more clear about, industry or the online article. So when you go to online article, you make sure that you're comfortable with the beta 1 and beta 0. Sometimes instead of beta 1 and the theta 1 and theta 0, or sometimes you have some other notation, but we'll use this beta 1 and beta 0. So over here, you might assume, why are not we taking m as beta 1, m as beta 0? But as a convention, we always start off with our bias term beta, which is b plus mx. Okay, so b assume beta 0 plus beta 1 times x, right? Okay, I'll just make sure about this. So your m becomes beta 1 and b becomes beta 0. Okay, so we can write beta 0 plus beta 1 x, that is equivalent to b plus mx. Okay, b is equals to beta 0 and m equals to beta 1. These are the parameters, but the meaning stays the same. Beta 1 is nothing but the slope, and beta 0 is nothing but your intercept. So now there are other names as well. So over here, when you multiply 2x, 2 over here, it scales your x, right? So 2 over here is a weight given to this x. Just like that, x has a weight. We have a feature which is x. For example, the horsepower has gotten weight. Horsepower has gotten weight beta 1, or we can say, even in this case, horsepower x has gotten weight m. So in this case, the horsepower gotten weight beta 1, and beta 0 is intercept or bias term. We'll talk about what is this bias term means later on, but this is a y-intercept, okay, from where it should intersect at y-axis. I hope it gives you a good sense about it. Cool. So I just want to talk a bit more about these things, a bit more on your hypothesis. So your h of x is equals to beta 0 plus beta 1 x, right? And beta 1 is a feature weight, and x is nothing but your beta 1 is nothing but a coefficient of your feature, or a feature weight, or a parameter. Beta 0 is also intercept. By convention, we have beta 0 x0 plus beta 1 x1, or we can say beta b times x0 plus m times x1. Okay, so what does this mean? They both are equivalent, but we are going to use our new notation. It is beta 0 x0 plus beta 1 x1. Okay, or we can say b x0 plus m x1. Both means the same. So going with the beta 0 x0 plus beta 1 x1. By convention, x0 is nothing but equals to 1. So whenever you multiply anything with 1, it just remains that number. So beta 0, so that's why we write beta 0 alone plus beta 1 x1. Okay, so we have x0 to be equals to 1, right? So that's why we don't usually write x0. Okay, so I hope that you understood. It will be more handy when we'll talk about multiple linear regression. You'll finally understand it. But as of now, just keep in mind that we have did a bit of notational change. Everything remains the same. Just our notational changes. Introduce beta 1 instead of m and beta 0 instead of b. Whole story makes sense. I hope so that you understood about relationships in detail. And now you can easily ignore. There's a direct formula, but I just want you to ignore it because I don't want you to focus on that. I hope so that you'll not focus on that. Now, what we will do, we'll talk about. So we have an hypothesis h of x equals to beta 1 times x1 plus beta 0. So this is your hypothesis. So what does this beta 1 represents? What does this beta 0 represents? In terms of, predict the price of a house given the size. So you're given the size of the house. So size has beta 1 times the size of the house plus beta 0. So what this beta 1 represents, or how does this beta 1 affects your output variable? If you introduce beta 1, how does it affect on your output variable? And what is beta 0 effect on your output variable? We'll talk about that later on.
So everyone, we come back to our next section of our video, which is talking about interpretation of coefficients, parameters, or slope and intercept. Both all mean the same. So usually just to make a remark over here, your I sometimes use f of x is equals to beta 0 plus beta 1. So function of, we want to build a function of f that maps your x to your output variable. H of x means the same and y. So they all mean the same. Eventually at the end you're taking out just an output variable y, right? You're taking out the dependent variable, right? So all mean the same. They're used interchangeably just to make sure that you're on the same page. So we are going to use this particular formula, eventual equation, where we're going to take out y, which is a dependent variable, and beta 0 is an intercept term, and you have beta 1 is a coefficient of x, or feature weight of x, or we can say slope. Okay. So now let's start talking about. About what is the significance of your beta 0 and beta 1 in terms of problem statements. That will make much more sense. That will make much more sense. So let's get started now. So assume that let's start talking about beta 0. So beta 0 is nothing but called the y-intercept term, or bias term. Y-intercept term and a bias term. So this is what the beta 0 is. So what does this beta 0 represents? What does this beta 0 affect the output variable? How does it affect the output variable? Right. So beta 0 represents the value of y when x is equals to 0. When x1 is equals to 0. So your beta 0 comes into play when represents the value of y. Beta 0 represents the value of y when x is equals to 0. So when 0 multiplied with beta 1, that will be nothing but beta 0 plus 0. So y is nothing but equals to beta 0. That's the first scenario when beta 0 really helps, is when x is by chance, when x is not there, when you don't have any information, we just go with the baseline. This is known as a baseline. So when x is equals to 0, then your y is equals to beta 0. So that, in other words, the intercept of the regression line with the y-axis. Okay, so which means this comes into play when x is equals to 0. Okay, and it's also the intercept. It's also the intercept of the regression line on y-axis. So it's a y-intercept, right? So if beta 0 is positive, if beta 0 is positive, so let me just make it clear. So if beta 0 is positive, if beta 0 is positive, it means that the regression line starts above the y-axis, which means it's above the y-axis over here, something like that. But if it is negative, then it starts below the y-axis. So it's like if your intercept is positive, if your intercept is positive, it will stay somewhere over here. But if it's negative, then it will stay somewhere over here, right? So that's one of the property. So let's take an example to make sure that we better understand this, like to what exactly when x equals 0 and all. So suppose build a simple linear regression model where y represents the price of a house and x represents the size of the house. So build a function f that takes in the size of the house and predicts the price of the house. So build a function f, right? Build a function f that takes the size and predicts the price. So beta 0 would be the price of the house. So this equation will be modeled as beta 0 plus beta 1 x1. So beta 0 would be the price of the house, when x is equals to 0. So beta 0 plus beta 1 x0, which is beta 0. 0 multiplies by beta 1 is also of course 0. So beta 0 would be the price of a particular house when the size of the house is 0, or nothing. Okay, that's when the beta 0 comes in play. So let's take a very simple example. To make you understand one more time. So assume that predict the application is predicting exam scores. Predicting exam scores. So build a function f that takes in the number of hours you study, and predicts the exam predicts the exam scores of that particular child. So that's the basic function, and you build a function. We'll talk about how we come up with this m and b later on, but you build the function f of x, which is nothing but equals to beta 0 plus beta 1 x. So f of x, number of hours study, which is equals to, assume that your beta 0 is 60 plus beta 1 is 5 and x. So you have just taken random one. You're just taking random one for the sake of an example. We'll talk about how can we take out this beta 0, beta 1 later on, but just assume that you're taking the random one. Right. So over here, your intercept term is nothing but 60, and your coefficient is nothing but the 5, is 5. So your beta 0 is 60. This means that if the student haven't studied anything, which means equals to 0, 60 plus 5 times 0 is nothing but 60. So if student has not studied anything at all, that is equals to 0, the predicted exam score would be nothing but 60. Which represents the average, which is nothing but the average score, which is nothing but average scores of students who do not study, who don't study. So 60 is nothing but the average score of the students who don't study. That it's a bit higher, but that's what the beta 0 represents. Beta 0 represents the situation when your x0 is nothing but equals to x1 is nothing but equals to 0, which means that in this example, the person has not studied at all, or in previous example, the size of the house is 0, which means the average of the size, average house of the price when size of the house is 0. Okay. I hope that you understood what exactly this beta 0 means. If this beta 0 means, and it makes sense. But in case of sometimes beta 0 really does not make sense, but it acts as a bias term. The average term. That's why we call this as a bias as well. Okay, cool. So we have studied about beta 0. Now let's talk about beta 1. Now let's talk about beta 1. Let's talk about beta 1 in great detail. So beta 0 represents the when x is 0, but beta 1 is the coefficient of x, right? Beta 1 is the coefficient of x. So we are multiplying x with something, beta 1. That means it represents that how this beta 1 will affect this output variable y. So it says that beta 1 represents the change in y for 1 unit increase in x. So if x increases by 1 unit, what will be the change in y? That's what the beta 1 represents. Beta 1 represents what? The change in x. The change in y. How much y will change if we increase x by 1 unit? Let's take a very simple example. To make you understand about this. For example, if we have a simple linear regression model where your particular y represents the number of hours of sleep a person gets, okay? The number of hours. So you're gonna build a function f. You're gonna build a function f. So let me just clear this. So over here, we build a linear regression where you're going to predict the number of hours a person will sleep. The number of hours the person given beta 0 plus beta 1, the number of coffee cups, right? The problem statement is predict the number of hours the person will sleep given how many number of coffee cups he has drank. Okay, that's the function which make. So if you have a simple linear regression model where y represents the number of hours, so y represents the number of hours a particular man sleep, where y represents the number of hours and gets sleep a person gets, and x represents your x is nothing but the number of coffee cups a person had, right? Then the beta 1 represents the beta 1. What does beta 1 tell? Beta 1 represents the change in hours of sleep for 1 cup increase in a coffee consumption. So if we increase the coffee consumption by 1 hour, what will be the change in number of hours of sleep of a particular person? Okay, I hope that you're understanding. Over here, the number of coffee cups, assume that number of if we drank 1 more coffee, what will be the effect on this output variable? That's what beta 1 says about it. That's what beta 1 says about it. Let's take a look at the previous example which we had. So the example was the predicting exam scores. We had to build a function f that takes in the number of study hours a particular person predicts. So beta 0 plus beta 1x, 60 plus 5x. So now we have now we don't have x equals to 0. Now we don't have that. That is what a beta 0. But now assume that what this is beta 1 tells over here. Beta 1 tells that for every additional hour of a study, if we increase x by 1, or which is 1 unit, which is every additional hour of study, x increases by 1, the predicted exam score also increases by 5. So this 5 represents the rate of change in y, which is the exam score. The rate of change in exam score. What will the change in exam score? Given there's 1 unit increase in x, 1 unit increase, 1 additional hour of study. So in this case, for every additional hour of study, which is x increases by 1, the predicted exam score increases by 5. This is the rate of change in y with respect to change in x. By 1 unit increase in x with respect to x. Okay? So assume that if a student studied 3 hours, so now f of 3, which is nothing but 60 plus 5 times 3, which is 60 plus 5 times 3, which is 15, which is 75. So student has studied 3 units, 3 hours extra, 3 hours additional hours. So 3 times 5. So it will increase by 15 times. The baseline will be increased by 15 times. So we can study, if a student has studied for 3 hours, the predicted exam score will be 75, which is 15 points higher than the baseline if the student has not studied at all. Which means that if your x is equals 3, then there is increase in x. Okay, then if for every additional hour, his or her score increases by 5. You can see clearly that how this 5 is affecting your output variable. How this 5 is affecting your output variable. Oops. 5 is affecting the output variable out there. I hope that it makes sense to you as well. Okay? Cool. Currently it was positive, but sometimes you have negative as well. Okay? Sometimes you get negative scores as well. So let's talk about negativity as well, which will make much more sense. And I'll give you a sheet where we have much more examples of interpretation that will make much more sense as well. Right? So assume that if you have a linear regression model where y represents the number of hours study and x represents the age of a student. Okay, so you're gonna predict the number of hours a particular student will study given the age of a student. So given the age of person, you predict the number of hours a student will study. Given like higher the age, higher they will study, and the coefficient for x is -2. So you have got beta 0 plus beta 1 x, and x over here is the number of the age of a person, right? So if your beta 1 is nothing but -2, which means it's different. So what does this indicate? This means that every 1 year increase in x, so x is nothing but age, right? So every 1 year increase in x, the predicted number of hours of study decreases by 2. You can see our misconception was that that higher the age, higher the study hours. But over here it decreases. So -2 represents, so if your beta is positive, this means if x increases, then beta also increases. In this case of predicting exam scores, if the study hours increases, then the exam also, because the beta was positive. But in this case, if beta is negative, my beta 1 is negative, which is -2, which means for every additional hour, which if x increases, if x increases, your output value decreases. Okay? If x increases, output value increases. But in this case, if x increases, output value also increases when beta 1 is positive. But in this case, when beta 1 is negative, when x increases, output decreases. One such example was that in this case beta 1 is -2, which means for every 1 year increase in age, the predicted number of study will decrease by this factor, which is -2. Okay? I hope that this makes sense. So we have studied, we have written over there here as well, that if there is a positive relationship. There's a positive relationship. X increases leads to Y increase as well. Okay. So you can see increase in size also increase in price. So I hope that this gives you good sense about whatever we are talking about. I'll take one more example maybe to make you understand in much more detail so that we are on a good page. Okay, so what I want to do is take an example of predicting sales. Take an example of predicting sales, and this is a nice example to start talking on. So suppose you have a data set that contains information on advertising expenses and the sales of a company. So you make a function f. You make a function f that predict the advertising expenses of predict the revenue. Predict the revenue, the sales of a person based on the give the advertising expenses, like how much you spend, how much you spend on advertising, and predict what, and predict Y, which is the sales. Establish a relationship between advertising expenses and the sales. Advertising expenses means the money you spent on advertising of a company. Okay, so you have only one feature X, and you want to predict Y. So your f of X will be nothing but X is equals to advertising expenses, which is equals to beta 0 plus beta 1 X. So assume that your beta 0 is nothing but 1000 plus beta 1, which is 0.8x. 0.8x. So what does this mean? What does this signify? So this signify that your beta 0 is 1000. Beta 0 is 1000. What does this mean? Beta 0 is 1000. If the company does not spend any money on sales, which means X is equals to 0, your sales with the sales revenue would be 1000, which is the average, which is the baseline of Y, which represents the average revenue of company when they do not spend without any advertising. Okay, that's beta 0. But what about beta 1? Beta 1 over here is 0.8. So this says that for every additional dollar we spend, which is 1 unit increase in X, will lead to the sales revenue increase by $0.8. So if we increase $1 on revenue, then 0.8, then we'll get a raise of $0.8 in revenue. So this is a rate of change. So this is a positive relationship. So it means the advertising revenue increases, then the sales also increases. Okay. So assume that your company spends $5,000 on advertising. So your F 5,000. Okay. This is equals to beta 0 1000 plus 0.8 5,000. So this is nothing but your total answer would be your total answer would be 5,000, which is 5,000. So your total your answer would be, let me just calculate it. So it will much worse. 1,000 plus 0.8 times 5,000, which is nothing but $5,000 is the 5,000 would be the sales. So basically, if your company has spent $5,000 on advertising, the predicted sales or the revenue would be 5,000, which is 4,000 higher. With the 5,000 would be the final sales if you spend $5,000. The 5,000 on advertising, which means that is a 4,000 higher than the baseline revenue. So this is 4,000 higher than the baseline revenue, right? So this is a positive guy. So it says that for every increase for every 1 unit increase in the advertise, for every $1 increase in the advertising, your revenue will increase by $0.8. I hope that this makes sense. Now I'm not going to talk more on that. I've given you enough examples for you to explore by your own. I hope that this really helped. I'll be catching up in the next lecture. Then we'll talk about how can we estimate our estimate our beta 0 and beta 1 in great detail. Let's get started in the next lecture. Hey everyone, welcome back to this lecture. In this particular lecture, what exactly we are going to cover is we'll just recapitulate whatever we have learned, and then we'll talk about how can we find beta 0 and beta 1 in our whole discussion is if we don't have better beta 0 and beta 1, we'll be not getting our best fit line. Eventually, we'll be failing to get the good predictions. So that was one of our goal. So let's recapitulate whatever we have done. So we have our hypothesis function or a prediction function, our hypothesis function or prediction function. And over here, the hypothesis or prediction function states that you have an h of x and a builder function, or maybe you have f of x that you have a builder function f that takes in the value of x and then takes in the value of x and map it to y, and y can be any problem. For example, you want to predict the sales given the advertising expenses, or you want to predict the exam scores given the number of hours study. So you have input value, only one input feature. As of now, you have only one input feature x. You have only one input feature x, and given and using this one input feature x, you're predicting what is the y, right? But it may happen that you have several input features, x2, x3, all the way down to the x, and you have several input features, and based on these several input features, you're going to predict the y. But we'll take a look at that several one later on. But first of all, let's build our baseline. So whenever you work on any type of problem, the first you should think about how can we build the baseline and a working solution. Then after building a baseline, we can extend it. Okay, usually I have seen a lot of people, initially they started focusing on advanced things, and eventually they end up losing time, money, and etc. So what I recommend is start with the very basic or sim baseline and then build upon that. So just like this we are doing over here, we are currently taking only one feature as of now, and then we are trying to predict, and then you will see that how I'll extend it, streamlining it very nicely to other features as well, to several features, several input features as well. Okay. Cool. So let's get started. So over here, which you're seeing over here, which is the hypothesis function, which is the prediction function. You put in the value of x and you get a prediction, and you have to learn your beta 0 and beta 1. You have to find your beta 0 and beta 1, and then you have your MSE, which is used to calculate your how well your best fit line is, which is 1 over 2m or I equals to all the way down to the m h of xi minus yi, where we are taking the difference of residuals and the squaring to remove the negative sign, and then we are averaging it up so that we get an overall sense, and we're adding 2 as a convention, or you will see that how this 2 will help us later on, but as of now assume that this is a convention. So what's our goal is? Our goal is to minimize a mean squared error, which is mean squared error. Why this called a mean squared error? Because we are taking mean of the squares of the error. Because we are taking the squares of the error, because these are called errors, because these are residual. The differences are errors, and we're squaring this up, and then we are taking the mean. That's why it's called the mean squared error. And our end goal is to minimize this mean square error, in order to find your beta 0 and beta 1, because our best fit line depends on this beta 0 and beta 1. So we'll see an approach that is common in finding these. So we have to find this beta 0 and beta 1. So what are your initial ideas? Right. So let's talk about what are initial ideas. I would like to give you some seconds, 5 seconds from now on, to think about what idea you can come up with, to actually get this beta 0 and beta 1. So you can take 5 seconds from now on to think about what exactly you want to achieve. And you can actually take a break as well if you are just feeling overwhelmed, but I'm trying to make it explanation so easier. So I hope that you have understood. Now, over here what is the idea number 1? The idea number 1 is to try out several values of beta 0 and beta 1 and see if with that particular parameter, whether your cost function is decreasing or not. So what I'm trying to say, that you can try out several, first what the idea is that you can try out random, say for example, you guess beta 0. Oops, what happened to me? OMG. Okay, wait. Yeah. So you can try several values. Let us assume beta 0 to be 1 and beta 1 to be 0. You take in these values, and then you plug in the value of over your beta 0 and beta 1, and then you evaluate, and then you take in the predictions for every x is out here for every predictions, and then you take in out the MSE. And then we have done this. Please don't interfere if you don't understand. Please see my past lectures. Okay, so we will take out the MSE. Now we'll take out the MSE. So if with these 0 and 1, if our MSE is decreasing, first of all, if our MSE is decreasing, if our cost is decreasing, if our error is decreasing, then what we did, then we'll update our values of beta 0 from, for example, assume that the first in the when you get started, you say every to be 0 and 0. You initialize beta 1 and beta 0 to be random values. Let us assume 0 and beta 0 to be initialized as 0 and beta 1 as 1. So first of all, initialize, and then you try a different value. Okay, and then you take out the cost function with this mean square error, the error from this particular betas. And then what you do, you randomly take another value. You just take another value like 0.25 or beta 1.75. You take the value and then you check MSE. And then you check your MSE. If the MSE is less than the previous one, then you update the beta value. Okay, then you update the beta value. Right. So you update the beta value if with this new value, if your MSE is less than the previous one, if your error is less than the previous one, right? And then you update your beta value to be the new one whose error was less than the previous one. Okay, and then after this you have beta 0 to be 0.25, beta 1 to be 1.75. Now this updated one, right, where MSE is something, MSE is C. Okay, now you again update 0. Maybe 95 and beta 1 to be 0. Now beta 0 is 0.95 and beta 1 to be 1.95. So you take these two values and then you check. Okay, now if I check our MSE is less than previous one, if yes, then we again update the value. Then we use the not previous but the current, which is 1.95, and beta 1 equals to 1.995, beta 0 is equals to 0.95. Okay, so we use the updated one. So what exactly we are doing, we are trying out several values of beta 0 and beta 1 and see if with that particular value of the parameter our cost function decreasing as compared to previous one or not. If it is, then we update, and if it is not, we just stick to the previous one. Okay, so our first step in this idea would be to initialize your beta 0 and beta 1 and we evaluate with these. How do we evaluate? Using this cost function where you predict on every samples of xi and then you compare with the yi and y hat I, and then you simply predict it. So the cost function will be super duper high, right? So the cost function will be super duper high because when you have beta 0 to be 0 and beta 1 equals 0, so the cost function will be super high. Now you try different values of beta 0 and beta 1 like 1.4 and 2.5 respectively, which is beta 0 for 1.5, beta 1 to 2.4, and see if the cost function decreasing. So if the cost function is decreasing as compared to previous one, you update the beta value from 0 to these values and keep on doing this until and unless you get low error. You get low error, right? So you have to try out several values of beta 1, beta 0, and then until unless you get a low error. So now, what's the big deal in this? The big deal in this is that we can keep on trying. So what to do? Like, this is something which you have to think of, right? So we need a strategy, right? So we can keep on trying, but we should know a strategy to keep on trying. We cannot just think about any value and then just go with it, right? It will definitely not make sense, right? So what exactly we want to think about in terms of, we want a strategy for us, or we want an algorithm to try for us. This is a good strategy, but we need an algorithm to try this strategy for us, in an efficient and timely manner. We need a strategy. So what's that strategy? The strategy is we want a system which automatically tries out several values without any human intervention, tries out every values in every iteration. So what is iteration in this case? You might be confused in this. So when your beta 1 is equals to 0 and beta 0 is equals to 0, so you have these betas, right? This is now when you update, now you update the value. So the first iteration would be, now you update the value and then check the MSE. Then the second iteration, you update the value as compared to the previous one and then check MSE is less than. If it is, then this is second iteration. The third iteration means the third time you're changing the value and seeing if the MSE is. So that's iteration, okay? So we want a system which automatically tries out the values every iteration in such a way that your iteration at nth value, iteration at the last parameter value, which is the last iteration or something like that, would assume that you want to make a 20 iteration. So at 20th iteration is better, or maybe this your second iteration at the error at the second iteration where you have updated beta 1 and beta 0 should be less than the previous one. Okay, it is what it's telling. The iteration at the nth value, for example, third iteration, in the third iteration, the parameters value of the third iteration should be better than the second iteration. And how to check betterness? By MSE. Is better than the before iteration. Hope so that you got it. This is a strategy one. Now, how can we come up with this strategy? This is something, this is something which you should be able to confront by yourself. So what is the exact strategy for this to occur? So the strategy is the strategy is we can make use of something known as, let's not go to what exactly. I have a very different mind to teach you all. So assume that we want to know. So what exactly we want to know? So how can we check? We want to check that whether my cost function or whether my mean square error is decreasing if I change beta 0. If I change beta 0. So what exactly want to know? Whether my cost function is decreasing if I change my what? If I change my beta 0 and beta 1. So I want to check this, right? I want to check this. So you might have heard about let's not go on again a mathematical term. So we wanna check this, right? So what is the we can check this? So you might have heard about slope. Okay, so let's talk about change in y over change in x. How much y changes when x changes? That's what is change in y over change in x. So how much y changes when x changes? So what if I can write how much j changes, how much your cost function changes when you change your beta 0, and how much your cost function changes when you change your beta 1. So can we get our change, the rate of change? Right. So if my cost function decreasing as compared to previous one, this is good. We can check the rate of change by nothing but the slope. Which you have heard. Now here comes an interesting part. Now over here, how can we take out the slope of this? Because we eventually want to take out the slope of this particular function. How can we take out this? A very interesting question. So let's worry about, first of all, tell me what is the, if you plot this function f of x, what will the plot looks like? So I would recommend you to plot this function on a graph right now, where you plug in the values of x and x squared, plug in the values of 1, 1, 2, 4, 3, 9, you plug in the several values and then plot it. The plot which you're going to get is nothing but something like this. Okay? Parabola. Okay? Or something like the so if not exactly parabola, but if you plot this on, if I just plotted it on terms of positive 1, but if you plot this on but the parabola, if you eventually plot this up, so let me just plot this up. So the plotting would look like this, which is a function x squared. This is a function. This is a graph of your x squared. This is a graph of your x squared. Now, this is a graph of x squared. So can you tell me how can you take out slope in this? Because at every point, your slope changes. So there is not a constant slope, right? So assume that you want to take a slope at this particular point. So at this particular point, what does it tell? What does the slope will tell? How much it will, what is at this particular point will tell how much your x square will change when you change this a little bit. Let's forget it. You can, let's say you wanted to take a slope at this particular point. Because slope is not constant, right? It's not same all over the graph. It keeps on changing, right? It keeps on changing. So now it is not possible. So what we do, there's a concept of derivatives which takes out slope of a curved line. Okay, of a curved line. I hope that this gives a good sense. Now this parabola, why does I introduce this parabola to you? Interesting question, right? Observe carefully. Can you see this? This is something. Assume that this is something, x, and then you're squaring this up. Isn't your cost function will look something like parabola? Right? Because we're directly squaring this up, right? It will look like something like parabola. So when you plot this equation up, you will get something like this. Okay? You will get something like that. Now, on x-axis, you will have your betas. On y-axis, you have your errors. So now, again, it might confuse you. for every point of the betas. For example, let us assume this is a beta 0, okay? So in beta 0 over here, if beta 0 if beta 0 point is over here, so your error at this point, where error with this beta 0 is very high, error with that particular beta 0 is very, very high. If beta 0 is over here, if beta 0 is over here, if beta 0 over here, error is bit low the previous one. If beta 0 is over here, error is bit low then. So this represents this, the x-axis represents the values of beta 0, and y represents the error. Y represents the error. Okay, so over here, what our goal should be? Our goal should be to get the beta, to get that beta value, over, we want to get that beta from here to here, so that our error is very, very less, approximately equals to 0. So eventually we want to get, so assume that this is a beta 1, this is a beta 1, and then over when the beta 1 is over, let us assume beta 1 is something like 4. Beta 1 is something like 4, okay? Beta 1 is something like 4. So what will be the error? Error will be super duper high. Beta 1, so now you have beta 1 at a little bit less than, or maybe something like that. So beta 1 is, in this case, beta 1 is less than the previous one. The error is also less. So I'm just taking an example. It can be more as well. It can be more as well. Don't worry about anything. Currently, it's a very simplest example which I can plot for you. Okay, which is now beta 1 you tried. You want to reach to a global minima. You want to reach to a global minima, not local, global minima, where your error is very, very less, where it is negligible. So you want to start with the beta value whose error is very, very high. And then you have to learn the beta value. You want to keep on changing the beta value. So you're seeing that we are changing the different beta values unless our error is nothing but equals to 0. Okay. I hope that you're getting what I'm trying to convey. I'm just trying to convey that you keep on changing beta value. You keep on changing the beta value. That will help us. That will help us to get your beta. That will help you. That will help you to get beta 1 equals to. So beta 1, the error of beta 1 is equals to 0. Okay. I hope that you're getting. So how can we take out the rate of change? How can we take out the rate of change? So how much your error changes? So when your beta 0 changes, how much your error changes when beta 0 at this particular point changes? Beta 0 will be same, will be not same. It will be changing, right? So what will the change in error when at this particular point? So what is the derivative of your error with respect to this beta 0 at this particular point? Okay. So let's so it will be more clear once we understand more in mathematical perspective. But eventually, what our derivative is telling, it is telling that how much your cost function or error will change if you change your beta a little bit. Okay? Then you change your beta a little bit. So we use the concept of differentiation, which is how much y changes when x changes. Matlab ki how much your error will change when your beta changes. So in a nutshell, we are looking for this strategy only. We are just looking for the strategy where we can take a look if this something increases or decreases. We're just looking for that strategy. And here we go. So here we go. Where it tests the dy by dx, where you're taking out the where we have when you take out the strat, when you have to do for individually for different parameters, because you have two parameters, beta 0 and beta 1, right? Beta 0, where one is slope and one is bias term, but it's not something like it's slope as of now. But over here is the optimization problem. So you eventually take out the derivative of your cost function with respect to beta 0 and derivative of the cost function with respect to beta 1, because you have to do. So this tells you how much your cost function will change if you change beta 0 a little bit, how much this cost function will change when you change beta 1 a little bit. So if that changes, if this it will happen in every iteration. So in the second iteration, assume that it changes and it decreases. Then compares from the previous one and see if there's something low. Yes, then you update the value of beta 0. So there's a change in when beta 0 changes. Same here as well. Okay. I hope that you're getting what exactly I'm trying to convey. Now, here's your algorithm. Here's your algorithm for updation. Like you get a change. Now you have to update. Now you have to update your values as well. And then you look for another beta value, right? So you update this is called the update rule. This is called the update rule, where you first of all update beta 0 with old beta. So basically you have a new beta 0, and then you assign this. This is assignment operator, where you have new beta is equals to old beta minus the learning rate. I'll talk about that, times the change in x with respect to the change in your cost function, how much your error changes when beta 0 changes. We'll expand this. We'll take out the derivative just in a second, but assume that so we multiply the learning rate with this. So what is learning rate? What is learning rate? So, but before that, we'll talk about that learning rate later on. But let's stick at some point. Over here, beta 0 is the old beta 0. Like over here, if you have beta 0 to be 0 and beta 1 is also 0, then this is the old. Now we have the second iteration. Second iteration, you have beta 1, so you have new beta, and you have to take out the new beta. So you have when you actually convert beta 1 assume that you have a 0 minus the learning rate alpha, the respect. So basically, this is the old beta as compared to previous one, the previous beta. Okay, the old beta minus the learning rate alpha, and this change of rate of cost function with respect to this beta 0, and then you do for beta 1 as well. I'm so sorry, this should be beta 1, this should be beta 1. Okay, this should be beta 1. Now over here, so now you may have several questions. The first question would be, why are we subtracting our old beta? The reason why we are subtracting, because we want to minimize our function, right? One way to think about it, it's not something legal, but we can think about that we want to minimize our function, right? When we want to go down, we want to minimize our function so that our error is less. So we want to minimize. That's why we subtract. If anything, you have to minimize, so to subtract, and then it will tell you. This change. This calculates the change. It calculates the exact points using derivatives at the current points. Okay. And of course, there's the change, and then you have a learning rate alpha, which is nothing but the learning rate alpha. So over here, you are going down at a certain speed, right? At a certain rate. You're going down at a certain rate. So the rate of going down, the rate of reaching to a global minima is nothing but called the learning rate. Okay, it's nothing but called the learning rate, the rate of by which we learn. With the rate by which we learn is also known as learning rate. We'll have a separate video on learning rate. We'll talk about some of the best cases of learning rate in great detail. But you can assume as of now, it scales the change by the factor of alpha, and that is the rate of learning in a geometrical perspective. I hope you're understanding. Cool. Let's get started. So what are the steps? So to summarize, you initialize your beta 0 to n beta 1 equals to 0. Assume that you initialize beta 1 to any number, any random values. And there is an initialization techniques we'll study in deep learning, not as of now, but you can ignore it. You calculate a gradient at the current point with the current value. Of course, the error will be high. You scale it a factor of x, so minimize it by subtracting. You subtract the old betas. Here the update rule happens, and then repeat 2 and 3 points. Right? You calculate, and in the first iteration, you calculate the gradient with the previous. Now in the second iteration, now your betas are updated. Now it's not the initial, but it's the updated one which you get after applying this update rule, right? And then you apply the derivative, and then you get the and then you get the new beta, and then you go to third iteration, and then now your beta are of the second iteration. So you repeat the 2 and 3 points. By how much we're going to repeat? First of all, we can do it for we want to repeat for 20 iteration, 30 iteration, 40 iteration, or we can learn this when you actually converge, when your algorithm is converged. So what we say converged is that your step size is smaller, smaller than the tolerance, and then the learning rate stops when it reaches the global minima. Okay. You will learn about this. You can ignore this as of now. We'll have a separate video on learning rate to make you better understand about that. Okay. So, and then we do for beta 0, and then we do for beta 1 as well. And then we do for beta 1 as well.
Okay, doing the same thing where you're updating the beta 1, the new beta 1, the old beta minus learning rate alpha, the change. Okay, and then we repeat until some conditions. What is the number of iterations? Repeat 24 or 20 iterations where you I for beta I equals to 0 and 1. We apply the for loop for beta 0, and then we update. We simply do for all the betas out there, whatever beta 1 and beta 0. You do for both one. Okay. Now your question would be, how can we calculate the derivative of this? So eventually, you don't usually use the derivative. You use the partial derivative of J of bi with respect to beta I. So this exactly means that they both means exactly the same, but this is a partial derivative which is applied in a vector calculus. If you want to learn more about calculus and everything, if you haven't yet, I recommend you to watch this playlist which I created over a year ago, which is quite famous playlist. Not by so much of people, but eventually it is very nice if you wanted to learn about calculus in great detail. I've considered everything which I know about calculus over here. So how can we take out this partial derivative of how can we take out the partial derivative of your cost function with respect to a particular parameter? This exactly means the same, that how much your cost function changes when your beta changes. Okay, I hope that this makes sense. So you see that they do the same sort of work overall. You simply same sort of work, but this is the vector calculus. So how individual parameter, affects your MSE. And over here, I have taken out the derivation. I have taken out the derivation for your model. Now you might be confused how this derivation came. We'll talk about that for a single training example in a free form. So I'll just talk about when we'll actually do a real world example. Then I'll show you the derivation. Ignore this as of now. This is just for notes purposes. I'll show you a worked example hands-on so that it is more clear. So now when you actually calculate, when this will yield to this formula, we'll learn how to utilize this formula. And for now you plug in the values. Now over here, this will give you the rate of change. Okay, this will give you the rate of change. So we'll talk about what is the interpretation of this, why do we use derivative, what is the interpretation of this number, and various things. This is just a starting point. My aim was to make you understand that we have an update rule, and then we have this give you a storyline for what exactly how do we learn, and this is the story behind the learning point. Okay, so you can see that we are having this is the derivation. When you calculate the derivative of the cost function, the cost function is which you have seen with respect to a particular parameter, you get this particular equation. Okay, so we'll talk about this in just in next section. We'll talk when we'll work on the example. Please ignore others now, but just remember that this is the derived. If you don't want to do the calculus stuff, you can actually ignore the next section as well, but I really recommend if you want to fully understand greatness, and you should be able to learn about it. Okay, now I have listed some examples of learning rate. So over here, which you have seen learning rate. Alpha is a learning rate which decides by how much you should converge, the rate of learning. Okay, so over here, if learning rate 0.1 starts with this, and then it slows down, and then it converges slowly. So if you see that at this point, it is very slow. Why? Because as it is learning, and it knows, you can understand this way. It knows that it is my conversion rate is coming. So I have to be very cautious because so I have to be a bit slow, because when you drive a car, you don't drive at the same speed, right? You don't drive at the same speed. You drive same speed. You drive fast, but whenever required, the breaker comes, you slow it down, right? Or whenever the stoppage comes, you slow it down. That's why the stoppage is slows. But if your learning rate is too high, this is the learning rate which you have to choose according to your problem statement, according to the data, which we'll talk about that later on when we actually do the practical. But this is something which you have to tune, like try out several and see what works well. So if your learning rate is too high, it will mostly diverge. So for example, if your car is going on, okay, with a high speed, so if you push a brake, if you push like 100 km/h, so push a brake, car is most likely to fall down. Right? Like it will most likely to fall down. It will most likely to crash like hell. So if the learning rate is right, it will diverge like this. It will never converge to the minimum. It will simply keep on diverging. It will never reach to a stoppage. And if your learning rate is too small, then it will never converge.
Okay, because it will be super duper slow. If you drive at 1 meter per kilometer, you know, it's I just messed it up. So if you drive slowly, you'll not be able to reach. Okay, cool. These are some of the learning rate variations. We'll talk about that later on, but I hope that you understood about gradient descent in upper level. Now let's go and do the worked example and the derivations and all to make you more understandable about all of this thing. So hey everyone, I'm back with worked example of gradient descent learning, and we will eventually take a sample data and perform a real-time learning on that, and then I'll show you how it is super simple to understand gradient descent even with mathematical reasoning. If you're not comfortable even with math, I would recommend you to watch it, right? It will be much more better for you. So let's get started. Over here, I wanna take a sample data. So sample data which I'm going to take is you have a one input feature. Oops, my mind is so diverted. I'm using yellow, green, and white. So x and y, and in this x and y, you have 1, 2, 2, 4, 3, 6, 4, 8. Please note, I'm not going to take a huge data, otherwise it will take me years, but I'm going to take a sample data, This is a sample data where you have only one independent feature, independent and then you have your output variable or target variable. Okay, you have one independent feature, and then you have output variable and target variable, which you wanna predict. So in a builder function f, or takes the value of this x, takes the value of this and maps it to y. So the builder function f that RFIs any sort of relationship between these two, right? So basically this for you it may be super simple, right, to understand the relationships, but eventually I want to take an example to show you how our machine learning algorithm will interpret this, how our machine learning algorithm will go on understanding the relationship. Okay, because I am always a believer of understanding from the baseline, so that you understand the core of it, you will understand even the big things of it. So your f of x is when you take in the value of, when you put in the value of x, you'll predict y. So build a function f. So your build a function f. So your equation for this line. So equation for this line, or y equals to mx plus b, or y is equals to beta 1 times x plus beta 0. So your point is to take out beta 1 and beta 0 out of this using gradient descent. So what's the first step? The first step of ours is nothing. Step number one, initialize your beta 0 and beta 1. So I'm going to initialize beta 1 to be 1 and beta 0 to be 0. So this is two things which I'm going to initialize initially, okay? Because anything you have to initialize first. Then the second step which you have to do, is calculate the error, calculate the MSE with the initialized beta values. And so how can we take out? First of all, it's very simple. You have your y is equals to beta. What was the beta 1? Beta 1 was 1 times x plus 0. This was the equation. You plug in the values of every x over here. You plug in the value 1, 2, 3, 4, right? So the y pred 1. So y pred 1, which is equals to nothing but 1 times 1 plus 0, which is nothing but equals to 1. So you keep on doing for every sample. So y pred 2, y pred 3, the prediction, which is 1 times 2 plus 0 equals to 2, 1 times 3 plus 0 equals to 3, and 1 times 4 plus 0 equals to 4. Okay. So now you have to calculate the step. Now you have to, after taking the predictions, now what you have to do is calculate MSE. Calculate MSE by nothing but 1 by m. I is equals to 1 all the way around to the m. I is equals to all the way around to the m. So what exactly we can do? We can simply say that one thing is we can also use our formula which we had of that 1 by 2m, which is nothing but 7.5 divided by 2, which is nothing but 3.75. Yeah. So what exactly we can do? Is we can either use 2 over here, but as of now, let's ignore 2 as of now. What do you say? Let's ignore 2 as of now because of and just for sake of simplicity more, but eventually we'll use this too. So maybe let's add 2 over here as well, 1 by 2 m. But eventually we're just going to take the squares, nothing else more. So let's stick to this only. What do you say? Let's stick to this only. It's much more better. So 1 by m. Of course we'll change it later, but my point is not to make it perfect accurate, but as of now, if you see in your machine learning libraries, they're consistent enough. But let us use very simple without using 2 or anything, which is 1 by and you have your edge of xi minus yi squared for removing, and the difference is squared for removing the negative sign. So now it will yield to 1 minus 2 squared plus 2 minus 4 squared plus 3 minus 6 squared plus 4 minus 8 squared divided by 4, and that will yield to nothing but 1 plus 4, 1 plus 1 plus 4 plus 9 plus 16 divided by 4, and that will be the 30 plus 4, which is nothing but 7.5. Okay, this is your error if you utilize these two values. Now let's add one more page. Let's add one more page. Now once you have the MSE, now you have to use gradient descent. Now a step is you have to use gradient descent to minimize your cost function, which is g of beta. So to use gradient descent to minimize that. Cool. So let's eventually talk about how can we eventually do it. So your cost function is, so I'm going to write the conventional cost function to show you what exactly this 2 means in how exactly this 2 eventually help us. So it will make you more clear. So 1 by 2m, your I is equals to 1 all the way down to the m, edge of xi minus yi squared. So this is your cost function. So basically what our goal was to take out the partial derivative of this because what was our gradient formula? Formula was this formula, right? So we have to take out this. We'll take out the derivation. We'll do the calculation of this. How we're going to do? You will see it right now. So you're going to take the derivative of j of beta with respect to beta 0. First of all, let's do for beta 0. Okay. So what this is will tell how much your cost function changes when your beta 0 changes. So it is nothing. So what we'll do, we're going to take out the derivative of this whole set of function, So how does this well? So which is nothing but derivative of the whole function. So we'll write that with respect to beta 0. So the whole function is 1 by 2m, I is equals to 1 all the way down to the m, edge of xi minus yi squared. Okay, this is your this is which you want to solve. So what I'm going to do, I'm going to take out the sum rule, sum outside. So I'm just going to take sum rule outside, which is 1 by 2m, I is equals to 1 all the way down to the m. Then we take out the derivative. Then we take out the derivative of your this function, which is over here. You're going to apply the chain rule. Over here, you're going to apply the chain rule on this particular function. So x of I minus yi squared. Okay. Now you're going to take out the derivative of this. How you're going to do it? We have a 2 function, one inner, one outer. So you will take out the 1 by 2m, I is equals to 1 all the way down to the m. Derivative of this particular cost function, that derivative of this particular cost over here you was the outer function multiplied. This is over here we're going to apply the chain rule. Over here we're going to apply the chain rule of calculus. So we are going to take out the derivative of outer function, leaving as it is inside, times the derivative of the inner function. The derivative of outer function is nothing but equals to 2 comes over here by the power rule, and then we subtract minus 1 from here. So 2. And we leave the inside as it is for outside derivative, and over here 2 minus 1 is nothing but equals to 1, times your derivative of your inside function, which is beta 0, and say inside function is nothing but minus yi. Okay, so this is your equation that you're trying to solve. Now 1 by 2m, I is equals to 1 all the way down to the m, all the way down to the m, and then you simply solve for it, which is nothing but your 2 and 2 cuts out. So you see that 2 and 2 cuts out. So now you will not write 2, and then your final answer would be 1 by m h of xi minus yi. This is your derivation. This is your derivation. You might think, yeah, Ayush, what happened to this? This becomes equals to 1. This becomes equals to 1. Why do we say that this is equals to 1? So let's talk about why exactly this is equals to 1. So when you take out the partial derivative of this function h of xi minus yi with respect to beta 0, what exactly, if we expand this h of xi is nothing but let us assume the beta 0 plus beta 1 xi minus yi beta 0 with respect to beta 0, right? So over here we are going to take the with respect to beta 0. So except beta 0, except this everything is constant. Everything is constant, so that will be nothing but equals to 1. That will be nothing but equals to 0. So everything is constant, and that derivative is nothing but equals to, so everything is 0. Okay. Now over here, if you go and if you see that everything will be 0 because it is except 0, which is nothing but and the derivative of constant is, it's 0. So now you add the derivative. Now this one, because this the whole equation will come to equals to 1. Why? Because when taking the partial derivative with respect to all the letters except beta 0 are treated as constants, and their derivative constant is nothing but 0. And then you have beta 0. When you take out the derivative, that is something but equals to 1. And then you have 1 over here. And when you actually do that, because it does not have any constant, and even if it as we know that it has a constant x0, and x0 is nothing but equals to 1, right? So I hope that it makes sense to you as well. If it not, please see my calculus lectures. Please see my calculus lectures out here. It will make much more sense if you see. I'm not going to go in depth explanation, but you can understand in this way that we come up with when we actually take out the partial derivative of g of beta with respect to beta 0 is nothing but 1 by m I is equals to 1 all the way to the m y hat I minus yi, and y hat I is nothing but the model predictions. Okay, so this is your beta 0. Now we'll do for beta 1, and now we'll do for beta 1. Okay, beta 1 exactly the same. The only thing changes instead of 1 now. So when you actually everything remains the same. So when you actually take out the derivative of beta with respect to beta 1, it's nothing but equals to, everything remains the same. Everything remains the same over here. Everything remains the same. 1 over m I equals to 1 all the way to the m y hat I minus yi multiplied by xi. Why multiplied by xi? Because now in this case, when you actually take out the derivative of this, you will notice that now h of xi is equals to beta 0 plus beta 1 xi minus yi, right? So now take the derivative of this. Everything except this one is constant. This one, everything is constant. Now over here, when I actually have beta 1 times xi, the constant is that this is the coefficient of xi. So this is xi would be over there. Okay, so xi will be written over there. Please see my lectures if you are confused, like how this xi, again, this is a rule of calculus and all. If you don't know, please ignore. Now over here you have you got this for beta 1 as well, right? Now what you need to do, we had an update rule. Now we have to update beta 0, old beta minus learning data alpha, the derivative of beta with respect to beta 0, and then we have beta 1 minus learning data alpha with respect to beta 1, right? You have this, you have this. So let's calculate this one. Let's calculate the first one. The partial derivative of beta with respect to beta 0 is nothing but we have already taken out. The equation. This was our equation, right? This was our equation. So first of all, our prediction 1 minus 2 multiplied by 1 minus 2. We are multiplied by 1, so we should not write anything. 1 minus 2, and then you have 2 minus 4, which is your prediction minus the actual value, plus 3 minus 6 plus 4 minus 8, and then you divide by the total number of values, which is 4, which is nothing but minus 2.5, which is the rate of change. Okay, you do the same for j of beta with respect to beta 1, which is nothing. You will get nothing but 1 minus 2, but this time you're multiplying with xi, and the first, the xi, which is x1, and this is for x1, right? So x1 is nothing but equals to 1. So if you go and see, your x1 is nothing but is now you do for second one. You do for second one, which is 2 minus 4. You simply add plus 2 minus 4 multiplied by 2 plus 3 minus 6 multiplied by 3 plus 4 minus 8 multiplied by 4, and then you divide the total by 4. You get nothing but minus 7.5. You get nothing but minus 7.5 when you calculate. So your with the current value of beta 0 to be 0 and beta 1 to be 1 is nothing but minus 2.5 and minus 7.5, which is the rate of change. Now once we get it, we can simply apply our update rule. Our update rule was, first of all, let's do for beta 0. Our old beta 0, which we initialized, was 0 minus learning. Let us assume that your learning rate is alpha. We'll talk about learning rate alpha in great detail. Multiplied by, so learning rate alpha multiplied by the rate of change, and the rate of change for beta 0 was minus 2.5, right? And the beta 0, the updated beta 0 is 0.25. And then your beta 1, you do the same. You have 1 in this case because the old beta was 1. Minus 0.1 multiplied by minus 7.5, you get nothing but 1.75. That's the output. Okay, this is beta 1. This is updated beta 0 and updated beta 1 after in the first iteration. Okay, as because it now you what you do now, this is now you're done with the beta 0 and beta 1 in the first iteration. In the next in the first iteration, you calculate the MSE and the updated beta 0 and beta 1. Calculate the MSE and updated beta. You'll be noticing that your MSE is low. So when you calculated the MSE with beta 0 to be 1 and 0, it was minus it was 7.5. But when you calculate your MSE with 0.25 and 1.75, it will be less as compared to the previous one. Please note that. You can try it out as well. And then you do the next iteration number 2 maybe, and iteration number 2, you do the same step. Now what you do, you calculate the MSE, you plug in the values of, again make the predictions. You again make the predictions with new beta value. You again make the predictions with the new beta value, and then you take out the error. And after taking out the error, you simply apply the update rule after calculating this derivatives once again. How this derivatives is calculated? You have your new predictions, right? If you have new predictions, you will get once again, and then you have to calculate derivative. Once again, you're getting new derivatives, and then you calculate, and then you have the iteration number 2 as well. Iteration number 3, you do the same, and then all the on unless you reach to 20 or whatever number of iterations which you have fixed up. Okay. I hope that you're getting whatever I'm trying to tell. You can try out this by your. You may be confused about iteration number 2. So let me just be clear about it. What exactly I wanted to. What you can do, you can first of all, you have got new betas, right? You make your Y pred once again. Now you get your 4 predictions. After getting 4 predictions, you take out MSE with these 4 predictions. You taken out, good. Now what you do, you already have your partial derivative of cost function with respect to beta 1 and beta 2. You have some equation. You plug in the values. Now the derivative you'll get is very different. Why? Because your predictions will change. Because you're using new beta value, new parameter value. Your predictions will change, of course. So beta derivative also change, and then you plug in the derivative over here. Now beta 0 and beta 1 will be different. Where beta 0 is 0.25 and beta 1 is 1.75. Minus 2.5 and beta 1 to be 1.75. Right. Now again, you will be getting new betas where the MSE will be low as compared to previous one. I hope that this gives you a good sense, and I really hope that you understood this as well. Now I'm just going to now we'll ask you to take break, because this was something, very tiring as well for me, and it may be tiring as well for you. In the next lecture, we'll talk about why does gradient descent use derivative, what is the significance of it, and I'll give you a Google sheet where we have one more solved problem of it, and then we are finally done with learning, and then I'll recapitulate you everything, make you a summary so that you understand it, and then we go to other forms of linear regression to study more about a lot of things. So let's catch up in the next lecture. Hey everyone, welcome to this lecture. So basically what I'm going to do today is talk about some of the key terms which may be useful for you, and then we'll have a bit of discussion around some of the types of regression algorithm, which is univariate or simple linear regression, or multivariate and multiple linear regression. So we'll talk about the differences and all in great detail. Okay.
And then we'll get started with the extension form, which is quite easy to understand if you've understood the previous one. So first of all, let us understand, why does gradient descent use derivative of the cost function? So first of all, let's figure out that. So basically in linear regression, what is your eventual goal? What is your eventual goal? That's a nice question to start forward with. So your eventual goal is nothing but to minimize your cost function or your MSE. So that is a goal, and your error between, or to minimize the error between your predicted and actual target value. So that we take that partial derivative of that cost function with respect to a particular parameter or a coefficient. Assume that in this case beta 0. Okay, so particular parameter coefficient, and which, so what does that derivative gives us? Of course, it gives us the rate of change, but what in terms of how does this help us to go down, or how does this help us to reach to global minima? That's a very nice question to ask. The first is the direction to move your beta, whether to increase the beta or whether to decrease the beta, right? So it also gives whether we should increase the value from 1 to increase or decrease the beta. That's what it gives. So direction to move your coefficients or parameters in order to minimize your error. So for example, if you have a current 0, should we minimize or max? So should we decrease or should we increase? This exactly the derivative tells, and it tells in such a way that it minimizes the error, minimizes our MSE. Okay. So the derivative of your mean squared error with respect to a coefficient or a parameter value or any kind of beta 0 and beta 2, beta 1 and beta 0, provides the rate of change of the MSE with respect to particular. So how much that changes when this changes, and so for example, if your derivative is positive, which is the rate of change is positive, then increasing the value of coefficient will decrease the error. Okay. First, please note that whatever I'm telling, if the derivative is positive with respect to this, so it tells that if we increase the value of beta, if beta is increased, the error will decrease. So if it is positive, then we increase the value of beta. Please note that this is the most famous question when we talk about the interpretation, because this derivative also gives you the direction to move you, whether to increase or decrease your theta in order to minimize the error, right? So if your derivative is positive, then if you increase the beta, your error will decrease. It means if it is positive, if the derivative positive, it increases your beta. Okay, and if your derivative is negative, then increasing the value. So for example, just for a note, over here, I think I had a very wrong interpretation. I'm going to retake it. Okay. So now the derivative of MSE with respect to a particular coefficient provides the rate of change, how much your cost function will change when you change the coefficient. So if your derivative is positive, so whatever the derivative which you've taken, whatever the derivative which you have taken, if this is positive, which means that if you increase the value of beta, so basically derivative, what does it gives? It gives the direction to move to increase or decrease the theta. That's what it gives, right? So if the derivative is positive, so that means that if we increase the value of beta, our error will also increase. So we'll have this tells if increase the value of beta, our error will also increase. So over here we decrease it. Okay, but if your derivative is negative, which means that if you increase the value of a coefficient, if you increase beta by some factor, increase beta from the previous one, it will decrease the error. Right? So over here, we just go with this change. Okay. So basically, this derivative gives us the direction to move your beta in. If the derivative is positive, that means if we increase the beta, our error will also increase. But if the derivative is negative, it means if we increase the beta, then the derivative will decrease. Okay. I hope so. If the derivative is positive, then we decrease the beta so that our error also decreases. Okay, I hope that this gives you a good sense. So by computing the derivative of this MSE with respect to every individual parameter, we can determine the direction in which each coefficient should be changed
like to increase or decrease in order to minimize our error. Okay, I hope so that you got it. And now our gradient descent uses this derivative. Our gradient descent uses this derivative of the mean squared error to update the parameters in the direction it minimizes. So we'll use the gradient descent in the direction that it minimizes the particular error. So at every iteration, the gradient of the gradient of mean squared error is computed, and the coefficients are updated in the opposite direction of the gradient, as we have already seen how exactly gradient descent works. And it keeps on changing the direction, increasing or decreasing, keeps happening opposite of the gradient, opposite of the gradient, and keeps on coming up unless we converge to the global minimum. So basically, the whole idea behind, first, it is the rate of change, derivative is the rate of change. Second, it tells you the direction, and second, like how big the step is. In this case, if you see that it's starting in the big step, but eventually it is started small, right? So if your slope is large, we want to take a large step because we are far from the minimum. We are far. So over here, slope is large, right? So over here, it is far from the minimum. So we take the big step. But as we go towards the minimum, our slope becomes small. And that's why we have to take a little step. So your derivative tells that how big the step we should take. I hope that this gives you a very clear sense about what exactly our derivative means. And I hope that this gives a good sense about why do we use derivative for the cost function. Cool. Now we'll talk about a couple of types of regression problems in great detail. I think this is important to talk, and then we'll end up this section. So there are two types of. So now in the next video, we'll talk about two types of regression, which is univariate, multivariate, multiple. There are a lot of regression. We'll talk about that.
It's one, and then you put the you make a vector x. You make a vector x which contains the information vector, and then you have a x1, x0, x1, and x2, and then you make a parameter vector, and then you make a parameter vector, and then you make a parameter vector beta0, beta1, and beta2, and then you take the dot product between both of them. Dot product between both of them. So when you take the dot product between both of them, what does it does? x0, beta0 plus x1, beta1, x2, beta2. So we studied the linear algebra. This heavily reduces the computational time because it follows something known as broadcasting, where it simply multiplies and adds at the same time. And the calculation, the dot product which will perform, the way taking the vector x, x0, x1, x2, and then beta0, beta1, and beta2, they take the dot product, it will be super duper efficient. So we have several frameworks to do this, which is NumPy framework, TensorFlow, which provides the optimized versions for the vectorized operations. This is called the vectorized operations. That's why linear algebra comes into place. Okay. Now, how can we write the dot product? So if you have the beta, which is the parameter vector which contains the beta0, beta1, all the way down to the beta n, number of beta. The number of beta is nothing but equals to number of features which you have, and x vector contains your x1 all the way down to the x0 all the way down to the xn. Then you take the dot product by beta transpose x. This is how you can write, or you can say beta dot x. Okay, you can write in this way. So you basically take the dot product, but we'll come to dot product. We'll come to dot product later on when we solve a real world example, but as of now, this is how it works. Now, let's get started with more detailing thing. Okay, first is let's prepare our design matrix. So let's prepare design. Design matrix is nothing but your data. How can you convert your data into a matrix, a CSV data into a matrix? So in this case, you have your design matrix X. Okay, X contains your data. Okay, so assume that you have x1, x2, x3, all the number of features. So x1 size of the house, so the number of bedrooms of the house, the number of so it can have n number of p number of information. So here we have written p instead of n. So we have p number of information. Okay, and the first data point can be represented as, if you have seen the matrix lecture, you could have understood this very easily. So the first data point in your in your data is x11, which represents that it is the first row and first column, which means it is available in the first row which of the first information. For example, if this is the size of the house, this is the first. Okay, now this is the second row, first information. This is the second data point of the first information, which is, assume that this is the size of the house, the first information of the size of the house, second information of the size of the house. So you have same information but different samples. Then you have price of then you have number of bedrooms. So first information of the second feature, which is the number of bedrooms, second information about the bedroom. So you have several samples for the same, right? So you have over here you have different features of as a number of columns, and then on the number of rows has an n number of rows. Okay, first data point, first column, first row, first column, first row, second column, first row, third column, all the way to the first row, p column. Okay. And then at last you have nth row first column, nth row second column, nth row pth column. Okay, so it says that it can have p number of columns or n number of rows. Okay, so this is nothing known as design matrix. This is nothing known as design matrix. Okay, and then you have this y, and y yn will be equals to xn. Okay, so the number of rows, the number of elements which you have in your parameter y vector is equals to the number of rows which you have in a design matrix, because it is a supervised learning problem, and every individual row has its y1, y2, all the way down to the yn. Every has its own label, so it may be small, it not be smaller than it. Xn is equals to yn. The number of elements in yn should be equals to the number of data points in xn. Okay. Cool. Now, what we can actually take out? We can actually take out our y hat I, which is the prediction. So now you might be thinking that, okay, every individual parameter has beta 0, beta 1, all the way to the beta p. Okay, p number of. Now, are we going to multiply beta 1 with all the variables over here? Beta 2 with all the variables, and how exactly the hypothesis function, how exactly will this work? A very interesting question. So your prediction y hat I, which is your prediction. First of all, you have beta 0 by default comes in beta 0 times x0. So basically, sometimes you know what we do, we actually have n times p plus 1. N times p plus 1. In this case, we add another column of 1, 1, 1, 1, 1, 1. We'll talk about that. Why do we add 1? Okay. So you get a predict, you actually have this prediction y hat I, which is beta 0 plus beta 1 xi1, beta 2 xi2 plus beta all the way to beta p xip. What does this mean? This you'll only able to understand if you understand this thing. Okay. So you have your y, and y, how you can get your prediction. You can get your prediction, which is y hat I. You can get your prediction. You can get your prediction from your model. By, for example, eventually you have to make a prediction for calculating how well your equation is, right? So you actually have a parameter vector which is beta 0, beta 1, all the way to beta p, which is of size of p plus 1, because there's a p number of features plus 1, which is beta 0. Okay. So you multiply it. So basically, in this case, we also add there 1 over here. So I'm just going to add to make sure 1, 1, 1, all the way around to the 1. So only 1. So this indicates x0. Okay. So that beta 0 gets multiplied with this. We'll talk about that in a bit. So you have this particular, and now when you multiply this matrix with a vector, it should lead you to a vector of your predictions. So every individual sample will have, because a row is a data point, second row is another data point. So basically, it's a column are different. You know, what I'm speaking about is assume that you have a data like this. You have a data like this. Okay, data like this, and data is mostly like this. So you have so this particular point has this label y. And now you have to make the prediction for this y hat I, so that you can compare the both and then take out the differences. So you take out the y hat for this particular data point, and then for this particular data point, because every row is a data point. Okay. What is it that will eventually help us in taking our decision or learning from our data? Okay. Hope so that it makes clear. We'll talk about this in a bit. But before that, what I would exactly want to convey to you all is you can actually convert this. You can take this x1. You can take this x1. You can take this x1, which is all the this column into a row vector. You can actually convert this. So x1 transpose, which means eventually x1 or as like this. You can convert like this, and then you have x2 transpose, xm transpose. You take this and convert this into a row vector. Take this, converts into a row vector. This has its own benefits. We'll talk about that. And your cost must become like this. We'll talk about this, all of this in detail. Just we'll come to this. Please ignore as of now. Cool. So you have x1, x2, or x3, all the way it has some feature. We have the x0, which is beta 0, and then you get a prediction y using our thing. Okay. Categorize, as I've already talked about this. You have p number of samples that are generalized to p samples, and the parameter vector p, and then you have y vector y, which is the ground truth. Okay. You have a matrix distribution, which is nothing, which is also called the data matrix and the design matrix. Now, based on every individual data point will have its own prediction, and then we compare with the ground truth, the actual prediction, and then take out the error. Okay, so every data point has its own prediction, and every column has its own B2, which is the beta values. Okay, understood. In this case, you're seeing that x0 is being multiplied by aggregating of the information. Now, let's get started. In how can we actually take out the y hat 1, y hat 2, y hat 3, y hat I, all the way down to the number of features which we have. Let's exactly work on that. So y hat 1, which is equals to beta 0, which is equals to beta 0, which is equals to beta 0. So where I am going to write it up, I don't know. Yeah. In this case, see this example. Now over here, I think I written. Now you want to make. Now you want to get a prediction. A prediction vector, and then you have your y, and then you have a ground truth over here. But you have prediction vector. And first of all, you have this one. You made a column where you have one filled up. Okay. Y you will notice, and then a parameter vector b. Okay. When you multiply this matrix. This should be equals to. So when you multiply this matrix with the product, the matrix is n times p plus 1 y, p number of columns plus one column which we added right now, times you have p plus 1 times 1 is p number of columns, which is 1, and there is only one column. So when you actually we want to take out the multiplication between both of them, the dot product between both of them, a multiplication vector product. Okay. In this case, what we'll do, you have beta 0. As I said that every individual point has its own prediction. Okay. It should not be like this. It should be like this. Every data point is a row. Okay. So beta 0 times 1, beta 1 times x11, beta 2 times x12, all the way down to the beta p times x1p. So basically you take the first row. You take the first row of the vector, take the dot product between the first row of the design matrix or data matrix with the first element of the vector. Understood what I'm trying to say? You take the beta 0 and multiply with every element of the first row of that every element. Sorry. I think I just messed it up. You take the first row of I'm so sorry. You take the first row of the design matrix, and then you take the vector. So basically, you have your row vector. You multiply with you multiply with the column vector. So you take the dot product between the row vector and the column vector, which is nothing. You'll come up with 1 x11, x12, all the other this x1p. So x11, x12, all x1p, all the other and there is 1. So take this, and then you have a column vector which is beta 0, beta 1, all the other. Take the dot product between both of them. So dot product will yield to something like this. So beta 0, this beta 0 multiplied with this 1, beta 1 multiplied with this, then plus of course, beta 3 multiplied with the third information, beta 4 multiplied with the fourth information, fourth information, fourth information, a particular data point in that fourth information. Okay. Ith index, and then you have got your prediction. You just take out this and then go to your prediction. Now you go to y2, which is the prediction for the second row. Okay, for this second row. So basically, you do you take the second row, and then you take this vector, do the dot product between both of them. It is beta 0 times 1, beta 1 times, this is the same information. It is the x21 it is saying that is the second data point of the first of the same. This, if the size of the house is the second data point, okay, second data point of the first information. So beta 1 times x21, beta 2 times x22, beta 3 times x23. So you have this by2 all the way around to the yn. You do for all the way around to the yn, which is a n number of predictions, which is beta 0 times beta 1 x n1, which is the nth data point for the first information. The beta 2 times x2 x n2, which is nth information for the second, nth data point for the second information, nth data point for the third information, and nth data point for the pth information. Okay, and in between you have yi, which says that you have beta 0 times x times of course 1 because everything is 1 in that first case, beta 1 times xi1, ith data point for the first information, ith data point for the second information, ith data point for the third information, and ith data point for the pth information, right? And this is nothing but your prediction function for nothing but your simply multiple linear regression hypothesis function. Okay, you can write this in a coefficient in a vectorized format, which is y hat is equals to xb, and this will yield to n times 1 vector. I hope that this makes sense. Okay, now over here, now once we have this, now you can actually now once we have the multiple, you have the hypothesis function. We'll do a worked example just like we did for linear regression, simple linear regression. We do a simple worked example for you to be better comfortable in. Okay, cool. Yes, so now you have this, now what you have to do, now you got your y. Now you need to compare this y hat I with y. How well your this particular equation is. So this can be, which you have this j of beta, which is your cost function, which is nothing but equals to this, which is defined for simple regression. But eventually you will notice one thing. You have your vector in this case. You have vector in this case, right? Of course, you can write your vector, not a big deal. You can actually, take out something. You can take out something like this. You can have the y hat and y, and then subtract it, and then you're getting another vector, and then you simply add all the elements in that vector and divide by the number of terms. You can actually do this, but this is computationally expensive, and computationally expensive we avoid in machine learning because it's already too much, very, very time taking. So what we do, we have a vectorized, as we have the vectorized hypothesis function, if something is vectorized, which is computationally good, we have vectorized cost function as well, which is defined by this, which is g of beta, which is 1 by 2m x beta, which is your prediction function, which is the prediction, which is y hat, eventually y hat, minus y transpose x beta minus y hat. Well, sorry, y not. This is your prediction and this is your ground truth. Prediction, ground truth. So you have this vector. This also yields the same vector. This yields the vector. This yields the vector. This yields the vector. This yields the vector. Okay. So how do we derived this cost function? So let's talk about how do we derived that. Okay, so let's break it down. Let's not take this. Let's take a very simple example where you have a vector x, where you have 1 1 1, and then you have first data point of the first information, second data point for the first, and you have only one predictor, which is independent variable, and then you and as you have only one information, you have beta 1 and beta 0 as a simple regression. But let's frame this in a multiple thing. Okay, so when you want to take the prediction, it is nothing but x beta. So you take the beta 0 and beta 1, the first row, take the dot product between these two, the vector, which is the parameter vector, and the first row, and then when you take the dot product, and then you write the equation over there, and then take this particular vector and then multiply with this vector, row vector, then you the dot product between both of them, the dot product between the row vector and this vector, so you'll get the 3 data points out here. Now what do you do? Now you have this. Now so you have the prediction from your model. Now what you have to do, as I say, that you wanna identify what is the differences between both of them, right? As please note that if you wanna know the geometrical perspective of cost function, please see my previous lectures, because I've already told this. I'm not gonna tell again and again. So you take out the errors, the residuals, how apart from they are. So you simply have the prediction function, the prediction which you got, x like xb, which is equals to nothing but the back vector, minus y hat, which is nothing but what? Which is nothing but a ground truth. Okay. So when you see this, you will simply have this. And now we have to, as to remove the, the squared sign, the negative sign, we square. So this is going to be squared. So if this is going to be squared, so every individual parameter is going to be squared. So when every individual parameter is going to be squared, now you can see that this is going to be state. So you can actually, you have x beta minus y beta, x beta, which is nothing but which will yield the prediction function, which vector minus the ground truth transpose. So basically, let's remove transpose as of now. So you have couple of times x beta minus y. So you simply take the transpose for better multiplication of both of them, and eventually you will be getting a very nice. So you have noticed a pattern, using vectorization, it will eventually helping you. It is helping you out. It is helping you out very, very easily. It is helping you out. So basically, you are simply multiplying. You're simply multiplying this 2 times, no? This square of this. So basically, you have this transpose for better computation. You can see further if we'll do one sample example just to see how does it work. So now, rather than doing this extensive computation, you can simply multiply subtract the vector and then take out the dot product between both of them to actually get the answer. Okay. Hope so. It makes sense. Okay. You have the dot product between both of them to actually take out the answer, and then you divide by 2m, or 2 over here is added because of the gradient descent convention, but you can actually remove this 2 as well to take out the what? Average. I hope that this gives you a good sense about how do we came with this cost function, efficient cost function. Apart from that, I think we covered pretty much very, very well about this multiple linear regression. And then now once we have this cost function, now we're able to evaluate it. Now what we'll do, now we want to minimize the cost function. You'll see that how I do it using, again, gradient descent. I'll showcase you the difference between the partial derivative, as we are using the partial derivative, why we are using a partial derivative. A very interesting question, but I just wanted to be with the convention. I just don't want to use that D. D is used for scalar programs, but this partial derivative is used for what? Is used for vector formula. But basically, I think I'll just note it down for you all that okay, here we are using in terms of future notation. The reason why I use that partial derivative in that when actually we were solving gradient descent is so that it works perfectly for a future notation which we'll study right now. So it makes you be a bit handy. Otherwise, I could have introduced various, so you might be confused. So that's why I didn't introduce over there. Okay, so cool. I think it's now in the next video, we'll talk about how can we optimize our cost function. And apart from that, I'll show you an analytical solution. How can we, without any procedure, we can just take out our beta's value in matter of no second, in matter of no time with calculating, and then we'll talk about how can we evaluate, and then we'll talk about some of the hypothesis testing, which is t-test, f-test, and a lot of things going to come up, and you'll be eventually enjoying all of this thing. And after that, what we'll do, we'll talk about something known as assumptions of linear regression, some of the assumptions, and then we'll do one other project as well. You'll be super duper enjoying that as well. I'm enjoying to teach you all of this. So let's catch up in the next lecture. Then bye-bye.
Hey everyone, welcome back to this lecture. So basically we are at linear regression, where we'll be talking about multiple linear regression. I already have the notes for you, but that's a bit less. So I just want to elaborate with you with some examples which may help you to understand much more better. So we will have a set of examples for you to better understand all of these things. Okay, so let's get started now. So basically, let's have an example so that I can show you the vectorized operation and everything. So assume that the example over here is x1, x2, in x1 you have 1, 2, 3, and 4, and x2 you have 2, 3, 1, and 3. And then you have two independent variables, and then you have one dependent variables, which is 3, 4.5, 4, and 6.
So you have the data available. You have a data available like this. So let me just draw a straight line. You have a data available where these two variables, which is out here, these two variables are independent, as this is not dependent output variable, and this is nothing but your y or your dependent variable Okay, so this is the data. Now you have now you can make a design matrix. So now you can make a design matrix. First of all we'll calculate we'll have the hypothesis function out there. Okay, so we are gonna train our linear regression model on top of it. So how we'll train? First we will put that in form of a matrix, which is nothing but 1 2 2 3 3 1 and 4 8, and then we have 1 1 1. I'll show you what is the use case of this one just in some moments, which you will see that why we are adding one more over here. So let me just have this in a nice way. You have x equals to 1 1 1 1. So we have the design matrix. We'll talk about this later on. And then you have beta, So basically every individual feature has its own beta, right? So beta 1 and beta 2. Right? Beta 1, but we also have something known as beta 0, right? So how beta 0 basically, when we do the multiplication, so basically we take the first row, multiply with take the dot product between the first row and the vector b. So basically here we have only 2. For example, assume that we haven't taken this particular 1 1 1, then we would have only 1 2, and this would have been left. So we have to multiply beta 0 to 1 as well, right? Because beta 0 times x0 is equals to 1. That's why. So you assume that you have initialized your beta with maybe a 0. But before that you have the beta over there, and then you have your ground truth vector, which is 3 4.5 4 and 6. 3 4.5 4 and 6. Okay, so you have this ground truth over here. Now what you do now? With the available settings, now let's do one thing. Let's form a hypothesis function. So you can get your prediction vector by multiplying your design matrix with the parameter vector, and this will yield to a vector. This will yield to a vector which is equals what was our design matrix? Design matrix was 1 1 2 1 2 3 1 3 1 1 4 8. And then let's initialize our beta value, beta 0, beta 1, beta 2, all the way to 0, because you have to find the best beta. So in the first iteration, what you just initialize. Okay, I hope that this really makes sense to you. Now once we have that, what we will do after initializing our beta values, to 0, what we will do, we'll simply have this 0 0 0. And now we will take the dot product between the first row and the column of that. The first row, the dot product between both of them will yield nothing but 0. The dot product between the second row and this vector will yield to 0. This and this is 0 and 0. So your predictions are 0, which is your y hat. So once you have the predictions from your model, when your betas are all set to 0, you'll be having that. Okay. And then now we have to compute the cost. Once you have the model prediction, now you have to estimate how well. So when you have the h of x in this case is nothing but beta 0 plus beta 1 x1 plus beta 2 x2. So beta 0 is nothing but 0 times x1 plus 0 times x2. So how well this equation or best fit line is. Of course, this is super bad because we have initialized as this is the first iteration. So let's compute the cost. So when we compute the cost of it, cost function. So cost function is computed by this. So we have already had a talk on the derivation of our cost function, which is nothing but 1 by 2m x beta minus y vector transpose x beta minus y. Okay, so this was our equation. So let's first of all compute x beta minus y. Okay, so how can you compute this? So you have model prediction minus the ground truth. Model prediction was 0 minus 3, 0 minus 4.5, 0 minus 6, and 0 minus
4 and 6. Okay, this was 4 and 6. So you have your model prediction minus the ground truth, which will yield to a vector which is -3, -4.5, -4 and -6. This will be your this will be your when you calculate this. Now what we'll do, we'll take this we have calculated. Now we'll take the transpose of this. So when you take the transpose of this, which is nothing but equals to -3, -4.5, -4 and -6. We have this particular transposed vector. Now we have the transposed vector. Now what you do to transpose vector multiplied with this particular vector, then you will have simply, now you have 1 by 2m. So here you have 4 examples. M is equals to 1, 2, 3, 4. 4 data points. 1, 2 by 4 is equals to 8. 1 by 8 times 1 by 8 times -3, -4.5, -4, -6. And then you have the non-transpose vector, which is -3, -4.5, -4 and -6. When you actually calculate this up, which is nothing but, so this is nothing but 9 plus 25, so 9 plus 20.5 plus 16 plus 36 as you multiply the element-wise operation. And then what do you do? And then you simply add it up, and that will geo beta will yield to 10.156. So you'll have this cost function out here. Okay, so you have seen that how we have taken an account of this hypothesis function. After that, we have taken out the and we have taken out the cost function out there. I hope that this gives you pretty much a good sense about how exactly we cover up things. Now, this was the vectorized operation out there, right? So how does vectorization really help? So this is a very important topic to talk on. Maybe it's very useful as well to talk on, like how vectorization helps. So if you were to do this normally, if you were to do this without any vectorized operations, first of all, let us assume you don't want to do it with any vectorized operations. First of all, even with calculation of hypothesis will take too much of time. Nested loops will come in. It will take too much of time. So when you have this particular your general form, which is something with h of x is equals beta 0 plus beta 1 x1 plus beta 2 x2, right? So you put in the value of x, you put in the value of x, and then calculate. You put in the value of x, you calculate it. Okay, you put it. Now that's for first data point, and then you do for second data point, do third, fourth. So you do for all the 4 data points. Okay. Now after this, what you will do, you'd have to take out the that you have to take out the errors for every individual, right? So that would take a ton of time, right? So that's why we over here you have seen that how simplicity by at the only one time it just calculates our error. Okay, cool. So so what are the operations involved? What are the operations involved which you have studied right now? So operations, the first operation which is involved is compute your hypothesis or compute xb, which is nothing. Your x is nothing but m times n plus 1 matrix, where you have 1 included for 1 column, and then you have beta, which is nothing but n plus 1 matrix, and then you have nothing but n plus 1 matrix. Okay, and then you have a beta, which is nothing but n plus 1 matrix. An n plus 1 times 1 matrix, or the vector, where you have beta 0 also included. That's why we have this plus 1. Okay, so compute this. So computation takes the complexity will take some amount. So that's the first operation is involved. Second operation which is involved, which is taking out the error like this. And then what you do, and then we take the transpose of this, and then we take the transpose of this, and then we multiply it. Okay, so this is the second and third information, and after you multiply it, you will be getting your answer. So the total time takes, it's very less as compared to you can also take out the runtime complexity if you want. So now I hope that this gives a good sense about what exactly we're trying to offer. Now what we'll do, now we'll go forward and talk about how can we perform gradient descent. How can we perform gradient descent out here? Okay, so that's the first question to tackle. So let's go ahead and have this current template, and let's get started. How can we perform gradient descent? Okay, so basically
How can we perform? Let me just write gradient descent. Amazing question, right? So how can we perform? So you have j of beta. Your cost function is nothing but 1 by 2m x beta minus y transpose x beta minus y. So this was a cost function, right? So now this is a cost function. As I've studied that you have to take the partial derivative of a cost function, the gradient of a cost function. So there's a difference between partial derivative and derivative. So there's a difference between partial derivative of cost function with respect to a parameter and derivative of. So previously, so basically this we use if we have this scalar program. If you have a scalar program, just like we saw in our previous simple linear regression. But in this case, this particular thing, we have a vector program which we saw in a multiple linear regression. But I just introduce you this into the first only so that you'll be comfortable with what exactly. Both mean the exact same thing, but this is for vector programs. This is for vector programs, and this is for scalar programs. So basically, whenever you have betas in vector, you actually use this, and then when you have this in scalar, you actually use this. Okay. So what you do? You take out the partial derivative of g of beta with respect to a particular beta. Why we take out and everything we have talked, that it gives the rate of change, it gives about everything, the whole story of geometrical we have already talked about. So you take the partial derivative of it so that you can identify the rate of change, how much the cost function is changing, where the beta is changing. So that when you take out the derivatives, which actually gives 1 by m x transpose x beta minus y. So when you actually take out the derivative, I'm not going to talk about the how can we derive it. It's not required maybe for you if you're not a calculus student, but we of course have the reading materials for you to get started with it. Okay, so what is the gradient descent algorithm? So once we have the gradient, once we have the gradient calculated out here, what we can do, we have the algorithm following. So you go for i in range number of iterations you wanna change the variable so that you that you can converge. You take out first of all the hypothesis. If using hypothesis function, you take the dot product between np dot x and beta, and then once you have the ground truth, now what you do, you take out the error. Now you take out the error, which is y hat minus y. This y hat is nothing but model prediction, and y is ground truth, right? And then you have gradient. Now you take out the derivative or the gradient at that particular point, and over here it will be sort of vector. We'll do one solved examples to better for you. So we take out the derivative or the gradient at that particular point, which tells us how much change we are getting in a cost function if we change the beta a little bit, which was nothing but which we have derived, which is nothing but 1 by m times the dot product between your here. So basically this is the dot product between the error, this is the error, and this is the transpose. Let's take out the dot product between the transpose of your x, which is this, and the error, which is this. So just simply multiply. Okay. Now once we have the error, once we have the gradient, we can actually use the update rule. So your beta new will contain beta old minus the learning rate alpha, which is nothing but learning rate alpha multiplied by the gradient, which is out here, right? This is the derivative, which is nothing but a partial derivative cost function with respect to a particular variable. Okay, so I hope that this is the algorithm which is for multiple linear regression. Let's try to do one thing. Let's try to solve a very simple example of using a gradient descent. Okay, so assume that I'm going to take a very simple data set, which is x1, x2 and y, which is 1, 2, 2, 3, 3 and 4.5. So based on this, you're going to predict the output variable y. So your design matrix will conclude f1, 1, okay, because this is important, x0, and then you have 1, 2 and 2 and 3. This is a design matrix. Okay, and then you have a output ground truth vector, which is 3 and 4.5, and then you have parameter vector, which is 0, and then you have beta 0, 0. So beta 0, beta 1 and beta 2. Beta 0 as it for bias term, beta 1 is the parameter of x1 and beta 2 is the parameter vector of x2. Okay, assume that your learning rate alpha is 0.01, and then now what you do, now you compute the gradient. So now what to know, but before that,
what you do, but before that, what you do, you compute the, you run this algorithm. The first step in this, when running this algorithm, you're going to calculate your y hat. The calculate your y hat, which is nothing but x beta, which is nothing but 0, 0. Okay, you calculate it. Now you calculate the error, which is nothing but over there, which is nothing but your 0 minus 3 and 0 minus 4.5, which is nothing but minus 3 and minus 4.5, which is nothing but this. Is nothing but the error, the difference. Now, once you have the difference, you calculate the gradient at that particular point. When you calculate the gradient at that particular point, which is nothing but 1 by 2, which is over here, m is equals to 2. That's why 1 by 2 multiplied by your dot product between your x transpose, the design matrix, and the error. The dot product between the design matrix, which is the design matrix over here, is 1, 1, okay, which is 1, 1. So you the transpose of it will be 1, 1, 1, 2, sorry, I guess I did a bit wrong over here. It should be 1, 2, okay? So 1, 2, and 2, 3, okay? So 1, 1, 1, 2, and 2, 3. So when you take out the transpose of this particular matrix, you'll get this multiplied by oops, multiplied by your error or difference vector, which is this one, okay? So when you calculate the gradient, you will end up being with this particular variable, which is nothing but, you'll have c. Let us assume that you have gradient. Now what you do, you have a gradient. So when you actually work on it, so this is the new set of betas. Now you come to the gradient here. This is a good, this when you solve for it, you'll automatically get it, okay? You'll automatically get it just when you solve for it. Okay, so you get all the values when you solve for it, and then you have the new beta is equals to old beta minus learning and grad. Okay, this particular grad, and is also a vector. Okay, so your new beta will be a vector, which is a 3 elements, which requires the old beta is also 3 elements, 0, 0, 0. Okay, minus 0.01 multiplied by your vector, which is the C1, which is C2 and C3. In this case, if we exactly want to focus on exact numbers, this will be nothing but minus 3.75, minus 6, and minus 9. Okay, so this is the basically the C will, when calculate, will come out, which is nothing but your new set of betas will be 0, 0, 0 minus 0.01 times minus 3.75 minus 0.01 times minus 6 minus 0.01 multiplied by minus 9. So you have this one, and then you actually calculate this 0.0375, 0.06, and then 0.09. So this is your new set of vector after first iteration, okay? And this is the first iteration. Now you after calculating the new betas, now betas are updated. Now what do? You run this once again with the new betas, calculate the same, break out the gradient, and then get the new beta, and then do the same thing until your number of iterations reached. I hope that this gives you a good sense about how exactly we work through. And for geometrical perspective, we have already talked a lot. Cool. So I'm just trying to make sure that you have every worked example into your hand so that it's much more better for you to understand it. Next, we are done with mostly this. We'll talk about a bit about analytical solution of linear regression, and then we'll talk about how can we evaluate our model specifically. And then after that, we have a lot of things there. So let me just go there. So after the calculation, we'll talk about hypothesis testing, which is one of the most important thing over here, which is the how can we test our model, the significance and everything. And then we go to the next step, which is nothing but actually talk about assumptions of the model, and then we'll do one project, and then we'll wrap up this course.
In this video, what exactly I'm going to do is talk about something known as analytical solution of linear regression. So basically, what exactly we'll talk about in the analytical solution of linear regression is you have direct formula for taking out your beta values by putting your x and y's into it. So how this is derived and everything, I'll be linking a very nice resources in this particular reading section of this, or you can see in the resources section for this particular lecture. I'll give you how do we derive this formula, but it's pretty easy. If you get to it, you'll have the assignments as well for on it. So basically, we have the direct formula when we plug in the values of x and y, and then we get our output variable betas, right? So we have an optimized beta, which is converged beta, which is the best beta, right?
right? So there's a direct formula, which we call an analytical solution to that. So basically the formula is x transpose x, then we take the inverse, multiply with the x transpose y. So let's talk about let's talk about by taking one particular example. So assume that this is a particular example. You have 1 1 1 1 x0, and then you have one independent feature and one x0, which is nothing but for beta 0, and then you have target variable which is y, which is a ground truth over here. Now we utilize both of them to actually take out the beta's values, right? So basically, the first step is to calculate the x transpose x. So when you take out the transpose of this, so this column becomes the row and row becomes the column. So basically 1 1 1 and 5 7 2 0, and then you have the particular matrix out here, which is 2 by 5 matrix multiplied by 5 by 2, that will yield to 2 by 2 matrix. So when you multiply this up, you will get a 2 by 2 matrix, which is nothing but this one. Okay. Now the next step, what you do is take out the inverse of it. So what is the inverse of it? Inverse of any particular thing is 1 by this. Okay, 1 by determinant of the inner value, which is 1 by determinant, and when you take out the determinant of this particular, which is nothing multiplied by this minus 54 times 54. So this is a determinant, which is nothing but the area under a parallelogram. We have already talked about determinant, everything in great detail. Please see the linear algebra lectures. So when you take out a determinant, you will have 674, and then what you do, you take out the adjugate of that, and then you take out the adjugate of that. So adjugate of that would be nothing but this particular matrix, and then you multiply with 1 by this with the adjugate matrix, where you will get your inverse of a particular matrix. Now once you have the inverse of a particular matrix, now what you do, you compute x transpose y, which is this one. You compute x transpose y, you'll get this particular thing, and then finally multiply this particular matrix, and this particular vector by 4, getting beta 0 and beta 1, and that's the required beta 0 and beta 1, which is your regression equation. Okay, I hope that this makes much more sense. As this was very simple example for a calculation of this, but I actually want you to just don't remember how exactly do this. This is something which is softwares are made to do it for you, so you don't need to worry about this. What you need to worry about is this particular thing, like what exactly this test tells is, here we have the formula which directly gives our beta values. Okay, if this matrix is not invertible means it cannot be inverted, then you need to remove the extra features to ensure that your D is smaller than or equals to n. So the number of features is less. Okay. So this is a very general thing which you need to know, but let's talk about what is the difference between this. This is important. This is usually asked in interviews. What are the difference between gradient descent and closed form solutions? Gradient descent requires multiple iterations. Okay, so you have to one iteration second, and it requires time, and you need to choose the alpha value as well. And it extremely works well when you have a large number of features. It does not works well when you have a large number of features. Okay, it supports the incremental learning. Okay, it is in closed form, it is non-iterative. It's just we plug in the values and then we get up values, and then it's no need for alpha values. You don't need that. It is slow if n is large. If a number of features is large, it is slow because you have to compute all the operations, which is linear algebra operation, which is quite expensive. And then you have this particular thing, which is nothing but you compute x transpose x, which is roughly order of n cube, which is extremely time taking. So if your data is small, n is small, then I suggest to go with closed form. But if data is large, then I support incremental learning, which is gradient descent. Okay, I hope that this gives you a very great sense what exactly this analytical solution means. Now what we'll do, we'll talk about how can we evaluate our machine learning model by going on to the next slide. So let me just make a template. Let me just make a template over here. So dotted paper, and over here what I'll do, I'll talk about some of the methods how we can eventually talk about how can I evaluate our machine learning model in a right way. Okay, so the first measure which we have already seen earlier, is nothing but known as mean square error. So the first measure for evaluating how well your model fits the data, which is nothing but mean squared error. So what exactly mean squared error is the average of the squared difference between the predicted value and the actual values, and emphasizes the impact of larger errors on overall error. So basically what exactly this does tells, you have the MSE, which is nothing but 1 by m. Sometimes we write 2 over here as well, but let's ignore 2 as of now. So 1 by m multiplied by I equals to 1 all the way around to the n, all the way around to the m, all the way around to the m. You do for every examples, you take out their prediction, you take out model prediction minus yi, which is minus your ground truth, and square to remove the negative sign once to remove the negative error if there's any, right? So basically what does it tell? What does it do? It gives you the differences, the overall differences in your model. But there's one note to be taken out here. You see that we are taking mean. So mean is highly affected by outliers. So assume that you have a 2, 3, 2.5, 6, and then 99. You understand this. This can easily affect your MSE. However, your model is performing best, only one example is it perform very worse, right? So over here, your MSE will yield to very bad exam, to a very misleading, misleading error, because it is eventually taking the mean, and this is something giving us a misleading outcome. Right? This is something which is giving out the misleading outcome. So basically we say that it emphasizes the impact of larger errors on the overall sense. So if you got if you're getting the large MSE, that means that it is not something like every error is performing. It emphasizes, what is emphasizes? The impact of large errors, like this, in overall sense. But I just told about it, MSE. So that's one of them. Another one is about mean absolute error. So it's the average of the absolute difference between the predicted and the actual values. It measures the average magnitude of errors in a set of predictions without considering the direction. So basically what it does tells that you have mean absolute error, and what does it tells? That first of all, the formula for this is a nothing but 1 by m, I is equals to 1 all the way down to the m, and take out the absolute value of yi minus yi. Okay? And not squared. Over here, please note that we don't need to square. So basically what we are doing, and rather than you doing square to remove the negative sign, we are taking the absolute value, and so that we get rid of negative terms. So basically that means that if we get rid of negative terms, what does it mean? It means that if you don't have any direction, it does not, if while you take out this, then it does not have negative or positive direction. It just says we don't have direction. So if we get rid of negative direction, which also means that we get rid of the direction without considering the factor of whether it is positive or negative. It does not focuses on that, okay? So it does not consider directions, but it takes the average of the absolute. When you take the average, you'll be positive B, positive C. Take the average, okay? It is not taking the differences that consider that it is going in other direction. It all in the consistent. It's like we're not considering directions in this case. So that's mean absolute error. That's one of the way to think about it, okay? And another one which we have is nothing but called root mean squared error, which is nothing but called root mean square error. So let me just write root mean squared error, or somewhere we call RMSE. So what does RMSE means? This is a very important thing to talk on. RMSE is nothing but a square of your mean square error. Square root of your mean square. So when you take out the square root of MSE, that will give you RMSE, which is root mean square error. Okay, that is the square root of that. It has the same units as the dependent variable. So why does we
Why do we take out MSE? Because the units are same as the target variable. That's why it is easier to interpret. Sometimes we take out the MSE because we want to come back at this format where it was. Okay, you can understand in that way. Here we squared it. No, we want to come back at where it was without considering the negative sign. So here it tells you it converts back to the units which was it previously in. Okay, cool though. So these are very small errors which I really want to talk on. One of the important and most important is nothing but called R squared error. R squared error, and in that we have SST, which is total sum of squares, and residual sum of squares, which we'll talk about that today. Okay, cool. So let's talk about these both in great detail so that you have a very nice understanding of what exactly you need to do. Okay, cool. So let me just start off with one example. So let's consider a very simple example to illustrate the R square error. So assume that you have a data set with one independent feature, okay, and one dependent feature. Okay, so let's consider the index number, the observation number, which is observation number is 1. So we have X, which is the index feature, which is 1, and Y, which is the target, which is 3. Okay, so 2, 2, 5, and then you have 3, 3, 7, and 4, 4, 9. So you have the index number, the observation number, and then you have the independent feature and the dependent feature. So basically you want to map a function X to the output variable Y. Okay. So now you built a linear regression model on top of it. When you built a linear regression model on top of it, basically we need to do the hypothesis test. We need to predict the y hat, right? So that let's take an example. Beta 0 is something this 0.1 and beta 1 is also 0.2. Then you want to test it, right? So you have to perform the predictions on the X and then compare the prediction y hat with Y, right? So your Y would be nothing but, so your actual Y was 3, 5, 7, and 9, and your model predicted 3.5, 5.5, 7.5, and 9.5, which is the model which your model has predicted. Okay. Now we have to compute the R squared. So the formula for compute, we'll talk about the geometrical meaning in some minutes, but the formula for computing the R squared, is nothing but 1 minus SSR divided by SST. Okay. This is the formula for calculating the formula for calculating your R squared. But let's break down what is SSR and what is SST. So SST is nothing but it's the total sum of squares. So SST is nothing but total sum of squares, which is total sum of squares. What does it tell? SST represents the total variation in the dependent, which is the variation in this. So let me just highlight this. The total variation between the dependent variable represents the total variation in the dependent variable. What differences? What variation it shows? Between whom? So it shows the total variation, how much variation to get into this, okay? How it shows that? By showcasing the difference between the actual value and the mean. So your SST formula is nothing. You go for I is equals to 1 all the way down to the M, yi minus y, which is the mean and squared, okay, to get rid of negative sign. So what does it tell? It is explaining about your y. It is explaining about a target variable. It is where we take out the differences between your prediction, your actual, not a prediction, ground truth. To explains the variation between the ground truth and the mean of this. So what is the average? So assume that average is 6. So 3 minus 6, which is minus 3, right? So the variation between the actual values and the mean. So what is the most common value in this, and what is the who are in beside of them, what is the variation is over there. So that's what it tells. So basically it is saying we have already talked about variance a lot. I don't want to discuss it once again. So it measures the variability of the target variable without considering the influence of the independent variables. Over here, are you seeing I'm taking y hat? I'm not taking y hat. I'm just taking out the variability of my target variable. How much my y is spread out. How much my y is target variable, which is dependent variable, is varying out, right? Is varying out without considering our beta 0 and beta 1. Because over here, this is our data, right? We are not considering anything. We're just taking the y, which is the mean, and then we are just trying to take out the variance. We're just trying to take out the variance between with that mean. So basically, we are not doing any sort of, there is no influence of your independent variables. There is no influence of these independent variables or literally anything over there when we calculate. So your formula for that was SST was this, where to summarize that you're taking out the differences between your not predictive, the ground truths values, the target the actual target values, and the mean of that to take out the difference. So to take out the variation in that particular, or the variability in that particular variable, okay, which is y. Then you have nothing but something known as SSR. Is nothing but SSR. So which is the full formula is nothing but residual sum of squares. So the formula for this is nothing but SSR is equals to I is equals to 1 all the way down to the n, yi minus y hat I squared. So this is something which you're familiar with. Here we are taking out the variability of the dependent variable. So basically, we're taking out the variability of the dependent variable considering our y hat. So we're taking out the variability of this. Here we are just taking out the variability without considering the y hat. Here we are over here taking out the variability with considering the y hat, because we're definitely taking out the residuals. So it represents the unexplained, so basically higher the variability matlab ki more the difference, and more the difference bad the model, because your model could not be able to predict. So higher the variability explained in this, which means that the more the model is not able to capture, which means that the model is not able to explain. Again, I'll summarize in very simple terms. The SSR is nothing but which you have studied. So I'm just going to reframe it in different terms, that you're taking out the variability of your dependent variable, considering the effect of y hat. How you're doing that? Previously in SST, what you're doing is taking out that variability of y hat without considering of y hat, just taking out the mean of that, and then just taking out the variation. But over here, you're taking out the variability with considering. So higher the variability means that your 3 is far away from 3.5. That's what it means. So if the variability is high, that means the errors are high, and if the errors are high, variance are also high. Variance means this how spread they are from the mean. So basically, the variability is also high, which means the variability is high, the model could not capture it. The model could not learn it in the nice way. Okay, so SSR over there indicates that. This is the formula. So now once you know about SSR and SST, now you can easily come back to formula. And what does it tell? Let's talk about that. So your formula tells me, so assume that we want to take out the R squared. So first of all, let's take out y, which is, let's take out the R squared for this, which is nothing but 3 plus 5 plus 7 plus 9 divided by 4, which is nothing but 6. And then you have SST, you take out the SST, which you'll get a 20, and SSR, which is residual, which is nothing but 2. Okay, now we can easily compute it. Which is R squared, which is nothing but 1 minus 2 by 20, which will get 1 minus 0.1, which is 0.9, which is, when you convert in percentage term, which is 90%. So the R squared value is 0.9, which means that 90% of the variation in the dependent variable y can be explained by the independent feature x using linear regression. So if we are able to explain, if there is a 90% variation in the dependent variable, it means that 90% of the answers are able to correctly, your linear regression model is able to give 90% of the correct answers. This is 90%. This is your model is able to correctly identify 90% of the examples. You can understand in this way. 90% of examples are correctly identified. Okay, but it's not exactly what I'm saying. It's something like 90% variation is explained by your model, which means the 90% of the variation which is perfectly explained. So if the variation is low, if, for example, if 20%, so this is pretty much low. So your model is not able to your model is not a best fit, because it is not able to explain your model. If you're 90%, by 90% your model, your linear regression is able to explain is explained. Okay,
I hope that this gives you good sense of what exactly this just says. Higher the R square value, good the model is, because it's able to explain more variations in the dependent variable y given or explained by the independent variable x. So the x is able to, which is your linear regression model, is able to explain your y. Okay. But one thing to be noted over here, there is one thing which I really want to write. One thing which I really want to write over here. Over here, maybe let's write it out. So the R squared, which means that the x percentage of the variation in the dependent variable y can be explained by x using LR. So this is what is said. So if the variation is large, then your model is good. But if the variation is less, then your model is not. But it depends on problem to problem as well. Okay. But over here, see over here that you have x. So what does it tells? If there's 90% of the in this example, the 90% of the variation in this particular y, and 90% of the variation in this particular y is explained by x. So x seems to be useful feature. Is explained by x using our linear regression. Okay, so 90% of variation is explained. You can you are able to you given the information, you're able to correctly identify 90% of them. Okay. So this is one way to understand it. But yeah, this is a very messy thing to help you understand the R squared. We'll have one practical example to have one more lecture on R squared, and there is something known as adjusted R squared. We'll talk about that. Baki, it's the end of this lecture. I really hope that you really enjoyed this. And now we are coming to the ends of our lectures specifically. Cool. So we'll talk about hypothesis testing, which is one of our last phases, and then we'll talk about assumptions, which is one of my favorite topic, and then we'll go into project, and then we'll end up this lecture. Hey everyone, welcome to this video. In this lecture, what exactly I'm going to do? I'm going to talk about one of the second last topic of whole regression analysis course is about hypothesis testing. And hypothesis testing is one of the most ignored as well as one of the most asked questions, the topics from which the interviewers asks in regression analysis, and we'll talk about this in pretty much very detail with several examples as well, like how do we use hypothesis testing in linear regression. We'll have the practical implementation of it as well in various terms, and then after working on the hypothesis testing, we'll go forward and talk about We'll go forward and talk about something called as something known as assumptions of linear regression, where we'll talk about some of the things, but that's for later purposes. Currently, our aim should be finish this hypothesis testing in very detail. Now, one thing which I recommend over here is sometimes you will see formulas. I would suggest you to completely ignore those formulas. Okay, sometimes there is some formula which will come up. The main idea from which you have to take up is how you can understand the concept, the core of it. Formulas can be seen later on as well. So how can you understand the core of it? By understanding the crux by several examples, which I'll try to take. Okay, cool. So now what we will do, we'll try to start off with this. But before that, I just want to clarify some of the things that, as I said, formulas will come. Please ignore if you're not able to understand it. And at any point, if you're not able to understand it, suggest go to our Discord server. And ask directly by giving the timestamp. You should tag the help or create a ticket directly out there, and then ask the question in a machine learning section about any such questions if you have. So let's get started eventually with this. Basically, you must have studied about hypothesis testing in statistical and probability lectures. If you haven't, please I consider to watch a little bit of lectures around hypothesis testing, because I assume that you know a little bit about hypothesis testing. However, I'll also describe over here if you don't know. But if you're not comfortable with statistics and probability, I would highly suggest to go and watch our stats and prob lecture, which is one of the most important, lectures, but it is available on our course, which is CS01, or you can say machine learning course by Anton. You will be able to see everything out there. But let's get started with actually this lecture. So basically, what is hypothesis testing? Hypothesis means some sort of statements or to be made, some sort of statements which is not yet, means like this is the hypothesis which we want to test. We say now this is an hypothesis which we want to test. So the formal definition, if we go to hypothesis, so hypothesis states that the hypothesis states that is what that the statement or the explanation, like for a statement, is made based on limited evidence or maybe small amount of evidence. For example, one of the example can be, if you stay up late, then you feel tired the next day. That's one of our hypotheses. Right? So these are some of the hypotheses. So how can we test that hypothesis? How can we validate that hypothesis is valid or not? How can we validate the current example which you have taken? What example which you have taken? The example which you have taken to say, we are saying that if you stay up late, then you feel tired the next day. That's one of the example. So how can we add, if you stay up late, how you'll file next? How can we validate it? So hypothesis testing deals with validating your hypothesis using several tests. You conduct tests for identifying that. But never mind. Let's actually talk about, let's keep talking about hypothesis testing. So it is a statistical method in terms of statistical maths. It's a statistical method which helps to make decisions about the data eventually. For example, that statement, what was that? If you stay up late, you feel tired. If you feel tired, okay? That's one of them. Another one is, let's say for the sake of an example, another hypothesis can be daily exposure to sun leads to increased level of happiness. That's one of the hypotheses. So previous hypothesis was if you stay up late, you feel tired. Second example of an hypothesis: exposure to sun, what does it lead? It leads to increased level of happiness. So this is one of them. So these are some examples. So basically, hypothesis testing, what does it do? It validates whether this statement is true or not based on the data. It takes the decision whether this statement is true or not based on the available data, based on the available evidences. Okay. So there are eventually two types of hypothesis which we generally know. Something known as a null hypothesis and alternative hypothesis, or you can say H1, so S0 and H1. So what does it mean, like null or an alternative and blah blah blah? So let's talk about both of them in great detail so that you could understand in pretty simple language. So let's take an example that your hypothesis is that your hypothesis, what is your hypothesis which you want to validate? You want to validate whether let's take in a pharmaceutical company invented a new drug of weight loss drug. Okay, so they invented a weight loss drug. And they want to test this hypothesis that the weight loss is effective. Okay, and if the hypothesis is true, then we say that if this is the hypothesis. What is hypothesis? Weight loss drug is effective. Okay, so we want to test this hypothesis whether this weight loss drug the company invented with the new weight loss which they have invented, is it effective or not? So this is an hypothesis which we want to test. Okay, so there are two types of hypothesis. The first one is null and second one is alternative. So what is the null hypothesis in this particular example? The null hypothesis in this particular example, the new weight drug which is published or which is invented has no effect on decreasing your weight. Okay, so we say that your null hypothesis, in the population, this is the population mean, which is that indicates the drug effect on the population is zero. Means the drug effect on a lot of people is zero. Okay, and that's null hypothesis. What exactly null hypothesis states? It says that a drug has no effect. But your alternative hypothesis, what does it states? It states that your drug has an effect. Your drug has an effect on decreasing the weight loss, which means that your population, in the population, this is working, which is not equals to zero. What does it mean equals to zero, and what does it mean? You mean the population mean equals to zero, which means that it has no effect. Population which is not equal to zero, which means that it has some effect. Okay, because if the mean is 0, on the number of people, for example, this you can assume the number of people which this drug if affected is 0, which means that that drug does not affect, but over here it is not equal, so the drug eventually affected the population. Okay. So how can we validate? How can we test it? So basically, we want to test whether we will consider null hypothesis or alternate. And a particular example, this particular can be either classified in null or hypothesis or a alternate hypothesis. So when we want to conduct a test. We want to conduct a test to identify whether it is null hypothesis, which means the drug has no effect, and an alternate hypothesis, which means the drug has an effect. Okay, so this is two of them. Which one to go for? So we have several tests in our statistical tools to conduct whether the drug has effect or not. Some of them are t-test, f-test, and there are several other as well. So we'll study about t-test in great detail. F-test will be given to you as an homework to actually work on by yourself, because we want you to be not even spoon food like this. We just want you to be expert in everything by yourself as well. So you now you're at a journey where you have to explore things by your own, right? If you came over here, this means that you have achieved a lot in your career as of now, in terms of learning. Okay, so of course, when you conduct a test, it will give some sort of number. Assume that C, right? So in what we do, for example, you got C. So we need to classify. No, you have to classify whether this is a null or hypothesis. So if assume that you conducted a test, don't worry, we'll talk about each test in great detail. You conducted a test and then you got some number C. Okay, you got some number C. So we check with the significance, with which is threshold, and we say that if your test value is smaller than this particular 0.00, which is 5%, smaller than 5%, then what we do, we reject the null hypothesis and then we accept the alternate hypothesis, which means the drug, then the drug has an effect. So if your value from the test which you conducted is smaller than the significance value, which is 0.05, which is the standard threshold which we keep for when we used to test. So t-test will give you some number, and then you compare with it. If the test value is smaller than this, then we say that the drug has an effect. Why? We'll talk about that later on, great detail as well about this. Don't worry. Okay. And then if it is greater, or your t value is greater than this, then we say that it is a alternate hypothesis. Sorry, we reject the alternate hypothesis and then accept. Basically, anything above the 5%, and your value t value or the test value is greater than 5%, then we say that the drug has no effect. Then we say the drug has no effect. If it is smaller than 5%, the drug has an effect. Okay, that was one of the example. Let's talk about in great detail. This was just an example to showcase you the hypothesis testing, but how we use the hypothesis testing in linear regression. That's one of the most famous questions to talk on. I just was getting a Red Bull. I'm so sorry for that. Okay. So how can we think about in terms of linear regression? And this is something which everyone needs to know about. This is something which everyone needs to eventually know about. So let's get started with that as well. Yes. Good. So how can we use that in linear regression? So basically, I'll just go through a past example so that you could be understandable in easy way. I rather prefer all of this thing. Okay, so this is one of them. This is one of them where we talk about f-test. Yeah. So basically, how does we formulate our hypothesis in terms of linear regression? So in a case of linear regression, the claim is made that there is a relationship. So what is an hypothesis? Hypothesis is that there exists a relationship between a response and a predictive variables. Now you might be thinking, why do we need hypothesis testing? So basically, how does it helps? Now all of this might be in your question, but first of all, I understand that your question is, so let's go ahead and talk about why exactly we need hypothesis testing. So assume that you wanna build a function f that takes in the number of hours of study, and the attendance percentage of a particular child, and then predict what will the exam score. So it takes the x1 and x2 and predicts y. which is the exam score. Okay, so it takes x1 and x2 and predicts y. And this is a nice this is the function which you have to build. This is the function which you have to build up. Okay, so you have now so it may happen. Now what do you want to do? You want to interpret, right? Is this significant to output variable? Is this information, is this particular independent x1 is significant? What does that mean, significant? Significant means important. Okay, it's like you can understand, is it significant? Is it even reliable for this? So basically what we do, the first hypothesis formulation is there exist any relationship between both of them? Yes or no? How can we identify relationship between both of them? How can we identify is there any relationship between both of them, the input variables and output variables? By calculating the significance. Okay, how much this value x1 is significant to this output variable y. Okay, because this is important in terms of the reason why it is important. The reason why it is important. Say, for example, x1 and x2, and you're getting the y. So basically, you identify the relationship between both of them. So if there is no relationship, then your machine learning model will be not able to perform well. So you can tell to stakeholders that there is no relationship into the number of hours a particular student study, that whatever number of hours student a particular study, it will not affect exam scores. Exam scores will be according to some other factors. Okay, so this can be one of the possible factors. So if we should first of all assure ourselves that there is a relationship. Okay, this is one of them. So there is a relation. How can we identify there is a relationship between input variables and output variables? We can identify the relationship between the input variables and output variable by identifying the significance of our input variables to output variables. Okay, so we can say that okay, so this is this significant to our output variable? Yes or no? Yes or no? Is this significant to our output variable? Yes or no? X1 is significant. So if so question is your number of hours study is significant to your exam scores? So this is the hypothesis formulation. Hypothesis formulation, what does it says? That there is a relationship between input and output variable, between input and output variables, or independent features and dependent features. Okay, and then we go to the x2 and then say, okay, is this something related to, is the x2, which is the attendance, is also significant output variable? Yes or no? Okay, so this is how this is very important, because we want to identify is there even a relationship, and assume that x2 does not have a significance. So we can drop this column, we can drop this feature. If we drop this feature, it will definitely help us in getting the robust model, because this is just unnecessarily over here, because it's not contributing to your output variable, does not have any relationship with the output variable. Understanding what I'm trying to say, I'm just trying to convince you that there is a relationship. If there is a relationship, that's the build of a hypothesis formulation. We'll talk about all of this in great detail, but you can understand. There exists a relationship between the response, which is the y, and the predictor. So that's the hypothesis formulation. Okay, so what the formulation of hypothesis says that if the claim is represented using the non-zero, then the alternative, this is the alternate hypothesis, and if your beta value is 0, then this is a null hypothesis. I know you didn't understood anything. Let's talk about what exactly that statement says. So what will be our null hypothesis in this claim, and what will be our alternate hypothesis? Null hypothesis means that there are no relationship between whom? Between your independent x1, x2, and y. There is no relationship between x1 and x2, y. And what is the alternate hypothesis? Alternate means completely opposite. Okay, that there is a relationship between x1 and x2 and y. Okay. So we now how can we say that? How can we even make it more mathematical? So null hypothesis, can we say that null hypothesis where your beta 1 and beta 2 are equals to 0, or we can say all your betas are equals to 0, or all your beta 1 and beta 2 are equals to 0. Null hypothesis means, for example, I know it's very simple to understand the concept. Please apply your mind now over here. That you have your hypothesis, which is beta 0 or beta 1, beta x1 plus beta 2 x2. Okay, you're understanding. So if we say that if if there is no effect of this in output variable, which means that this is equals to 0, this is equals to 0. Bro, I'm just trying to say that if this is equals to 0, that means that will yield to 0, and that will not affect your output variable. But what our eventual null hypothesis is saying, that your x1, x2 does not have any significance, right? So if your beta 0 is equals to 0, that means that x1 does not have any significance. If your beta 2 is equals to 0, that means x2 is also does not have any significance on output variable. Okay, so your all betas will be equals to 0. In null hypothesis, all betas are equals to 0 in null hypothesis. An alternate hypothesis says that which means that all the betas are not equals to 0, That's your this is your hypothesis. Now you might be thinking a bit of how this coming. Again, I'll summarize it for you. That your h of x is nothing but equals to beta 0 plus beta 1 x1 beta 2 x2. So null hypothesis, what does it say? That there's no relationship. If there's no relationship, that beta 1 is, if we make beta 1 to beta 2 to be equals to 0, that means it will whole yield to 0 and this will whole yield to 0, which means they're not affecting any output variable, right? But what if there's something out of 0? That is alternative, which means that it is affecting some sort of output. It is affecting some sort of output variable. So in null hypothesis, we say that all our beta value are nothing but 0, but the alternate all our value is nothing but not equals to 0. This is our hypothesis formulation in linear regression. I hope that this gives you a very good understanding about what exactly we aim to start solving about this. Okay. So now you can see that if everything is equals to 0, equals to 0, that means this is a null hypothesis, which means that does not have any output, that does not have any consequence on output variable. But if there's not equals to 0, that means they have a consequences on output variables. So there are 3 types of tests we should talk on, which is test for significance of regression. Is it a regression problem or not? Maybe it can be easily classified when we'll talk about linearity assumption. It can be easily talked about linearity assumption, which we'll see that later on. One is t-test, which checks the significance of individual regression coefficient. So what does it tell? I think I did a bit wrong. Yeah. So what is the t-test does? T-test, as I said, that we have an hypothesis where our S0, where what does a null hypothesis indicates? That our beta value is nothing but equals to 0. And our alternate hypothesis, what does it indicates? Our beta value is not equals to 0. This is our formulation of our hypothesis testing, which we're going to test. So in a test, we want to test whether there's exists relationship or not. So we have a test, right? We conduct a test and then we get some certain value. Let's assume C. So if that C is smaller than 0.05, is smaller than 5%, we'll talk about that this again significance just in a second. But if this smaller then we say that we reject the null hypothesis. That means there is a no, we accept that there is a relationship. But if it is greater than 0.05, that means that we reject the alternative, that there is no relationship between the variables. Okay, reject this alternate and then we accept this. We'll talk about the significance just in a second. So this test checks the significance of individual regression coefficients individually. Okay, not something like it checks that whether this x1 is significant to output variable or not, or whether it's x2 is significant to output variable or not. How does it checks? That if your beta 2 is equals to 0, so your hypothesis will be h0 where beta 2 is equals to 0, and h hypothesis with beta 2 is not equals to 0. So this is a hypothesis. It checks individually, and once it checks individually, we can easily take out the overall significance. Okay, so if we take out individual significance, then we can easily, okay, this x1 is not significant, then we can remove this x1. How can it, if the beta 1 of x1 is 0, that means that it is not significant. And then we have something known as t-test. And then we f-test, and f-test is used for taking out the overall significance of your regression values overall, which means whether this overall equation is significant or not. Okay, significant means overall. So the hypothesis formulation would be the null hypothesis would be beta of all the beta values, and the null alternative, which is all the beta values not equals to. So this is the hypothesis formulation. 3 tests. Let's talk about the first test, t-test. Test will be left upon you to explore. I hope that I'm giving you a very great knowledge out of it, and I really hope that you'll utilize this information, because for me it takes a ton of time, to develop this, and I hope that you're enjoying this course out till here. And if you are till here, that means that something you're a special guy, that's you're a special guy, and you're always up for ready to take challenges out there. Okay, cool. So now I've been talking about something known as significance value. So we'll conduct the t-test. So how can we conduct the t-test? So there are some steps for conduction of a t-test. I'm directly going to the t-test formulas, so that it will make much more sense to you only when we'll do one example. Okay, so let's go to one t-test example. Yes. So you're basically, again, I'll just write the t-test example so that it makes much more sense. Yeah. So your hypothesis formulation is, so assume that let's take an example, because I really like to take examples in every bit whatever I'm explaining, because that something makes me motivated to, like, you're able to understand by the simple examples. So example, what does example says? Example says that you want to build a simple linear regression model. We build a simple linear regression model. And what does that same simple linear regression model build? It will build the function f. That takes in the square footage, the square footage, or you can say the size of the house, and predicts your price. So given the x values, you're going to predict y. I'm just taking a simple linear regression to make you understand. So in this case, what will be our null hypothesis? Null hypothesis, which means this does not have significance to output variable, which is null hypothesis nothing but your beta 1 is equal to 0. Okay, and alternate means that your beta 1, which means the beta 1, is the coefficient of this x1, right? Beta 1 is not equal to 0, which means that there is this means there is no relationship between x1 and y, which means that no relation between size of the house and price. Size of the house does not affect price. And this alternate means there is a relationship between x and y. That means that there's a relation, that size of the house definitely affects this price. Okay, so when you fit the linear regression model, you have the following equation. Now what you do? You do the test. Now you do the t-test. How we'll talk about just in some seconds. But the formula for doing this test is we do individually for every parameters, right? If we do the individually for every parameters, so we calculate the t statistic. The t statistic for whom? T statistic for the size of the house, because it does individually. So we'll take out the t for every individual parameter. So currently I'm doing for only one. So it takes the t statistic for the size of the house, which is estimated coefficient, the coefficient value. So in this case, it will be beta 1 minus 0, divided by the standard error of that beta 1. A very nice equation, a very confusing to a lot of people. Now, let's talk about why does it confusing, and let's talk about each and every integrity of it. Okay, each and every integrity of it. So we'll talk about why are we subtracting it, why are we dividing with standard error, what is a standard error, and so after conduction of this test, what we do, so that it makes much more sense to you in your initial stages as well. Okay, so let me just open my calculator, because this is something which will be required. So let's first of all talk about the general formula. So the general formula for calculating the t value, t statistic for a particular beta is nothing but estimated coefficient, the coefficient which is estimated, because we have to train this hypothesis testing only can be tested if you have a fully trained model, so that you can test your hypothesis. Okay, estimated coefficient minus 0 divided by standard error of that coefficient. So what does it measures? what does it measures? So what we are doing over here, so basically we're calculating the t statistic, and then we are subtracting the hypothesized value from the estimated coefficient. So you might be thinking, what is hypothesized value? This is something which is confusing to most of the people. So hypothesized value is the value of a coefficient under the null hypothesis. So we first of all assume, okay, in basically what we do, we hypothesize something, we make something like true, like there is a no relationship. We prior to assume that there is no relationship, okay, and then we disprove that. So hypothesized value is 0 in this case, because your hypothesized value is 0. Okay, so estimated minus the hypothesized value, which means the value of the coefficient under the null hypothesis. Okay, this is the hypothesized value which is under the coefficient. So if the beta 1 is equals to 5, that means you write 5 over here. Okay, if the but it should be in a null hypothesis. So we pre-assume things that we already assume that there's no relationship. Now we disprove that with t statistics. So if you're not able to disprove that means there is no relationship. But if you're able to disprove, then we accept the alternative hypothesis. Okay, so over here, this assumes usually that there's no relationship. So basically, we subtract with the hypothesized value, and then we divide by the standard error. So what does a standard error means? What does standard error means? So let's just go and talk about a very nice explanation of standard error, because this is something also people worry a lot about. So standard error is nothing but it's nothing but the accuracy of an estimated value, the accuracy, or how much uncertain your regression coefficients are. So I'll take a very simple example to make you understand about this. So basically assume that you built a linear regression model, and the standard error is the measure of uncertainty of the estimated coefficients, and then describe the ratio. Basically, uncertainty means the standard error. So I'll just write it over here. Standard error, it measures the uncertainty, or the accuracy or preciseness of the estimated coefficients. This is a very important to talk on, that the standard is nothing but the accuracy, uncertainty, preciseness. So lower the uncertainty means better your coefficients. So basically it evaluates how your coefficients are uncertain, how your estimated coefficients are accurate, how your estimated coefficients are precise, and all. So these are certain words to talk about. So basically you calculate. So basically you calculate and say that, okay, this is something is used to indicate how precise or accurate your estimated value are. Okay, so again, you might be thinking, so you might have beta 1 equals to 2. Beta 1 is equals to 2 by estimated by your gradient descent. Okay, estimated by your gradient descent. That's one of them. So when you estimate beta 1, so how much precise this is, how much accurate this is how much uncertainty it contains, how much unsureness, how much we are sure about this. We quantify that. So we quantify how much we are sure about that. We quantify how much we are accurate about a particular beta value. That's what the standard error means. Standard error means how much we are sure about that particular beta value. Okay, how much you're sure about that. I hope that it gives you. So if your standard error is high, if your standard error is high, that indicates that there is more uncertainty, less accuracy, less preciseness. Okay, so if your uncertainty is high, which means not sure about that. that means that is bad. No, if you're not too much sure about the particular coefficient, that means that means that is something wrong with it. And if it's super accurate with that, and you're also not accurate. So if your standard error is small, that means that your uncertainty is low, which means you are too sure about. You are able to quantify things. You are able to quantify how much sure and unsure you are. So in this case, if your unsureness is too low, which means that you're sure of that beta value is 2, that means that is good. So your standard error should be less. So basically what we are doing, we are simply subtracting. Sorry, we are simply, first of all, now you understand this full equation. You calculate the t value, which is beta 1 minus 0 divided by the standard error. So now what does the division gives you? This is something which is usually taught in the statistics classes, and I usually recommend you to not even which is not even recommended for you. Even if you're just curious, you can just go ahead and talk about things. But what I'm going to do is talk about my interpretation from what I understood, because that's something I also have to take care whether I understood it nicely or not, right? So let's talk about that. Otherwise, it will be a bit off to me as well. So the t value which you're going to get over here, which will give you a number, so that we can compare with the threshold. We'll talk about to the threshold just in some seconds, just after this topic. So the this is called the t statistic. What is this test? It helps us to assess the significance of the coefficient relative to the variability or the estimate or the uncertainty of our estimates. So what does it tell? Again, I'm going to repeat. It tells you, please remember, the significance. It tells you, I'm not taking very mathy, if you go online, no, everybody is taking so mathy things. I'm not able to even understand why they're taking mathy things. But it tells you the significance. Of a coefficient relative to the uncertainty of the estimate. That's exactly what does it t-test gives you. And geometrically, if you understand it, it can be thought of as how many standard errors the estimated coefficient is away from the hypothesized value. So again, geometrically meaning, I know this is something confusing as well. I can ask you to ignore it as well, but if you just want to understand in much more depth, it will be easy for you. So it can be thought as how many standard errors are away. Are the coefficients, the standard errors of the coefficients is away from the hypothesized value, is away from our, what is hypothesized value, which means that we already assume it, which is our beta is nothing, which hypothesized value, which is equal to 0. So what does it give? Now this is something which how much our standard errors are away from that. Okay. So now what does it give? The t-test, what does it give? It gives so if once you calculate the t statistic, so we can understand in two ways, either by this particular example or this particular. What does it give? A significance of a coefficient relative to the unsureness. What is the significance of a particular coefficient with respect to the, or relative to the, there is uncertainty of the estimate. The higher the uncertainty, like it's not good, right? So the large t statistic. So now let's talk about what does it mean. If you have a large t statistic, what does it mean if you have a large t statistic? So if you have a large t statistic, it indicates that your estimated coefficient is different from the hypothesized value. Is different. So large t statistic means that your estimated coefficient is different from the hypothesized value, is different from hypothesized value, which is S0, which means that there is a relationship between your HJ, between your beta 1 and Y. Okay. So this is what large T statistic mean. You will be talking, but usually it depends with the if you have the p values, we have to compare with our p value. But as of now, why do we divide? We divide because it tells you the significance of our coefficient. Now, once we have the significance, now how can we say that okay, this is the perfect? Like how can we identify whether to accept the null hypothesis or whether to expect the hypothesized value, which means the pre-assumed thing, which is that there's no relationship, or should we accept it, or should we reject that we have an evidence to say that there is a relationship between that. Okay, let's talk about that. This is something important to talk on as well. I'm just talking too much. I'm so sorry for that, but it's actually 38 minutes. But this is something which is important as well in terms of understanding level as well. Okay, so let's talk about p-value. Let's talk about p-value. So p-value over here, what does it p-value means? So once we have the t statistic, once we have the t statistic, we compare with the threshold value. Usually this threshold value is 0.05% or 5%, and we say that if your t statistic is less than 5%, then then we can reject our null hypothesis. Then we can reject our null hypothesis and say that there is, if it is greater than 5%, then we say that okay, this is something null. Then we can reject the alternate hypothesis that there is no relationship. Then we can say that there is no relationship if your t statistic is greater than the t critical value. The t critical value. Okay, currently t statistic is different from t critical value. T critical value, which we'll talk about it just in a second, but assume that you got some critical value and then you compare with a 0.05. Okay. Okay, so you can take a break as of now. Even I'm speaking for the last 40 minutes, but that's all right. This is something which we have to do if you want to understand hypothesis testing in detail. So basically, what is the so how can we say that? How can we say that if your t critical value, the critical value, the value which will get, the probability, the critical value which will get is if it's smaller than 5%, then only if it is. How can you support that statement? We can say that. How can we say that? How can we say that? As I say that the null hypothesis is a statement that assumes that there is no effect. There is no effect or the relationship. So there we introduce a concept of something known as p-value, and threshold value, or it is also called nothing but p-value. So what does p-value means? It says that the observed result is unlikely to have occurred by chance alone. And so basically, what does it mean? I know it's something chance and all. It's something which is also very great to understand it. But I'll take a very simple example so that you have a nice interpretation. So assume that you want to test if new weight loss supplement is effective on weight loss or not. Again, the same example which I've taken up. So you conduct an experiment on two groups of people. So group number 1 and group number 2 conduct on two groups of people. And then once you one group that takes the supplement and other takes the place, which is the other takes the supplement. One group takes the supplement, other does not take that supplement. Okay, so hypothesis, what does null hypothesis says? Null hypothesis says that there is no effect of that supplement. Okay, that there's no effect and no difference. There's no effect. So basically, there is a two groups. Again, there's a two group number 1, group number 2. So each taken their own treatment effect. The supplement, the supplement number 1 and supplement number 2. Okay, so the null hypothesis states that there is no difference between these two. So identify if there's any difference. That's an hypothesis, and the hypothesis, the alternate hypothesis says that there is a difference, which means that if there's a difference, that means there is something cooking in that. So we can of course use that for treatment effect, but null hypothesis states that there is no difference. So after you conduct the experiment, you calculate your critical value, and then what you have a significance. And then your critical value comes. T critical value is 0.02. Okay. And 0.02. So your value is 0.02, which is the t critical value by taking all the t statistic, you calculate 0.02. Now your threshold was 0.05, right? So what this means, that means that there is enough evidence to support that the weight loss supplement has an effect on the weight loss. So we reject the null hypothesis. Why we represent? So if your critical value is smaller than your significance value, then we reject then we reject our null hypothesis and accept our alternate hypothesis. Now you might be thinking, why does it happen like that? Why does it happen like that? This is something this is something which also you need to understand. So this is a general thing. If a critical value is smaller than this, then we say that okay, reject the null hypothesis, and then we accept that there is a but if you got 0.07, that means that you have to reject your alternate hypothesis, accept the null hypothesis. Okay. I know this is something hard to understand as well in the initial level, but you have to understand it anyway. Assuming that you have brain for this. Cool. So how can we connect this? How should we connect this p-value, the concept of p-value, to linear regression? So in linear regression, your null hypothesis states that the independent variables and dependent variables has no effect. Your independent variable has no effect on the dependent variable, which means all your betas are equal to 0. And the p-value associated with every coefficient help us to determine that has a significance with us. So basically, you have a critical value. In this case, you'll be having critical value for every betas. Okay. So currently, we'll be having critical value or the p-value for this size, which states the significance of our size of the house on the price. So in this example, as we have seen, so you obtain the p-value, or we can say, so there are p-value, or we can say critical value. We can say critical value by taking the t-test and then comparing with the t-test distribution. We'll talk about that. So you calculate the t-test after calculating the test over here. After calculating this, you compare. After you take out some number, you compare with the table. And the table, it is a table which is already published on the internet. Okay, you don't need to remember everything. You don't need to worry about how this came. You compare. Okay, this is something over here. Now this is we'll select how do we select the p values as well later on. But you calculate how much significant, what is the probability that that size of the house is significant. Okay, you calculate the p value for the coefficient of what? For the coefficient of your size of the house. And now we say that if your p-value is less than 0.05, which is the threshold, you reject the null hypothesis. You say that there is not enough evidence to accept the null hypothesis. So you might be thinking, what does it mean, bro? Why do we don't say if your p-value, like if your probability is higher, that means that it is something significance. It is not. Okay, p-value is always related to the null hypothesis. So higher the p-value is, the more you're providing evidence that there is no relationship. Lower is that there is an evidence to reject them. There is evidence for alternative. That there is a lower chance of there's a lower chance that it occur, that it is a null hypothesis. Okay, I hope that you are understanding what I'm trying to say. If you're not, then please watch the lectures once again so that you're able to understand in much more easy way. So if you want, I can actually take an example. To help you understand what is chance and all. But let me know if you want to understand about that. Like, how can we? There's a support to statement. How can we say that why not greater? Currently, you can understand this way, that if the p-value is smaller than 0.05, you reject the null hypothesis, accept the alternate hypothesis. Okay. If you want to know, please let me know about that as well, because I have a very nice explanation, but that is a bit out of the context of the course. But it's all right. I can actually understand. This is something which people face as well. Cool. So now once we have that, if it's greater than or smaller than, we accept or reject our null hypothesis. Cool. I hope that this gives a good sense. Now let's do a very nice example, a numerical worked example, so that you understand it nicely. And then we'll be done with the t-test. You'll be left with f-test by your own. You'll be left with the f-test, which you have to explore by your own. I'm not going to talk about that. So let's talk about, let's continue our previous worked example. Our previously worked example was that you have a square footage, which is 1,200, and then you have 1,500, 1,700, 2,100, 2,300, 2,600, and 3,000. Okay, and then you have nothing but the y variable, the price of the house. You can understand some sort of price. Okay, I'm not writing the data, but I'm just making it like this. Okay, so your equation will be beta 1 plus beta 0. Beta 0. I think I did it wrong. Beta y is equals to beta 0 plus beta 1 x. Okay, x1. So assume that your beta 0, assume that your beta 0 is nothing but 50,000. Okay, 50,000, and your beta 1 is nothing but equals to 100. Okay, so so let's state our null and alternate. So null is h0 is where all your beta values h1 is, the alternate is they are not equals to 0, that there is a relationship existence. You calculate the t statistic, how it is calculated, estimated. We have to calculate for beta 1. Okay, because we are going to take out the significance of this x1. You calculate the beta 1, 100 minus this is the estimated minus 0. Well, because minus the hypothesized value, in this case it is equal to 0, divided by the standard error of that coefficient. The standard error is also it's a nice formula for calculating of a standard error, but in real world you don't need to worry about the formula. You can actually look on the internet to calculate the standard error formula. So the standard error which you're gonna get, is nothing but the whole calculation will yield to 100 divided by 10, which is nothing but equals to 10. So your t statistic is 10. Now you might be thinking, hey Ayush, this is the greater than this, but in most of the cases this will be greater, right? No. Once you calculate the t statistic, now you convert this into, you can understand, you convert this into a probabilistic value. Understand in this way. I used to understand in this way that you convert this into some sort of probability value so that we can compare with the threshold. Okay, so for calculating the threshold, for calculating the threshold of critical value, so that we can compare with our significance, which is 0.0, so that we can compare. We cannot compare this. We should compare our probabilities values. We calculate something known as degrees of freedom. Degrees of freedom is calculated by n minus 2. The number of rows which you have in a column, number of rows which you have in a data, minus which is number of parameters of your model. In this case, it is 7 minus 2, which is nothing but 5. Now you may be thinking, what is degrees of freedom? Again, new question asked. So degrees of freedom is nothing. So if you also review the notes, I have written a very nice and detailed notes on what is degrees of freedom, so that you also understand it. So if you go down, so degrees of freedom is nothing. So assume that your data set contains 10 observations, and regression model has 2 parameters, the intercept and the slope. Okay, in this case as well, it was intercept and a slope. The degrees of freedom is equal to 8. So what is degrees of freedom? Is used to describe the number of independent ways a system can change. Number of independent ways a system can change. This is used for calculating. If you're not able to understand, I would say ignore it. But eventually eventually this has a statistical meaning, where it says that number of independent values, or the independent values in your data set. So basically beta 1 and beta 2 of course is dependent, right? Number of independent values of your model. The number of independent, why we say that is number of independent, you can search online more about degrees of freedom, but this is number of independent value which so basically the two are dependent because it's slope and intercept which is dependent. So we can subtract it from our whole data number of observations, will eventually get your output variable y. The degrees of freedom. So once you calculate the degrees of freedom, in this case is 5. Okay. Now your significance value is 0.05. Degrees of freedom is 5. Degrees of freedom is 5. Degrees of freedom is 5. Okay. So your significance is this. Degrees of freedom is this. Now let's go ahead and talk about something known as t-table distribution. So ACD, open up the t-table distribution. To do that, you'll need to be online. Oops, I'm not online. That's pretty bad. So yeah, so I'll put up you should open it online by your own. I'm not online as of now. So I suggest you should open by your own so that you understand it by yourself as well. Open that online and then just go to a table. And then if you see on x-axis on the top of it, you have nothing but t values. The probability, which is you have to go to two tails. In regression, you always use two tails, not one tails. The difference is listed in the reading materials. Please see that. So in two tails, you see that 0.05, you see that there is 0.05, and then if you see the fifth, the degrees of freedom is 5. That is 2.57, 2.571. 2.571 is your critical t value. 2.571 is a critical t value. Now you compare the t test statistic with the critical value. So it shows that if your of course t is greater than 2.571, t is greater than of course 2.571. So we reject the null hypothesis because this means that there's a significant relationship between that. So you might be saying that yeah, you should just some seconds ago you told that it should be smaller than the critical t value. So not about that, but in this t-test, of course we do in several examples, but in t-test we simply do this is we simply reject the null hypothesis in the favor if a t-test statistic, if a significance level is greater than the approximated critical value, because of course it changes. So as I said, your t statistic should be greater if the significance is greater than your approximated value, then we say that okay, this is something to be predicted nicely. So I hope that this gives you a good sense. If you want to know more about all of these things, I would really suggest go forward and talk about. I have also given several examples above. So if you go and see several examples of mine of t-test, you can go over here and talk about like for every individual predictor variable. You should be able to view it nicely. But my point was that you can easily use the materials to actually t-test, to calculate t-test statistics and then approximate a t-critical value and then compare and if the t-test is greater than approximated critical value, then you go forward and accept it. Okay, cool. But you have to also make sure that but it depends on several other problems from test to test. So that was pretty much about t-test statistic. Now what we'll do now we are done with almost hypothesis testing. Now we'll go ahead and talk about assumptions of linear regression, and then we'll wrap up our whole course with the one project. Hey everyone, welcome to this one of our last of lectures. I'm super excited that we came along over here, and I hope that you really understood each and every integrity of everything which you should know. We have talked about a lot of things as of now, and it's still not ended yet. Let's say we still have a lot of things to explore. We still have a lot of things to cover up. And one of the things to cover up, which is one of the most famous interviews kind of thing, is assumptions of linear regression. So basically what I'll do is I have tried to make it in a unique way or a structural way. Okay. So basically, we have several subtopics to cover in this. The subtopics are linearity, then you have, independence, then you have normality assumption, and there are several other assumptions listed out here. So what I'll try to do, I'll make sure that you understand each of the subsection in great detail, and I'll make sure that you also do your substantial research by yourself. Okay. Cool. So basically, let's start off with the first assumption. These are the notes for you to, review quickly, but I prefer using my own hand right now. So let me just open my new hand, which is this one. Let's open a dotted paper. Once we open the dotted paper, let's get started now. So the first assumption, but what exactly assumption is? Now you might be thinking, hey Ayush, okay, this is an assumption, but what exactly assumption is and why do we need to study about this? So assumptions. So what is the definition of assumptions? So tell me the definition of assumptions. So first of all, let's get it clear about what exactly the formal definition on dictionary says, because anything which I learn about anything, I just make sure that I know that definition of the topic. So thing is, what is assumptions? The thing that is accepted as true or as certain to happen without any proof. a very nice definition. So what this says, when you apply a linear regression model, this linear regression model assumes several things without any proof. It assumes that your data should be linear. It should follow linearity assumption, homoscale or no constant variance assumption. There are a lot of assumptions. So your assumes all of these things and assumes all of these things, and then you can expect your model to work fine. So if any of those assumptions fail, like if any of the assumptions fails, then you cannot expect. The LR model will only perform best if and only if these assumptions are met. Assumptions means certain things are met. Like for example, when we have something like, let's take an example, when you prove something, or when you say no, assume that this is something, and then you put an argument. So when assumption is that not true, then how can you say that particular thing will work, right? So assume that we have some certain assumptions to be there, and then we expect these assumptions to be true for our LR model to work perfectly fine. Okay. So this is one of the definition of assumptions in a great detail. Now what I'll do, I'll talk about, there are several assumptions. So as I talk, there are several assumptions. So I'll talk about some of the most important assumptions for you to explore it out right away, and then we can further get started onwards. Okay. So the first assumption which I'm going to talk about is something known as linearity assumption. Linearity assumption. Please ignore my handwriting. I have to write it super quickly. That's why I'm writing it super duper quickly. So linearity assumption says that what does it says that? It says that the relationship between the dependent variable, independent variable is linear. Okay, so what does it says? The relationship between, as this linear regression, so it expects the linearity assumption where it says the relationship between the independent and the dependent variable are linear. So what exactly linear is? As I've already talked about, it means that we can have the straight line which can represent or approximate our data. So we can have a straight line that can reasonably approximate our data. Okay, so over here, this is a very nice example of the linearity assumption. This data where we have only one input feature and then your output variable, you plot this y onto this and x onto this. Now over here, it can be your data is linear. Why? Because it can be approximately on the straight line data. But in this case, this is not a linear. Over here, you cannot make a straight line to data. It forms something like this, which is not linear. Okay, it cannot be reasonably approximated as a straight line. So that's what the linearity assumption says. Okay, so this is important. Why this is important, or why this is important? Because accuracy of the linear regression model relies on the underlying relationship, which is nothing but linear. Okay, so if your model is not linear, assume that in this example, the errors will be super high. And if the errors are super high, which means that your model is not performing well, and it can fit in any way, you will not be able to perform well. You have to use extensions of linear regression to work on this data, but we'll talk about that later on. But over here, it will definitely not work pretty well. Okay, so this is something which you should know about. Like this is an important assumption because it will lead to inaccurate predictions because of high error. Okay, cool. So once we have those assumptions, so which you can see, if you plot the data on a graph, the point should show that it should be reasonably represented in straight line. And if does not form the straight line, this means that they are not significantly appropriate, or we should use this other significant model, which is a polynomial regression or other regression, to actually make it more appropriate. Okay, cool. So this was one of the example. Now, as I told, once you have these assumptions, this is the assumption. Now, how can you test if that particular data set follows linearity assumption or not, linearity assumptions or not? We have to test, no? So we have an assumption. How can we test it? Over here, what we did, we just did a visual inspection. Okay, this is something which you can draw a straight line. But what if we have higher dimensional of a data? So there are several ways to test your model. Okay, the first test which is very popular is nothing but visual inspection. So in that visual inspection, what you do, the first thing which you do is scatter plots. The first way to test if your data follows linearity assumption or not is apply scatter plots. So what exactly scatter plots does? What does it does? we simply take an independent and or dependent variable. We have to, of course, do it in a 2D plane, of course. So when you have the on y-axis, you have the dependent variable. On x-axis, you have independent variables, and then you plot it. So if the relationship shows the straight line or the linear data, that means it is following. But if it does not, then it is not. Your assumption is not satisfied. So visual inspection is one of the most common ways as well. But over here, the only downside to is if you have a more number of variables, large number of variables, input features, independent features, so you have to plot it against every individual and then see if it works. But it's sometimes not good as well. But eventually it helps you to get a better understanding. But this is scatter plots to eventually help. Okay, so this is one of them. Another one is, which is more common, like over here we have to plot for every individual independent feature x2 and then y, and x3 and then y, and all we have to do for scatter plots. But another example is how can you test with residual plots. So residual plots is one of the most common ways to test those assumptions. What you do, you simply take the residuals and then put it on a y-axis against the predicted or the predicted values or the independent variables. So basically, you on y-axis you have the residuals, on x-axis you have the prediction. Okay, on y-axis you have the residuals, on x-axis you have y-axis with prediction. Residuals, and on the over here prediction. So you might be thinking, here, Ayush, how does it even make sense, right? So let me show you a very nice example of what exactly residual plots looks like, so that it makes perfect sense to you. So I'm just going to take a very nice example. Maybe that will make much more sense. So I'm just drawing out a very nice example so that I can actually send it from Mac to my iPad. That really works, sometimes it works and sometimes it does not. So let me just open up a very nice, open up a Safari. Where is my Safari? So how can I download this? Cool. So I send this on my laptop, from laptop to over here. Now I should be able to show it to you all. So this is the example of a residual plot. This is an example of a residual plot. And what does this plot says? On x-axis you have the temperature, and on y-axis you have the residuals. Now if you see when you plot the predicted values against the residuals, or even a temp, or even the independent variables against the residuals, it should show what it should show. It should show a very random scattered points. So over here, you see they are very randomly scattered. That's not the residual plots. There is on y-axis you have residual, on x-axis you have the independent variable. So this does not forms any sort of a pattern like this. What patterns I'm talking about? For like this or like this or like this. It is not forming. It is a very random one. You cannot even fit any sort of model. It is very, very random, and they're around zero only. They're around zero. Okay. So if the linearity assumption holds, if the linearity assumption satisfies, the residuals are scattered randomly, and they're around zero. Okay, I hope that you are able to understand this pretty well. This is the visual inspection. This is what you do for visual inspection. Another way is something known as partial regression plot. And this is something which you have to explore by your own. I'm not going to teach about that, but you have to explore by your own, because now you're at a stage where you have to explore by your own as well. I cannot spoon feed you everything, but this is one of the way which you should explore right now by yourself. Another way to test it is nothing but something called as statistical tests. So we have seen our hypothesis testing. In that hypothesis testing, we have several tests, which is t-test, f-test. So there are several tests for testing the significance of our coefficients or independent features. So just like that, you have a tests for testing the linearity assumptions. For example, one of the test is nothing but rainbow test. I'm not going to go into mathematical details of it, because this is something you're not studying statistics in detail. If you want to study statistics, just go and search more if you're interested, But I don't suggest you to go in so mathy details of it, because nobody usually asks. You just need to know, okay, there's something test a variable which we have to use for testing this linearity, or maybe something known as Harvey-Kohler test, which is one of the most statistical test, which is often used for testing the other, like how can we eventually talk about things, how can we eventually test if the model is linear or not. Okay, so just you can explore the mathematical details, how do we test exactly, but it just follows the same thing which I've studied. The test assesses, we have a null hypothesis. The null hypothesis states that what does it test? It states that there's the relationship between your x and y is linear. So it assumes that it already assumes. Now we have an alternative which says that it is not. The relationship is not. So what we do, we conduct the test, and once we have the critical the p-value, if the p-value which we get from after conducting the rainbow or these tests, if it's smaller than 0.05, which means that you can reject the null hypothesis. If it is more than, you can reject the null hypothesis, which means the assumption is not satisfied, because we are saying that it is not linear. Okay, so this is the same concept holds for every hypothesis testing. Another example. So these are some of the ways to summarize up. Linear regression assumptions holds for there should be linear significant relationship between two variables. We have scatter plots, then we have residual plots, and then we have partial regression plot and statistical plot, and that we have hypothesis and tests. There's several hypothesis tests available to test whether it follows statistical or not. Okay, I hope that this gives a good sense about our linearity assumption. Now what we'll do, we'll talk about something known as another assumption, which is nothing but called as the remedies of it. This is one of the way to think about. I just forgot, like we have some remedies about how can we fix. So once our assumption, so assume that your assumption is violated. So assume that your assumptions are violated. Now if your model does not satisfy linearity assumption, which means that your model is not going to work well, right? So you might be thinking, okay, you told about that this will not work well. So what we should do if this does not work? So I will say that fix that assumption, make it from non-violated to non-violated assumption. Okay. And this is what you have to do. So there are several remedies for it. Remedies mean something to fix. If it is being violated, we have to fix that as well. #fix. #fix is also a very famous thing. So you have to fix that assumption. So there are several remedies. The first remedies is nothing but called transforming variables. The first remedy is we call transforming of our variables. So over here you can see that we transform our variables. So this is one of the transform our variables. So what does that mean, transformation of our variables? Which means that if the relationship between the predictor and the response appears to be, you can try transforming the predictor or to see. For example, you can take the square root or log or square of a variable. For example, assume that you have a house price square, and then you want to predict based on the size, you want to predict the house price. You have something to 1,000, then you have 200,000. Then 250 to 200 square feet, then you have 250,000. So what you can do, you can apply the log, or the square root. You can apply the log or a square root on variables. Okay, on variables, so that it comes on it becomes linear. You get? So you apply the transformation on the variables. You still study more about feature engineering. So if you want to study more in detail about all of these things, I suggest you take the course which is CS01 BO4, which is one of our famous courses available online. So you can actually talk about this. So we take this log, a square root, or a square of the predictor variables or independent variables out there, so that it works perfectly, so that you bring them back into the linear way. So when I take the log, it of course comes in a linear. So this is a very nice note to make sure. So that's one of the transformation of variables. Another one is add higher order terms. Or interaction terms, which means that if you have your x variable, then you make another variable x, but you square that. Okay, so you add the cubic terms or quadratic to help capture even the non-linear relationship. So eventually this introduces a concept of polynomial regression, and this introduces the concept of polynomial regression, but that's something for later on, where you introduce the higher order of the variables, where you just take the x and then take the x squared, and then you have x2 x1, take the x1 squared. So you just introduce the higher order terms, for example, quadratic or cubic, which helps to capture the nonlinear relationship. Another one is like if nothing is working, then you should start going on to take out the different model. Okay. Different model means you can consider using GAMs or decision trees models like random forest, which can better capture if your data is non-linear too much and not able to satisfy the assumption. Then I think you should go to random forest or somewhere like that to actually cover up our assumptions of random forest and all. Okay. Cool. So I hope that gives you a very nice understanding about a linearity assumption. What the next which we'll talk about is something known as independence assumption, which is also a very nice assumption. And then after that, we'll talk about homoscedasticity and normality assumption. And then we'll wrap up the lecture on this. Hey everyone, welcome to this video. In this video, what exactly I'm going to do is going to talk about independence assumption. This is one of the second most famous assumption available right now, which is independence assumption, which is again, I said, the second most independence assumption, which is like important. So what does independence assumption states? Independence assumption states that, what is it states? It states that the errors or the residuals which you have, the residuals which you have are independent of each other. Okay, so for example, you have x1, and then you have y, and then you have a, b, c, d, and you have y1, y2, y3, y4, and then you have y hat, which you've taken from, which is y hat 1, y hat 2, y. So your error will be error 1 is equals to y hat 1 minus y1, error 2 is equals to y hat 2 minus. So the error number 1 should be independent of error number 2, or error number 2 should be independent of error number 1. Okay, so errors or residuals associated with the data or the observation should be uninfluenced by any other observation out there. So error number 2 should be uninfluenced by any other. So error number 2 should not get affected by the error number 1. Okay, or error number 2 should not get affected by anyone else. So I guess the independence assumption states that the assumptions which it holds that your observations associated with one observation should not influence the error associated with the another observation. Okay, if you don't fix this, you will end up with biased results, inaccurate estimates, unreliable predictions, and a lot of things can happen. So this is what the assumption state, that your error should be independent. So let's take a very nice example. So example states that you have something known as electricity. So you're going to predict the electricity based on the temperature in a city based on the hour. Okay, so we collect the hourly data for an entire month. So you have hourly data, and then you have temperature. Okay, and then you have your electricity demand. Temperature, electricity, and demand. So 1, 2, 3, ... 15, 16, 17, ... and 80, 85, and 90, ... So this is one of our this is one of our data which we have in here, and you want to test whether this assumption holds the independence assumption or not. So if you see that the demand for electricity at 1 hour might be related to the demand of the previous one, right? So basically what is it trying to say you? It's something which is trying to tell you that assume that the electricity demand at hour 2 might be related to the previous hour, right? Might be related to previous hour. Electricity at 3 might be related to the previous hour. Hour number 3 might be related to the previous hour. So you see that there is some sort of relation. And as we said that there should be not any relation. Of course, if this is related, then of course errors will be also related. Okay. So electricity usage tends to show a pattern. So as we are using electricity, it is being so that it is greater than the previous one. That's what it is showing. Okay. It is as the hours increases, your electricity demands also increase. So it is showing some sort of pattern over the course of a day. So it is of course showing the pattern over the course of the day because it is related to each other. So what is it showing? For example, over here, the demand is higher in the day and lower demand at night. or lower demand at night. So this is something which can be showcasing the patterns. So over here, this is showcasing the trends, which is not good, right? This means that our the points are independent, violating the independence assumption, and that's one of our important major issue. So this is what assumption indicates. So how can we test our assumptions? For testing our assumptions, we have a couple of things. Again, we can talk about residual plots. So again, you can take your residuals and plot it, or like this. You take the residuals and plot it on a y-axis, and you take the fitted value, the prediction value, plot it on x-axis, right? And when you plot it, you will see that there is no patterns or trends of the residual. So there is no patterns. There's no certain patterns over here. There's over the line. They are distributed randomly or scatteredly. If there's some sort of patterns like this, like this, so we can say that something does not hold true. But over here, this does not have pattern. But in the case of this, it will hold a particular pattern. When in this particular example, it will hold a pattern. Okay. So this is the visual inspection from which you can see. The another one is nothing but called statistical tests. And statistical test, what does it say is that you have a couple of tests, which is Durbin-Watson test, which will give you some sort of number, and then we say that okay, that number is greater than the significance of 0.005, which is a p-value. Then we say okay, we can reject the null hypothesis and say okay, this is something which is correlates. So we'll talk. These are tests which I've already seen the way we conduct tests and all in the previous lectures. But Durbin-Watson test and Godfrey test. So let's talk about a bit about Durbin, but your stance should be that you are making it researching a bit more about it. Okay. And so how can we? So there is one of them is what we can do. So what exactly the Durbin-Watson test means? The Durbin-Watson is specifically was introduced. Why it was introduced? It was introduced to detect the autocorrelation. It was came on to detect the autocorrelations in the residuals of LR. So what means autocorrelation in the residual? So which directly means, what is autocorrelation? First of all, autocorrelation nothing but the correlation between the residual. Correlation means is there any relationship between both of them? So if they're highly correlated, which means what? They are dependent on each other. So basically it tells you the correlation between two residuals at different time points. So basically it means that it checks whether errors are correlated across observations or not. So if they are, that means they don't satisfy the independence assumption, and if they are not correlated, then that they satisfy the assumption. Okay. So your the Durbin-Watson test which you have, it lies between 0 to 4. And if your Durbin-Watson gives test of value 2, which means that there is no autocorrelation. And if there is no autocorrelation between residuals, that means the assumption satisfies, because there's no values correlated with each other. Okay. So, but if the values are less than 2, that means there is a positive correlations, which means there's a positive correlation. We have already talked about positive and negative correlation. Please see the lectures of probability. If you haven't bought the course, please go and just enroll in a course if you haven't studied about probability statistics. So value less than 2 suggests that the positive correlations are nothing but the positive correlations which you have is nothing but a value less than 2. If your Durbin-Watson test statistics give less than 2, that means they hold a positive correlation, but which means the residuals are positively correlated across observations, but your value is greater than 2 suggests negative correlation, which means that residuals are negatively correlated. So your value should be 2 if they want to satisfy this assumption. If they are less than 2, that means they are positively correlated. If they're greater than 2, then they are negatively correlated across the observations. Okay. So how can we perform some of the steps? So what you do, you first of all fit your data, and then you calculate the residuals. you calculate the residuals. After calculating the residuals, what you do, you take out D. And in t-test, you're taking out the t value. Over here, you can take out the test statistic, which is D. You can search online for the formula, but formula is not even required. There are automatically tools which does for this. Now, once you have this D, now what you do, you compare the test statistic to the critical values for the Durbin-Watson, the table which we have. Okay, the tables or statistical software. You compare it, and if your D is less than that lower critical value or greater than that, then we reject the null hypothesis of no autocorrelation, which means assumptions is likely violated. For example, what does it say? What does it say? That you conduct the test, and then we again our null hypothesis and alternate hypothesis comes into play, and if it's greater than that, and then we reject it, and so this rejection automation will eventually happen. Okay, so but mostly what you do, if your good D statistic gives 2, that means there is no autocorrelation. But however, you can perform test as well for detecting autocorrelation. But one of the more drawbacks of it, the Durbin-Watson test is more for, it's more for time series data. Is more for time series data. Okay, so that's why you have to use proper tests for all of these things. I hope that you understood about how can we test our independence assumption. So there are several remedies for it. So there are several remedies if the assumptions are violated. How can we fix it? So one of the way to fix it is add additional variables. So you can actually add additional variables. You can actually add, the first one is add additional vars, add variables. So for example, if there's any underlying factor which is causing, for example, in this case, which you have taken example that this violates the independent y because it might be related to the previous one. So we can find a factor which is causing, we can try to find a factor which is causing the dependence, and then we can, add this factor as an independent variable. Okay, we can add this factor. So adding more variables definitely helps. For example, in this example, what we can do, we can introduce another variable. We can introduce another variable. What variable? Time of the day. In this case, the time of the day. So you introduce another variable. So time of the day, which is night, morning. So how does it help? This helps. How does it help? If we convert, we can actually take it that we can actually understand the pattern. Your model could understand the pattern. Okay, this is something is daily patterns. Your model should be able to capture the daily patterns. That was the factor. So you can consider adding more variables according to what is causing this factor. So basically at night time. So we can actually explicitly add this to actually help it so that your model does not be dependent. So this is one of them. You can add more variables. We'll do one proper example as well. Don't worry. You can use time series model. For time series model, relatively works well in these type of examples. And then at last, you have nothing but called mixed effect models, but that's something you can use hierarchical linear models, but I suggest you to explore by that alone. It's not too much use, but that's what people actually use sometimes if you have hierarchical data. But I suggest you to learn about hierarchical linear models, HLM. A very nice concept around it. Okay, so adding more variables, time series using another algorithm, all of this really helps. Cool. So I hope that you understood about independence assumption. Now we'll talk about homoscedasticity assumption, which is also known as constant variance across it. So we'll talk about that, where your variance of all the residuals are constant across all the levels. So we'll talk about that constant variance assumption, and then we'll take one example, and after that we'll have our simple last one, which is normality, and then we have no multicollinearity, which is left upon you for you to explore. So let's get started with what homoscedasticity assumption, or you can say constant variance assumption. No, okay, cool. So what does this homoscedasticity assumption states? That I really have a hard time understanding, pronouncing this. So please ignore if I sometimes pronounce it wrong. So homoscedasticity assumption is a statistical assumption that states that the variance of the error term, also known as the spread or what does it mean? The spread of the values. Variance means spread of the values. Okay, how does it spread across the mean? So the mean of it, how does the variance is in a regression model is constant. The residuals or the variance are constant. Okay, they're constant across all the predictor y variables. You may be thinking, yeah, Yush, what the Okay, so what just you told? Okay, so you have you might be confused. What exactly does it mean? So let's talk about what exactly does it mean. So you can assume that it states that your variance. I assume that you know variance, the spread of values of the residuals is constant across all levels. They do not change. Or you can say the spread of your residuals should be approximately same for all values of the independent. So you have X row number 1, you have row number 2, row number 3, row number 4, row number 5. So your error on number, row number, error on so they should be constant across all independent values. Okay, they should be constant. If they are not, if the variance of the residuals increases or decreases dramatically, for example, at row number 1, error is something C, and row number 2 error is C plus 100. That means that increases, and at row number 3 C minus 100, that means it decreases. So it increases or decreases dramatically, which means that it is not following that assumption. That is not constant. The variance is not of constant across the individuals of your samples. Then we say that it is not following our assumption, and that violates the assumption. Okay. So I hope that really helps about that. Again, over here for testing it, we have nothing but called residual plots. Which really helps to test the homoscedasticity assumption. So what is so let me just again, if there's no any patterns, then you can conclude that there's no such assumption. So just going to make you aware about like a very nice example maybe for you, which will be super helpful if you understand it the nice way. So just going to have it over here. The PNG file uploaded right here, share, done, and then I'm going to share again, airdrop, and iPad. Oops, yeah. So this is one of the nice image which I usually use to explain it. So this is called the residual plots. We have the residual plots which you plot on the y-axis residuals. On x-axis we have some sort of fitted values. We have fitted values or the predicted values or the model predicted values. On y-axis you have the on y-axis you have what? On y-axis you have nothing but residuals. On x-axis you have fitted values. And when you plot it, it shows some sort of patterns. Over here you see that it is showing some sort of patterns. Over here it is showing some sort of patterns, but over here it is not showing any sort of patterns, right? So in this example, if your model shows something like this, that means assumption is satisfied, you can go ahead with it. But if there's some sort of showing patterns, that means that assumption does not hold. This is example of a heteroscedasticity, and this is also example of heteroscedasticity, but this is an example of homoscedasticity, which means that homoscedasticity assumption is true, which is constant. Your variance, your errors are constant across the your residuals are constant across the independent variables. Okay, and there's no trends over here. It is increasing, over here it is decreasing, over here it is constant across all variables. Okay, this is a visual inspection. Another one is nothing but called we have several statistical tests, just like as previous one, which is called the Pagan test or white test, and all of this you don't really need to understand what exactly it does. But again, the hypothesis testing formula looks in, you have the null hypothesis alternate, and then you perform the test and then checking the significance value, and then you say, okay, this is something greater than, then we reject or accept. Statistical test, all the statistical tests which you have to understand by your own by searching online. I'm not going to do with it because it is out of the scope of the course as well. It is not required as well for initial steps at least. So once you assume that your model does not satisfy, so what are the remedies? How can we fix it? So fixing can be happen in two or three ways. Okay, so 2 or 3 ways. So let's talk about what are those 2 or 3 ways. The first way is we can transform our variables. Transformation can happen. So you can add, you can apply transformation on dependent on independent, like a log transformation or square root transformation or inverse transformation, and then see if your assumption is being fixed or not. Another one which you can do, which is weighted linear regression. What does weighted linear regression says that instead of using ordinary, which you use right now, you can use weighted, which what it does, it assigns weights to so you have 9 observations, so it assigns the weights to every observation, okay, based on their variance. based on the variance. But weighted linear regression is something which you should learn in the extensions of linear regression, which is upon you to understand in much more great detail. I'm just doing it because I want you to explore by yourself. So not I'm giving you the nobody gives all of these names, but I'm giving you to explore by your own. And another one which you should explore, which is more sort of used to remedy, is something known as Hubbard regression or quantile regression. Regression, quantile regression, or Hubbard regression, and these two are used, for techniques for what it is used for checking whether and this really helps in fixing those assumptions: quantile regression and Hubbard. So I suggest you to explore these three types of extensions of linear regression, which helps to satisfy this assumption. So I really want you to go ahead and then stop this lecture and then go over and search about this, learn about this, make a note, and tag me on LinkedIn. Okay, cool. So I hope that you're done with this homoscedasticity assumption. Now, at last, we'll talk about nothing but called normality assumption, which is our most, as well as, what most. It's something which is required for everyone, Cool. So let's get started with normality assumption. So what is it? Normality assumption states that normality assumption states that the residuals, now previously in independence and the constant and homoscedasticity constant, independence independent of each other, constant, and now we talk about they should be normally distributed. You know that what is normally distributed? What is said to be? Write me in the comment box, what is it said to be a normally distributed? A very nice, so I'll just wait for 5 seconds. What does it means? So tell me, what does it means your residuals to be normally distributed? So let me just write the question so that at least I can check for it and in the comment box. Yeah. So please go ahead and write it so that I could understand. Cool. So what does it say to be a normally distributed? Which means that your mean is that your distribution is following a normal Gaussian distribution. Okay, your mean is following a normal Gaussian distribution, that your residuals are following the normal. When you plot the residuals, they should follow something like this, where most of the values should lie between this range. Okay. This should be symmetrical. This should be symmetrical, and most of the values should be around the mean. Your mean is something that's nothing but mean is equals to 0, and then you have the bell-shaped curve, which is symmetric, which should where the mean should be close to 0 in the case of residuals. So your mean should be close to 0 in the case, because residuals are of course 0, right? Because we don't want our residuals to be high. So it should satisfy our normality assumption. I hope that so basically normality assumption states that, and what does normality assumption states that your normality assumption refers to assumptions that the errors are normally distributed. In other words, that your it should be bell-shaped curve with the symmetrical positions, with most of the errors clustered around the mean and fewer errors. So most of the errors, so when you plot it, so most of the errors should be over here. So it should be constant. So you see that it is related to the previous one. This is constant. So your most of the errors should be constant. It should be independent, and they should be around. They should be similar. It should not be. It should be very one or two errors should be at extreme, like very different. But it should be most of them should be between. Like it should be around the mean. Okay. Over here you can see that if you violate this, it can affect the validity and the conclusions your model is going to make, and it can also often result in biased and inflated standard deviation errors, which can directly affect the accuracy. So there are several ways to test and the easiest way is to plot a distill plot. Is a normal plot, which is nothing but a histogram or something like histogram with a bell-shaped curve, which you usually do. So let me just introduce you with a very nice image for this as well, maybe for you, which will help you. We have two types of plots which we can use. The first one is quantile plots. The second one is histogram plot. So assume that I just want to take a very nice example. Which example I should take? I don't even get it. So I just gonna use this. So assume that you have this particular example where you plot the residuals on a y-axis, where you plot the residuals on a y-axis, and then see, okay, eventually your bell shape should form like this. It should form like a Gaussian distribution. That's one of them. When you plot where you plot the histogram, where you plot the histogram, and then what you do when you plot the histogram with a bell shape curve, and then you apply the distal plot on top of it, so that it looks like a density plot, the density plot, and it should look like a Gaussian distribution. Or what you can do, you can create a quantile plots. What does quantile plot means? It means that, what does quantile means? That it means that if the residuals are normally distributed, should fall approximately along a straight line. Now this may be a bit off, a bit off to you. So let's just go ahead and talk about it. So what I'm going to do is have it like over here, quantile plots. I'm just going to send it out to you over here. Usually, what I do, I usually teach along with it. I just don't like, to teach it like just having a preparation, because I feel like having a preparation really affects, the way we teach. So of course I have a preparation, but not too much, because I like to be very natural. So over here you can see that you have a QQ plot, and QQ plot, so what does QQ plot indicates? The QQ plot says that if your distribution are if your residuals are normally distributed, then the points on the point that should lie approximately, which is saying that approximately, if they, over here this normal distribution, there lies approximately on the straight line, but over here this is not a normal distribution, log normal distribution. So your points are diverged. The points are not on the straight line over here. This is also not on a straight line, but over here, this is on a straight line. So if you get the quantile plot like this, then you say, okay, this satisfies our assumption. And then you have several other statistical tests, just like previous one, like, which is over here we have Shapiro-Wilk test, or you can say Smirnov test, where it is used. But we'll perform the test, one of the tests in practical. But that something is according to you if you want to do it. But I like to do it by normality assumption, which is just by visual inspection. What are the remedies for it? Transformation is one of the most popular remedies. Removing the variables which is causing to be it non-normal. So you can remove the variables which is causing to be non-normal, or you can talk about, or you can use different other algorithms such as quantile regression. As I told, that you should be comfortable with that. And actually in the course, the course which we have CSO1, we teach about all of these extension as well. But as of now, I feel like as we made it for free, we just want you to explore by your own as well. Okay. So this is about normality assumption, where we ask our residuals to follow a normal distributed plot. Okay, cool. So I hope that really makes sense. Now what I'll do, I'll just wrap up. So now we are done with almost all the assumptions. Now what is left is something known as no multicollinearity assumption, which is for you as a homework to understand. It's very easy and very, very tricky as well if you don't understand the right way. So, but that's something which you have to deal by yourself. We have already talked about 10 hours of lecture. That's something which you have to do by your own as well, right? And we have a talk in very things in great detail. And I really hope that you understand all of these things. We have came to an end actually. So we are done with the assumptions and everything. Now what's next? The next is nothing, but we'll go and do a sample project. One simple linear regression and one multiple linear regression to showcase you several other things as well. So you don't need to worry about a lot of things. So let's get started with the final section of the course, and then we'll say goodbye. Hey everyone, welcome to mostly the last section I've been telling in the practical session. So we'll now start off with the practicality stuff, get you comfortable with what we have learned and how to implement that as well. Okay, so we'll definitely do that. But prior to this, you have a programming assignment for you, so that you could implement linear regression from very scratch by your own. I'm not going to do that. What I'm going to do, I'm going to utilize libraries, teach you the core and concepts and crux, which nobody else teaches. That's my aim. So we'll be doing a couple of linear regression projects. One of them is using simple linear regression to give you a basic idea about how we go about building a very nice report, how we go about interpreting the results of linear regression, and etc. And as my strategy suggests, we'll start off with a baseline, and then we will slowly extend to the multiple variables as well, right? So what we can do, we can actually do that in terms of having more sort of, adding more sort of projects in future if you want to go with the free one. But as of now, let's get started with the very simple example on how we can use linear regression for identifying advertising prediction. But before that, I'm pretty much sure that you might be confused about what exactly the project is and how we're going to go forward with it. So basically, let me show you what exactly the project. I'm going to start off with the problem statement. And then after the problem statement, I'm going to make you familiar with something known as, with something known as like what simple and linear regression, and then we'll do a couple of stuffs like for example data ingestion, and then we'll talk about how do you build the model, how do you test the assumptions, and etc. So I hope that really makes sense apart from it. And on the other hand, let's get started eventually talking about, first of all, what exactly the data is. So first of all, we have the advertising data set, as we have already seen a lot. And you'll also see the programming assignment, which you'll be doing. Please see the course website where we have listed for the same. So over here, you have three variables. You have three variables, which is TV, radio, and newspaper. And these are listed expenses which a particular company has put on. For example, they have spent around 230.1 on expense on TV, advertising on TV, $37,800 on radio, and $69.2 on newspaper advertising. And based on the advertising, they got 22.1 this much sales. Okay, so basically we had, this is over here, we have the expenses which every company has did on TV, radio, and newspaper, and we are going to predict what is the significant number of sales. So now your task as a data scientist is to identify which mode of advertising is much more liable for, which a company should increase the expense to get the sales, and which one source we should completely vanish it, like we should completely ignore it. For example, in some cases, okay, you might say, okay, for this particular example, you might gonna go with TV because it is more significant in getting more sales as compared to newspaper or radio, right? So that's what your work should be as a data scientist, is help the stakeholders to take better decisions out there, right? So what decisions they have to take? They have to take the decisions about like whether to use TV, whether to spend more on TV, radio, or newspaper, or a couple of them. So we have to identify which independent variable is giving most amount of contribution to sales, which particular medium of source is giving most amount of information to the sales. And that's our problem statement. So what I'll do, for being it super simplistic, as I told, it's not a full-fledged project. Project is just for the learning purposes, not for the putting on a portfolio. So basically, over here, what exactly I want to do, I want to take this TV and I want to take one of the advertising source and understand its impact on the output variable sales. For example, I could take TV and then understand its impact on sales. So I can build a linear regression on top of it, where given the TV, the expense curve given on TV, it will predict me the sales, so that I can identify, okay, this much, and then I can do for separate variables, and then I can do for separate variables, and then see which is having the most amount of contribution. However, this is not we do it. We actually use the multiple linear regression, where we'll use the three of them to actually predict the sales. But that's for you to try out, not for me. As a programming assignment, we have listed detailed programming assignment for you, where we'll do a small thing and then you have to extend it to further. Okay, so over here, what we'll be doing, we'll be making the data into a simple linear regression, which is a simple PDF, where you take the only one column as of now, so that you have X1, we have only one independent feature and then one dependent feature. And over here, we're going to identify the significance of TV onto the sales. the significance of TV onto the sales. However, you can also include other variables if you want to understand the significance. But as of now, let's get started with it. You'll be also doing a very nice programming assignment where we'll be actually answering that question of which one to go forward with. Which one of the medium source to go forward with. So let's get started with actually talking about the how can you code in a complete data. So here we went back to this lecture, to this project. So I'm going to start off with the data ingestion. So the first step of any machine learning project is to ingest the data. And I'd really like it to be in sort of class and everything. So basically over here, we have a class, and we have a data ingestion class which ingests the data advertising and then lowers it down to only one to a simple to a data set where we can use simple linear regression on, where we have only one independent feature and one dependent feature. So the first step is to initialize the class with a file path. So we require a file path when someone instantiates this class, and then what we do, and then we have a method called load data which reads the CSV from the specified file path. And then we get our specified, as I said, that we want a specific TV and sales only, so that it is for learning purposes. And then we concatenate both of the X and Y variables, and then we return that data frame. Okay, so this is a basic data ingestion class, not a big deal to understand it. Okay, now we can actually use this. Over here, which is where we are importing. So ignore everything, just go over here. You can say from source, which is the source folder, dot data ingest with the file name, import the data ingestion class, and then you say, okay, this instantiate a class, and then source it to make it to the advertising.csv, and that gives your simple df. That will give you the data frame, which is a simple df which we want to perform on. Okay, now data ingestion is done. So let's run our file to actually see. Okay, that will make much more sense. And I'm going to use something like very nice over here. So I'm just so clear ls, and then I'm just going to have this. I have actually an environment protection, so I'll just environment variable. So what was the name? LR crotch, maybe, I'm not sure. Yeah. So Honda deactivate ls clear. Okay, so I have activated my environment. If you don't know how to activate, you will be also seeing the reading materials for that, or otherwise in the next set of projects I have showed you how to do this. Okay, so I just want to remove this because it's not required. Yes. Over here now, what we will do is we will simply run this python main.py, and I just want to run that. Just going to make it comment, and I just want to take a look at what exactly the data frame looks like. So I'm just going to print that data frame, data frame, so that it may seems good to you, so that you can see what exactly it's working on. So when you run it, you'll be eventually getting a data frame where you have only one column, which is an X, and an Y over there. Okay, so it eventually takes time initially, and then it works fine. So you have the TV, which is the expenses on TV, and then the sales, which happen if you had advertised on TV. So that's our data ingestion is done. Now the next step is I'm going to do a basic data processing. Please note that in the next project which we'll do, we'll have the very extensive data processing thing. But as of now, I would suggest you can ignore this as of now. Okay, maybe it just for information purposes. If you want to know how we are performing, basically what we're doing, we are importing a class known as data processing class, and in that we are instantiating with the data frame object. Sorry, which takes an input, which is data frame, and then performs a couple of methods. The first method it applies, it identifies if there's any outlier. We box plot and see if there's any outlier in that particular TV's variable, because linear regression it's sensitive to outliers. So we have the TV, and then we just see if there's any outliers. If there's any, we identify who are those outliers numerically. Okay, and there are several ways to deal with it: capping, trimming, and several ways to identify as well, which we'll be seeing in the next lecture. Please ignore that as of now. So when you go to main.py, now you can just import the same thing. We can import the same thing, which is the data processing from that data source folder in the data preprocess file, and then you simply run it. So when we run it, it says, okay, let's identify if there's any outlier. So it says that there's no any outlier. So let's print it out. Let's print out. Oops, I haven't printed out. So outliers. So if I just print it out, you will be able to see that there's 0 outliers in that particular column. Okay, of using z-score, but you'll identify a method to actually identify which are outliers. And I would recommend to, if you don't know about outliers, you should wait for the next lecture. As of now, you can ignore this. This is not the scope of this project. The scope of this project is focused on model building only. So now once we have the bit of processing left, I just want to show you the process, nothing else. Like, okay, after data ingestion, we process the data in a good way. And then what we do, we go on how can we build a linear regression model. So how can we build that? So we'll be using a stats model API because I really like that as compared to the scikit-learn, because I don't know why, but yeah, it is more interpretable. It gives more results. It gives more explanations when we after building up the model. Okay. So basically, we'll build a class which takes in x and y, which is the independent and dependent variable, and then what we do, we add a constant, which is 1 1 1 terms. In x is a design matrix, and then 1 1 1 1 1 a column of 1, so that we multiply with beta 0 and 1, which is sm.add constant. We have sm as an alias for this library, and then what we do, and then we make a method called fit. And that fit, what it does, we are calling ordinary least squares, which is equivalent to linear regression, and then we're calling dot fit. And when we're calling dot fit by giving your dependent variable, independent variable, where we were saying, okay, this is something is a independent, and this something is independent. So model the relationship using linear regression first. What this fit will do, it will perform all the steps. First step, hypothesis. Second, calculate the cost. Third is perform the gradient descent on top of it unless your model is converged. We have already talked about what exactly fit method does. It fits the method. For example, we have already seen what the algorithm is. Take out the hypothesis, take out the error, take out the derivative, and then perform the gradient descent n number of times just after updating beta's value. So that's what fit does. Okay, fit means it trains your linear regression model by the number of iterations. So when you actually go and see what exactly sm.ols is, you will be seeing all this stuff. But basically, it trains your using gradient descent algorithm. Cool, and then return the model. And then we can print the summary of our model. What exactly, after training our model, what exactly the summary of our model looks like? And if you're getting confused what this dot fit method does, please take a look at online for a scratch implementation of linear regression if you're still not sure about how to be programming it up. But you have to attempt a programming assignment for this for better understanding. You print the summary of the linear regression model, which is model is equals to self.fit. First of all, you train the model, and after self.fit, you train the model, and then print the summary of the model and return the trained model so that anyone can use it for prediction. So over here, when you actually use that, so let's have a basic simple linear regression model over here, and let's print it out. Let's print that stuff out, the model summary. So basically, we're just calling dot summary. We are just calling dot summary. And when you're calling dot summary, it first of all trains the model, prints out the summary, and then return the model. So how does that summary looks like? Which is the most important part of this lecture. Is we have this OLS regression results, which is telling, okay, this is the dependent variable, what model we are using, and a lot of things. We should talk about that in just a second, about how we can interpret the OLS results regression. And then once we have our OLS results, now we have a model trained with a full report of how it is performing, how our model is performing, how they're performing in different tests, and etc. So this is something which we'll talk about. Okay, each and every integrated, what exactly this report says, and everything in greater detail. So let's talk about how can we interpret each of them in a nice way. So I would suggest if you go to interpret.md, so when you go to interpret.md, you have pretty much everything listed out there. So I'm just going to focus on important explanation of which is required for you as of now, and which is in the scope of the course, like confidence intervals, which we haven't had a talk. So I'm not going to talk about that, but we're going to talk about most of the things which is listed out, which is also very, very important. Cool. So let's talk about that. So first of all, let's assess the results. So now we have trained a model that can take in the TV expenses and then predict, and that can predict what will be the possibly the number of sales which you're going to get. So what you can do, you can simply go over here and then say, okay, and then say when model.predict, you given the value of TV sales, and then that will give you given the value of TV sales, and that will yield you to the particular variable, which is the TV expenses, and that will give you the sales. Okay, so this is what you're going to model or predict, but that's something for, I just like, you can easily do that. I assume that because that's something which I will also explore by your own. Okay, cool. So over here you have the first one is dependent variable, and dependent variable is a dependent variable in the model, where in this case it's the sales, and predict the sales given the TV expenses. Second one is R squared. As you know, we had a talk on R squared, right? In great detail, how do we evaluate our linear regression model? So over here, our R squared, which is nothing but 0.812, which means that 81.2 variations of the sales is explained in our TV. That means that is pretty nice, which is 81% of variations in the sales, whatever the variations comes in the sales, is being described by your TV expenses. And that's pretty much good. So higher R squared indicates the model is better fit to the data, where lower is not good. Okay. But it also depends on problem to problem, so you might have to worry about that as well. But basically over here it explains pretty well. What is adjusted R squared? Adjusted R squared in this case is almost the same, which is 0.811. And what exactly adjusted R squared is? It's nothing but a modified version of your R squared. So what is modified version of R squared? For example, it is a measure of a goodness of fit for the linear regression model that adjusts for the number of predicts. Now you might be confused in this. So let's consider a very, very simple example. Consider that linear regression model that predicts the sales of a product for the amount of money spent on advertising. Okay, so R squared will give us an idea about how well the model fits on the data, how well your sales is being described by your independent variable. Okay. Now let's say that you add an additional independent variable, such as how much your company spent on radio spending. Okay, so the R squared value will increase if the radio, for example, R squared which we have will increase if the radio spending improves the model. Okay, like if the radio spending improves the model, R squared will also increase, right? So basically it will increase even if one of the predictor is not improving the model. Okay, so you put another variable X, and then if it is not improving but a radio is improving, then it increases. So R squared might not be significant if you have lots of independent variables. Okay, lots of independent variables. So adjusted R squared is pretty much same because we have only one variable, and they are almost same because over here we have only one to check to check how much they're explaining to the output variable Y. But for example, if you introduce to one of the variables like radio, newspaper, then you will see a massive difference because if you have a large number of, even if one of them is improving the model, your R squared will increase. But R squared just increase the R, but adjust R squared. What does it do? It only increases R squared if and only if your overall model is improving. Okay, so that is adjusted R squared. You can take a look if you want to know more about it. Another one is method. What method which you're using? Least squares method, where we are using gradient descent, almost same, but a little bit of difference and all. But we are using gradient descent algorithm to optimize it. And then we have something known as F statistic. So F statistic, which we have already talked about in hypothesis testing, and F statistic, which tests the overall significance of the regression model. In this case, the F statistic is this much, which tests how much your regression model is good. So basically, over here, which you see the F statistic, which tests overall significance of a particular model, and if you convert that to a probability of F statistic, which is around 7.93-74, which means the model is highly significant. How can we say that the model is highly significant? So you might be thinking, hey, 7.934 is values very, very small, like very, very large. right? But it's not actually. If you know maths, then you'll be able to understand this, that actually a very, very small number. Okay, so what we'll do, we'll compare that value, the probability of Swift statistic, will compare that value against our p value, and then we can see, and then we can see over here, and then what in the p value we can test. Okay, in this case, so we can have a null hypothesis that the model coefficients are equal to 0. Okay, a low p value indicates that the evidence again, so we can, a p value, which is the p value, p value lower than 0.05, which, so that will, if it is, then we'll reject it. So over here it's actually lower than 0.05, then we'll say, okay, let's reject our null hypothesis. The null hypothesis was that all our betas are equals to 0. So that is not, so we can say that it's very zero, that model is highly significant to our so your DV is highly significant in predicting that. But this F statistic can be for several other values as well. It tells the overall sense. So if you also see the highly significant, then if you use 3 of the variables like radio, newspaper, and the TV, then if it's highly significant, you say, okay, 3 of the variables are very highly significant as well in predicting the sales. Okay. Number of observations, there are 200 observations as of now. As I said, there's degrees of freedoms. So degrees of freedoms in this case is 198, because you have 200 number of rows, and then you simply have number of rows, number of data points minus the number of parameters. In this case, only beta 1 and beta 0. Beta 1 is related to TV, and beta 0 is the constant term, is the bias term. So what exactly degrees of freedom is? So what exactly this does is represents the number of independent values in your data set. Number of independent values. Okay, this actually helps in calculation. This actually helps in calculation of T statistic or F statistic and a lot of other way. But this is what the DF residual says. It's saying their DF residuals is nothing but your 198. Okay, so covariance type. So what is covariance type? Covariance type over here is nothing but non-robust. We'll talk about that. What does that mean? What does it mean? But the covariance type is the type of the covariance used to compute the standard errors of the coefficients. Again, the blah blah blah. It's very difficult to understand, but I'll explain in a nice way so that you understand it. So over here, what is it telling? That your standard errors. First of all, what is standard errors? We have all talked about how efficient or accurate or how reliable our coefficients are. For example, a very nice example which we'll list over here. Say you want to predict the mean height of all adult males in the United States of America. We can take a sample of adult males and calculate the mean height of the sample. So from the sample, we calculate the mean height. So how much? So we say that because the sample is only a small portion of the whole US population, so the mean height of the sample will not directly match the population sample. That's true, right? That's true. Right? This is mean height will of course not match. So the standard error, what does it tells? It tells the measure of the variability of the height of the sample, which provides it provides an estimate of the uncertainty. So how much we are sure about how much our sample mean is accurate, how much the sample mean is accurate accordance to the population mean. So smaller the standard error is, more precise the estimate for your population estimate. So you based on sample mean, you're predicting the population mean, which means that we're using there is some sort of standard errors which tells that, okay, how much precise we are in getting the population mean given we have the sample mean. And in this case, covariance type is non-robust, which means we calculate the covariance of our matrix without any elimination of the data. So what exactly does this tells? What exactly does this tell? So I'm just going to go over here and then tell you about that. So over here, if you read this out, is typically non-robust, where there is no elimination of the data to calculate covariance between two features. But what exactly covariance is? Covariance is a nothing but it tells you the relationships between two random variables. So for example, you have two stocks, which is S&P 500 and ABC Corporation. You want to assess the directional relation. What is directional relationship? So if SP is increasing, what is happening to ABC Corporation? So what is the covariance between SP and ABC? So it tells either one is increasing or one is decreasing. So basically, this is a data is an example, and it's X random variable and it's Y random variable. So over here, both are increasing. That means they have a positive covariance. This one, it tells you the direction of the relationship, not like if one is increasing, then what is happening to another. So if both of the stock decreases, then we have certain things. So that's what the covariance is. It tells you the relational, it tells you the relationships between two random variables. Okay. Cool. So I hope, let me just ensure that, yeah, it's running. Cool. So covariance shows two variables between how they move with respect to each other and blah, blah, blah. It just tells you about everything over here. Okay. No, that's non-robust, which means we don't eliminate any data. Okay, which is most common way. Coefficient. So coefficient is nothing but for constant, which is the bias term, which is beta 0 is 6.978, which is the average when x is equals to 0, and TV is 0.055. And constant for the standard error for the constant is 0.323, which is how reliable our constant or how accurate or precise our estimate is for bias term, and how good our estimate for TV, which is pretty much very low for both of them. And then you calculate the t statistic, which we had a talk, which is t statistic, which is okay, t statistic for constant, like how, because t statistic, what is it? It tells you the significance of the individual parameters. It tells you for individual parameters. Okay, so which is calculated by dividing the coefficient by the standard error of that coefficient. So basically that's the t statistic. Now what you do, you compare that t statistic. So this basically you have the p-value. You have the p-value for each coefficient, which measures now if and you can see that both of the p-values are close to 0, which means that they are pretty nice. They are less than 0.05, and they're both significant to the model. Okay. We have omnibus test, which tests. So now over here we are done with a couple of things, which is the testing significance of a model. Now what we do, we have the omnibus test. What exactly omnibus test does? It tells us that we have an assumption, which is normality assumption in a linear regression, which tests whether our residuals are normally distributed or not. So omnibus test statistic gives you exactly helps to validate the assumption. That's why I really like stats model API, because it tells you everything which you need. You don't need to calculate further on. So omnibus test statistic, which gives you 0.013, and the probability which gives the p-value, which is 0.993, which suggests that residuals are normally distributed. How can we say that they are normally distributed? So over here, which you can see, the probability value, the probability of omnibus value is the p-value associated with the test statistic which was calculated. Okay, so t statistic, t statistic which we calculate, and other things. So over here, the probability omnibus is if your value, the probability of omnibus value test is close to 1, that means are likely normally distributed, and if they are less than that, if they are less than 0.05, which means they're not normally distributed, right? So over here it is 0.993, which means they're close to 1, that means they're normally distributed. Another one is Durbin-Watson test, which was used for testing the independence of residuals, whether one error does not affect the another, which we had a talk. So it usually ranges between 0 to 4, and the value indicating 2, which means they follow the assumption, but less than they are positive, and greater than 2 they are negative correlation, right? So in this case, your Durbin-Watson test is around 2, which means that they also follow the independence assumption. Now we don't need to check for too much, and then value close to 2, as you can see that you can read over here. And then we have another test, which is again for normality assumption, which is Jark-Bera test. There is a lot of pronunciation for the same, like Hark-Bera, Jark-Bera. So it depends on what you use. So you have another test. You don't need to understand how exactly the mathematical working works setting. It's just for statistics purposes. So which tests the assumptions of a normality of the residuals. In this case, your beta statistic. As you know, first you have a t-value and then the critical value, right? So first of all, calculate the beta statistic, which is this much, and then you calculate the probability of that, which is from the table distribution, which is 0.979, which says that residuals are normally distributed. What is the probability? Which is so that we have the probability, so that we can compare with the significance, right? Alpha value. Otherwise, how can you compare this? This is not a probability. Convert that to a probability. So we suggest that the residuals are normally distributed. How can we say that? You can read that. How can we say that? We have actually written you everything which is over here. that also test suggests. Now we have skewness. Skewness means so how can I explain skewness? Skewness is a statistical, I think that you have to enroll in my course for learning about all of these things. But basically skewness means that skewness also suggests some normality assumption. Okay, so basically it also helps to calculate our normality. So over here in this case is minus 0.08, which means residuals are close to being normally distributed. I suggest you to have a look in detail about skewness and kurtosis, because this is something which you have to, and the both indicates the validates our normality assumption over there. But I suggest you to explore by your own, because this is something it takes a long time to explain. That I explain in my probability course. Cool. And this is the condition number. This is not important. You can actually ignore. But actually, condition number, if you wanna know about so you have a condition number over here. Condition number, what does it state? It represents the sensitivity of the predictions, of the model predictions, to small changes in the value of independent variables. So how much your model prediction will change if you change the training data and then retrain the model. Okay, so if you change the training data a little bit, and then how much that will change. So higher the condition number is, better. A small condition number indicates that the model is relatively insensitive to changes, which suggests are relatively stable. Okay, so they are not sensitive. So basically, smaller condition number, which means that even if you change the data, your predictions will remain stable. It will not drastically change. It will not drastically change. So I hope that really helps. That really helps. Now, I hope that this provides a very nice explanation about our condition number and the summary of everything. Now, what you can do, now we are done with this interpretation. Now you can actually go to something known as by your own, which is explanation. And explanation consists of everything which we had talked on a lecture. Like I had over here, I given what exactly the report is, what is the small summary of the model. Over here, I've interpreted every the important tests and everything. I've also validated the assumptions. If you can also go on images and then see figure 1, figure 2, figure 3 and all, which will give you a very nice for every assumption by your own. Okay, if you want, you can actually tell me in a comment box if you want me to develop for it. But you can see that I have written a very nice blog for this, so that you don't need to worry about too much. And also just what are the further improvements or limitations which can be listed out there for you to work on. And that's pretty much it about this project. I'll be catching up in the next project. Till then, bye-bye.
Hey everyone, welcome back to another lecture and section where we are going to eventually talk about one of the last projects for the midterm. So on regressions, on regression part, and then we'll move on to classification projects. So basically what this project indicates, this project says that in this we'll try to predict cancer mortality rates for the US countries. Right. So what exactly the problem statement is, etc. So here's the walkthrough of the project, which we'll go through it. First, we'll start off with the introduction, which is this lecture. So we'll start off with the introduction lecture and then give you some motivation to start with it. And then we'll go through what are some of the required installations, and what is the virtual environment, setting up the virtual environment, setting up your workspace, etc. And then we'll go forward in understanding exploratory data analysis. So in exploratory data analysis, we'll try to do some basics ED of the data set, and we'll try to understand more about the data. And then after that, we'll go through preparation of the data. What is preparation of the data means, which means cleaning up and then feature engineering, etc. And then we'll model our work where we'll implement our linear regression model to predict what is the death rate for that particular country, for the different states. I hope that makes sense now. Now, what I'll do is make you go through all the first part of this project walkthrough is introduction section, where let's talk about what exactly we are going to solve in today's lectures. So basically you can go to the given link, so OLS regression challenge. So you'll be having the link in the readme of your project.
And so if you go over there, so basically this is a challenge listed by data.world, which is one of the good challenges which I've ever seen. And basically this challenge says that you want to predict that your task is to build a model to predict what is the rate of cancer mortality, what is the rate of the person dying with the cancer for US countries. Okay. So if you go and see the data, so the data dictionary, where you have several independent features and then you have one dependent features. So what is let's talk a bit about on this is you have the data dictionary. Let me show you first of all the data. The data which you'll have is over here. This is the data which is in CSV file. Okay, so you have a total of 3047 rows and 34 columns, in which there is one column which is a target variable. So let's talk about which is the column which is target variable, which is target death rate. The target is the death rate, which is a dependent variable. It says that mean per capita, which is what is the death rate in per capita, which is 100,000 cancer mortalities. And then you have again the same thing, average mean number of reported cases of cancer diagnosed annually. So you have these features, which is average count. So if you go down, you see average count, and then you have average deaths per year, which is mean number of reported mortalities due to the cancer, average death per year. Then you talk about incident rate, mean per capita, and then median income per country. Then you have population of that country, percent of population country. So you have the features out here. And every feature has its own description listed out here. So I suggest, without doing anything, go through understand every feature and try to first of all understand what exactly each feature is trying to tell you. Okay, so basically the years of data it contains is from 2010 to 2016, and between that you have several number of information out there, right? For example, you can just go and see some birth rate, which is the number of live births relative to number of women in a country, which is the percent of married households, percent of country resident who identify in a category which is not white. So basically these are the information for a particular observations. Okay, so let's go with that example. So first example is where your average GNN count is this much, and then you have a death rate where given all of this information, you have to predict this particular information, which is the death rate. So where is the death rate? Yes. So you have to predict this target variable. So this particular is the target variable where you have to predict this given all the information out there, given all the independent features. So these are independent features, and you have one which is a dependent feature. I hope that makes sense now. So what exactly we will do, let's go to this now. Given the data, so basically we need to predict the rates, so cancer mortality rates for the US based countries out there, right? Which is nothing but how many people died. We have to predict the death rate death rate which will happen using cancer, okay, with the cancer diseases. So the task is to build a multivariate, which is multiple linear regression model to predict the death rate for the US countries. Right. So what should be the deliverables when you will complete this task? What should be your following deliverables? Like what you're going to deliver to the taskmaster, whoever is checking your assignment. Is first is your should be model equation where you should have a model. You should have a statistical software where you're telling about R square, mean squared, your code file, and the model diagnostics. Whether your model follows the linearity assumption, independence assumption, etc. And then your interpretation of the model, and there are other factors to also consider in this. Okay, so I hope that this will tell you a lot, and now I hope that this gives you a good sense about what exactly we have to do. Now you may be thinking we'll be covering each and every part. As you might have already noticed that we have covered this part, which is assessing which is model assumption test, as well as the evaluation part. So these two things are in your assignment. However, we'll do the big chunk of portion of this project to help you better understand mainly the data processing steps and all. So I hope that this gives you a good sense about what exactly we are going to do. So as I told, our aim, we have given you the short introduction about the problem statement. Problem statement is nothing. We have to predict the death rate per me, which is the
death rate and what is the which happened with cancer mortalities. Okay, now you might have some issues like understanding variables. So here's you have to do if you're having a very hard time in understanding cancer whatever the independent features, then I suggest you to search that particular term online on Google, and then you'll be automatically understanding what exactly you need to do, right? But as of now, you have to predict what will the death rate in that particular country given that sort of information. So basically, if you go out here, you will see a geography. In that geography, you have the geography as well as for that particular place and for that particular year, you have all the information available. I hope that this gives you a good sense what exactly the problem statement is. Now in the next set of lectures, what I'll try to achieve is I'll start off with a very basic introduction of what is the required installations which you need to do, what is environment variables. So we'll start off with a basic introduction to environment variables, and then we'll move forward accordingly. Hello everybody. Now we'll talk about one of the theoretical concept today is a bit about on programming basis, but this should already be covered in your Python. But if you don't know, I widely use this virtual environment in this project. So if you don't know about virtual environment at all, this lecture is for you maybe, but if you don't know completely Python, this lecture is not for you. Please complete your Python stuff. Like in Python, you're taught all these things. So please make sure that you have some idea what exactly these things are. But even if you don't, if you have basics of stuff done, then you will be able to solve things up. Cool. So let's get started. Actually, what our agenda today to talk about a virtual environment variables in Python. Our agenda is to talk about this, especially in this particular lecture. And first of all, let's talk about what exactly they are. Right. So virtual environment is an isolated working copy of your Python version that allows you to install any sort of packages or dependencies which you have for a particular project. So I know it's something which is a very big definition. Let's say one thing. You're working on project number A. You're working on project number A, and also you're working on project number B. You have Python installed, right? And then in that Python you have several libraries installed, such as NumPy installed, pandas installed, matplotlib installed, blah blah blah. So in that Python version you have several dependencies and packages are also installed, right? And now you have this packages and all. So your project A also downloads in your base version. In project A, you download your whatever. First of all, download your packages required for project A from these and every library has its own version, right? They have the V1, V2, V3, etc. And project B might also have some sort of similar libraries or different packages installed. Okay, but you may be thinking, but over here, project A is utilizing. It might happen that project A might have different versions requirement, and project B might have different versions requirement. Right, that's one of the way to think about that. If your project A runs on NumPy 1.0, then if project B works on NumPy 2.0, then that's an issue, right? You cannot run project B on that first library, right? On the other hand, you might be having questions like you might be thinking, how can we solve this? There's one way to solve this is that we can have every project separately. So we can have a project number A. We can have a project number A with its own Python version, with its own libraries versions, with its own dependencies. Right. So for example, NumPy can be dependent on several other packages to work, right? So pandas can be dependent upon NumPy, matplotlib, right? So a single library can be dependent upon several other packages. So one way to think about why do we need, first of all, what is first of all, the problem which arises that a particular project number A might have different requirements of your Python version. They require 3.8, but project B requires 3.9, and they might require several other set of versions of your libraries, and maybe there might be different dependencies. So for example, NumPy can be dependent on pandas and matplotlib, but pandas may not be dependent on matplotlib, right? So this is dependency conflicts which may can happen, and etc. So what is the ideal solution? We can have a container. We can have a container sort of thing. Or the variable sort of thing, or an environment sort of thing for every project. So we have two projects. So project number A. So we create an environment for that particular project number A, and in that project number A, you might install your own Python version. You might also install your own libraries. So now you can run that project A using this and whatever versions you have, and then you make this another environment for project number B, and in that project B you can have different versions. So you can have NumPy 1.2, NumPy 1.3, and then you can activate this environment if you're running this particular project. You can have project C with different versions of your libraries or Python and all, right? And then if you want to run project number 3, you can activate this environment. If you have project number D, then you can have several other versions, and then you can activate. If you want to run this project, then you can activate this particular environment. Okay, so this is one of the way to think about it, right? So basically, you can have a different versions of a packages and different for the different projects for the different environments. And it will, and we can create this, and this will not affect anything on a global means where you have global means which is setting over here. In that global, you have certain packages installed, Python installed on your path environment, but in that global one you have several other virtual environments available, right? There are different tools that use to create these sort of environments. One of them is Venv, another one is Conda, another one is Venv, another one is Conda, another one is let's say for the sake of an example, PyEnv. So we have these three where you can simply create your virtual environments out of these tools, right? So let's talk about a bit of reasons why exactly we need a virtual environment in our daily life, as this is something which is super important. So there are several reasons which we might use for virtual environment. The first one is package management. So this is the first one, which is in package management. You can install your packages. You can install and manage your packages or libraries for particular projects. You don't need to install in such a way that it should be applicable on every project. It can be for a particular project, and this like you manage your project. You have a project, and then you have several other dependencies. So you have to you can package this without affecting the project number 2 on which you're working. So you might have noticed in my previous projects, I always create a virtual environment so that it does not affect my other projects dependencies, right? Another way is we isolate our projects, which is another one is isolation. Another one is isolation. Isolation means that if you have lots of environments, you have lots of virtual environments for project number A, project number B, project number C. So you can have these virtual environments. So changes in the project number A does not affect the changes in project number 2. Even if they have a same library, because they have all installed separately. They have all are installed separately by creating a folders. So everyone has their own folders, and in that they have their own packages. So every environment has their own different versions, or it may be same as well, but one does not affect others. So in COVID-19 we used to isolate people. So in just way over here as well we isolate guys. Okay, now you might have another one is, another one is reproducibility. Reproducibility. Okay, so this is another reason of reproducibility, which means that, let's take an example. You run a particular project number A, and that there has own requirements, should have numpy, should have pandas in that project, should have cbond, should have this particular requirements, all the technical requirements, right? So when you package this up, you can exactly set up in such a way that it will work on other systems as well. You can also deploy to production. So whatever you change it over here, changes in production as well. So you can actually have a very good reproducible pipelines out here. And I hope that this gives you a good sense about what exactly you should be able to. But reproducibility is nothing but sharing of your project to others or deploying your project to a production. That's why, because it may happen that you have a global, let's say for example, you have a global environment, and in that you have hosted project number A. So even if a single dependency error occurs, the system which is running for users in production will fail, right? So you have the separately, so that your model is so production is contained in a single container or an environment. I hope that this gives you a good sense about what exactly we wanted to talk on, packages and all. Now what we'll do, we'll try to get into a bit of coding part. So now we have completed a bit of theory which was needed before it. Now what we'll do, we'll try to install our packages now, and then we'll get started with basics of exploratory data analysis and try to understand from there. Hey everyone, welcome to this another video on what you're going to do. We're going to set up our project and make sure that you're also following. You have the downloaded materials and all, so you're also following throughout the course. So what I'll do today is make you a bit comfortable with a bit of setting up the environments, installing required libraries, getting you through the notebooks which we have, getting you through the important stuffs out there. Right, so let's start with that. First of all, I want to show you one thing, which is a documentation of Python where it says that we'll be using Ven to actually create the environment variable out here. So so now if you want to create the virtual environment, so if you really want to create the virtual environment, then what we can do, we can simply have maybe this one, which is Python mvenv, which says that. So basically, I have opened my, when you unzip your file, you will be having this stuff. Okay. So now you open your terminal, and go to that folder. So when you clone that, when you'll be downloading the zip file, open that zip file and go in that folder. So it should be easy, right? So cd and write go into this file and open your VS Code in it, right? And once you open your VS Code, write Python -m and Ven. It indicates that you're going to create a virtual environment, and let's name that as an OLS regression challenge. So just write OLS, which will be the name of our environment, and then let's click on enter, and that creates. We noticed. Do you want to select it for the workspace folder? Yes, I want to select it for workspace folder. Now we have created a virtual environment. Named OLS, where it says that you can see that a new folder has been created where all our files will be installed, or our packages will be installed. Now it's containerized in a particular environment. So now project will only run if that environment is activated, if this environment is activated. Okay, so how can we activate this? This is pretty much like I'm totally trying to make sure that how eventually if I'm in initial versions, how I'm going to make sure that you're able to get it. So basically if you go to the if you go to the bin file, and then you have something which is activate, so you can either go there and then confirm it, right? Either you can go there like cd and blah blah blah, you just go there, or you can just have a sets like, let's say you want to go with in the folder of cd ols. Eventually I actually use pyenv, to be honest, because because of my organization, because in previous organizations they were using PyEnv, but I recommend you to use Ben because it's just initial version of yourself. That's why I recommend to use that. Then I go to Ben and then click on source activate. Or maybe you can run simply the activate as well. It should run very fine. So now when you see over here OLS, which means that now you can run your project with that particular environment. Okay. Now you can go out of that. However, you can also write source and then you write OLS, and then you simply write our bin, and then you simply write activate. Okay, it should work perfectly fine, right? So I actually gone and showed you the step-by-step solution of that, right? Let me just zoom in a bit. Maybe it may be beneficial for you to notice, which is out here. So let me just zoom in a bit. Yeah. So now we have activated our environment. Now what we need to do? Now, as I said, now once we have activated our environment, now what we have to do? We have to let us go through the project. Let us go through all the files, right? That's much more better rather than showing it like this. So now you'll see something like this after you have activated your environment. So I'll recommend you to go to readme.md, and this in readme.md you'll find everything which you need, which is what exactly the problem statement, etc. Now what we need to do, we need to install the required libraries which we'll be going to use in this project. So we'll be going to use this project, as well as we have some other libraries to install. So we'll install that for sure. So as of now, we'll install these libraries which I've created as requirements, which says that these are the requirements for this particular project, which means these are the libraries or packages which needs to be installed for this project. So when you go to there, and then what you can do, you can simply add, first of all, which Python. So let's think about which is the Python which you're using over here. We are using the Python which is created for this environment, and then let's talk about which pip you're using pip for this particular. You can see that OLS, bin, and pip. So pip is also for this particular environment. Now what we can do, we can simply install pip install -r requirements. So what this does, so you can simply name all the libraries with the specified versions which you need for that particular library. We'll come to that how we created this at the end, but as of now you can simply have this pip install, and this indicates that you can also install it individually, but I have added in a file so I can install it all at the once by a single command which is in the requirements file, and then it goes in the first, install the first, second, third, fourth, all the way around to the end, and then simply click enter. Once we click enter, it takes a bit of time to do that, and then you will see that it is being all the packages are being installed. So all the packages are, I think, being installed over here, where they're installing matplotlib, they're installing numpy, they're installing scikit-learn, they're installing stats model, and then we are done. So we got a bit of warning over here. What that warning says that the pip version which we are using, it's not upgraded. So let's upgrade our pip version. So let's upgrade our pip version. So we can simply add Python and then use this particular command. So it is saying that use this Python, which is a Python. The path of the Python is over here, but you can actually absolutely use that Python because you have just checked that Python. The Python is like the environment Python only, and then you're installing pip install, and then you upgrade the pip. You simply upgrade your pip and then click enter. Now it upgrades your pip to the latest version, which is 23.0. Now that warning can be removed. So I hope that this gives you good sense about what exactly we wanted to do. Now we have the working available things out here where we set it up our project. Now we are ready to start off with our explanation of the project. So if you open our notes, we had this notes out here we had this notes out here. Let me just move it a bit. You have the introduction. We have done with the introduction, all the setting up, everything. However, we haven't covered the setting up Git repository, which we'll do at the end, not right now. So now we have the required things. Now what we'll do, now we have the data. So when you open this data folder, you have a lot of things available out here. You ignore these two as of now, because this is something which will be built in the project only. You will see that is the data, and this is the original data, right? So I suggest you to go in this data, and this data you will find out the data which is available out there. So let me just open that. So I think when you'll open this in CSV file, it will look much more better. I have already shown you in the introduction session where you can, if you go over here, you will be having cancer regression.csv. You will be able to see the data out here. Okay, now over here, the first step is which you'll see a very simple where we had a class where we are taking out, ingesting the data. And second, what we'll do, we'll start off with understanding our data. Okay, so I've created a very nice notebook where we did a very extensive EDA, dealt with, outliers, we dealt with a lot of things out here. So we'll cover that in great detail. So I hope that, and then we'll after the EDA, we'll cover some pre-processing techniques, we'll cover some feature engineering techniques, then we'll cover some pre-processing steps, etc. I hope that this guides you super well. Let's catch up in the next set of lectures to understand the EDA and everything out there.
So everyone, welcome back to another lecture, especially on some theory part, which we'll try to discuss. I will start off with this basic EDA, and then with the basic EDA, we'll try to figure out what is the possible, data cleaning techniques and data preparation techniques which we have to go forward with. Right. So let's start talking about all of these things. But before that, we're going to review a quick concept which we have to go through is about quartiles, right? You can read about deciles, percentiles in the lectures taught in the probability and statistics part. I would like to go through only one concept of over here, which is quartiles. So what is quartile? Quartile is something which basically quartile is a part of quantiles where we divide our data into some sort of distribution which are equal sized, right? Or subgroups. Okay, so we divide our data into subgroups, right? So we have already studied that it divides our distribution into 4 equal parts. So quartiles divides our distribution to 4 equal parts. And there are 3 quartiles. So here, assume that you have this data. So assume that this is a column 2, 4, 5, 6, 7, 8. So divide this data into equal parts where you have first, second, third, and fourth. So you'll see that all are equal parts, and this is the quartile number 1, this is the quartile number 2, and quartile number 3. So quartiles are at the cuts where we divide our equal parts, right? So the first step of is for taking out the quartiles. So what is quartile? Quartile is where we divide a distribution for 4 equal parts, and quartiles are like Q1, Q2, Q3 are the quartiles which are present at the cuts, and they, first of all, we have to put our data in a ordered format. It should not be unordered, otherwise it will not work, right? Over here, your quartile number 2 is the median. Quartile number 2 is the median. So let's talk about quartile number 1 and quartile number 3 in great detail. So basically you're seeing in front of you that you have that you have distribution of your particular data, right? And this is quartile number 1 and this quartile number 2 and this quartile number 3. So given this particular information, Q1 is the central point between your smallest value and the median of your column. Okay, Q3 is the median. Q3 is the median, and Q2 is the highest score. So basically, what given this example, so assume that this is an example of your marks you got, right? This is an example. So you put in order format. Now you take out Q1 by this formula. You take out Q1 by this formula. You take out Q3. You take out Q3, which is the middle value by this formula, and you take out Q1, Q2, Q3, which we have already taken out, right? And now what Q1 tells you, Q1 tells you that 25% of the scores are less than 68. So if we have the quartile number 1, which is at the position number 5, which is 68, so we say that there is 25% of values. There's 25% of values which are less than 68. Quartile number 2 tells there are 50% of values which are smaller than So whatever median is there, so there is 50% value which is smaller than this particular median, right? 50% values like this 50%, and the 50% who are greater than this. So that's why Q2 is called the median, which is the middle value where 50% greater than this and 50% smaller than this. We have Q3 where we say that Q3 which says that which is the 75th percentile, or you visit where it contains the top 25% of the scores which are greater than 84. Right, so basically it is saying that whatever the score which are greater than 84, that's what the greater than 84 are the 25% of the values which are top 25% of the values, right? So this is also called the 75th percentile, where it says that 25% of the scores are greater than 84 and 75% less than 24. So basically out this we say that there is 25% of the score which are greater than 20, which are greater than 84, because that's the quartile number 3 for this particular example, greater than 84, and there's 75% of the examples which are less than this. Okay, again I'll repeat, quartile number 1 says that the 25% of values are smaller than this Q1, whatever the value over here. 50% of values are small, and quartile number 1 says the 25% of values are smaller than this particular value, and 75% of the values which are greater than this particular quartile. And how you can take out? You can take out by this formula. Okay, I hope that you're getting one way to interpret it. Q1 is the middle point. Q1 is the middle point between the lowest value in your data and the median of your data, right? Median of your data, that is the, because 50, what is the half of 50? Because the median is called the 50th percentile. So what is the half? Is 2, which is 25th. So you have to take the median. This is the central point between both of them. And Q3 is the central point between median and the largest value, maximum value in your data. Okay, this is the one way to interpret it. Another one which we are going to talk today is IQR. What is IQR? IQR, it tells us how far apart your first and third quartiles are. Okay, indicating how spread out your 50% of your data is. So what it is telling? That IQR is the difference between your quartile number 3 and quartile number 1. Okay, where it says that because most of the data lies between these two, right? Because most of the data lies over here, right? So we are not take out the range. How do we take out the range? First of all, is the simple range is taken out by maximum minus minimum, right? But that is not resistance to outliers. We have a talk. We had a talk. Please see the probability lectures. Please, again I'll repeat. It is if we use our formal range, where we take out the maximum value and maximum and minimum value, then it can lead to outliers. Why? You can see over here, which we have listed it out. For example, you have this data out here, right? Now you have quartile number 1 3.5, quartile number 2 6, and quartile number 3 8. Okay, which are the cuts. So we can say that there's 25% of the values which are less than 3.5, 50% of values which are less than 6, and 25% of values which are greater than 8. Okay, so assume that you can take out IQR, which is the quartile number 3, which is the range of the values where your most of the data are present. Okay, where your most of the data are present. You should think logically as well in this. Over here, we are taking out the range of this particular where are most of the data lying, right? Where are most of the data lying? So they are not likely outliers. Outlier are the one where they are out of the distribution, right? So IQR is it tells the range. It describes the range between these two, quartile number 1 and quartile number 3, where it says that how much your data is spread out, just like the range where you talk quartile number 3 minus quartile number 1, because we just take out the range of this particular part of the data. That's why it's quartile number 3 minus quartile number 1 we do. So you get 4 and range is 7. But why we don't use range? Why we don't use range? Because let's take an example. We introduce 100 over here. So 100 minus 2, which is 98. Right, but quartiles will not change over here. The quartiles will not change. So our IQR will be resistant to even these outliers, but range will be affected.
right? So that's why where are most of the data are present, we take the range of that. That's what the interquartile range. I hope that that gives you good sense of what exactly we wanted to have a talk on. Now what I'll do in the next after the review of this, we'll talk about a very nice stuff which is box plots. So let's go into the next lecture and talk about something known as box plots. So hey folks, welcome to the another lecture on box plots. So eventually I think we haven't had a good talk on box plots and all, but it's very easy, relatively easy if you know about quartiles and all, right? So assume that you have a data, assume that you have a data out here. So let me just first of all give the title as box plots, right? Box plots. I know my handwriting is not good, but that's something which you have to bear with. And we'll extensively use this box plot to do a nice thing. Okay. So basically assume that you have this data 18, 34, and then you have 76, and then you have 29, then you have 15, then you have 41, 46, 25, 54, 38, 20, 32, 43, and 22. So you have this data available out here. Now the first step, as I told, the first step is to sort it, right, in an order. So when you sort it in an order, you'll have 15. Okay, let me use another pen. Assume that you'll sort it on another order, which is 15, 18, then you have 15, 18 is 20, then you have 22, then you have 25, then you have 29, then you have 32, and then 34, 38, 41, 43, and 46. Right? So this is our sorted data now. So now once we have the sorted data, now and then we have 54, sorry, then you have 54 and 76. So now we have the sorted data. Now what we need to do, right? So now once we have that sorted data, we want to take out the quartile number 1, quartile number 2, and quartile number 3, right? That's our goal to take out. So how can we take out these? As I said, divide your data into equal parts first. Is divide your data into equal parts. So first of all, let's find the middle value. So first of all, let's count the number of our values. 1, 2, 3. Okay, so let me just 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you have an even number of values, right? So that's something. So basically, I've already conducted it. So when you take out the median of even, then I think you should tell me the formula in your Discord. So go over there and tell me the formula for median. You should be able to. We have already covered this. So the median will come which is over here, which is the quartile number 2, which is around 33. So the values over here are the values at this side on the left side are the 50% of values which are smaller than 33, and the values which is over here are greater than 33, which is the 50% of the values. I hope that makes sense. Now once we have this quartile number 2, now we are going to go forward to quartile number finding 1. So quartile number 1, we can use that formula to find the index. I have already used it. So this particular is the quartile number 1. This particular is quartile number 1. This particular is quartile number 1, right? And now we want to find the quartile number 3, which is over here, which is quartile number 3. So now you see that we have divided our data set into 4 equal parts: 1, 2, 3, and 4. Right? 1, 2, 3, and 4. So we have already divided our data into 4 equal parts. So now your quartile number 1 is 22. Quartile number 2 is, which is the median, which is 33, and quartile number 3, which is 43. So you have 50% of the values which are smaller than 22. 25% of values which are smaller than 22. 50% of values are smaller than 33. And then 20% of values which are greater than 43. Okay, so currently you have this particular example with the statistic which you have. Now what we're going to do, as I told, let's take out the IQR as well. IQR, right? What is IQR? IQR is the range where all the data lies in, right? Which is Q3 and minus Q1, where all your data lies in, which is 50% of the data, which is 43 minus 22, which will give 21. Okay, so that's your IQR. So that's your
IQR. Now what we need to do now, what we need to do, okay, first is we can go forward with taking out the maximum, we can take the minimum and then take out the maximum and then make a box plot out of it. But for outlier identification, we need to make whisker, okay, we need to make whiskers. So what is whiskers? Whiskers gives you that a maximum and the minimum value in your data, and maximum and the minimum value data according to the IQR range, right? According to the IQR range. So it gives the maximum and the minimum value in the data according to your this value 21, according to this. So basically we have the maximum, and then if we say if any data points go above this maximum, then that's an outlier, or any data points which go below this minimum, then that's also an outlier. So for outlier identification with respect to our IQR, because our IQR is resistant to outliers, so we're going to take out, so we have a whiskers which gives us the maximum minimum values which are also resistant to our data, which helps in detection. You will get to know, just wait for a second. Now we want to take out the maximum and the minimum value. So minimum value can be taken out by Q. I think we can take out Q1 minus 1.5 times IQR, right? That's the minimum value, and then maximum value can be taken out Q3 plus 1.5 IQR. Okay, so this is the formula for minimum value, for taking the minimum value in the data with respect to this IQR range, and this is for maximum. Now you may ask, how does this came? This is something which you can go forward even if you want to research more, how does this derived, but that's a very general explanation behind this, but that's not a scope on this. My scope on this to tell you that we want to find out the maximum and minimum values with respect to the outlier range. If there was simply a range or something, you would have just taken the minimum and maximum values, right? But that cannot be used as the outlier. I'll tell you at last why we cannot use the minimum and maximum, why we need to take out the minimum maximum with respect to IQR. So if we do the calculation to 21 minus 1.5 times your IQR, which is 21, and then comma, because this for minimum, and this for Q3, which is 43 plus 1.5 multiplied by 21, you get 9.5, and then you get 74.5. So this is your minimum value and this is your maximum value. So if anything goes above this, if anything goes below this minimum, if any data points go below this data point, we say that 9.5 minus 9.5. If any goes above this is called the upper limit and this is called the lower limit. So if any goes above this, we say that that's also an outlier. So let's try to do with the help of a diagram. So I'll make a very nice diagram right now. So assume that you have a diagram over here. You have the diagram over here, a number line. So let me just make a diagram like this, and let me just use another pen. Yeah. So you have 0, then you have 20, 30, 40, 50, 60. Let's extend this. 70, 80, right? So you have 10. So you have this number line out here. Now basically what was our outlier? What was our outlier? What was our quartile? The quartile number 1 was 23, quartile number 2 was what? 33, and quartile number 3 was 43. So it is slightly over here. So we simply make something like this. Okay, I know this something is not great, but this is what it looks like, and this is your quartile number. So now this particular is quartile number 1, this particular is quartile number 2, and this particular is quartile number 3. As it makes sense, it is 22, it is 33, and this is 43. Okay, so you have these three outer quartiles as of now, which you have already seen. Now we wanna now, one thing which we can do, we can simply say that something like this. We take out the minimum and a maximum and then just add it. For example, in this case the minimum is 15. So we can have over here, we can have like this minimum case, and then what is the maximum? Maximum is 76. So we can have something like this. Okay,
We can have something like this, but I'll tell you why it will not work. First of all, you see that 76 is bit out of the distribution, is bit outlier just by seeing it, right? So I'll tell you why it will not work. First, as we said that IQR is resistant to outliers, and IQR represents the 50% of our data. So if we take out the maximum and minimum value using IQR, that makes more sense, because we'll be able to identify where our most of the data lies. So if any of the data goes out of that spreading out, we'll consider that as an outlier, right? So now I think it will make more sense if we just try to now make it more sensible. Yeah. So now we have this minus 9.5. We have this minus 9.5 where we say that we make a whisker, which is minus 9.5, which is minus 9.5. So, and then you have the 70, I think, what was that? Yeah, so it will be something over here. So anything which is now anything which this is for the maximum, it's for the maximum value, and this is for the minimum value. Okay, it's for maximum and this is for minimum value. Okay, so any our data. So how can we use this to remove our data? How can we use this to remove outliers from our data? So we say that anything below minus 9.5, anything which below minus 9.5 is outlier, anything above 74.5 is outlier, because this is the distribution, this is the range of our maximum data, where are most of the data. So anything above this, so if we see our data, anything below minus 9.5, there's no anything below minus, but there is above 74.5, which is 76. So we simply say that we consider this particular thing as an outlier, this particular thing as an outlier. Okay, this particular thing as an outlier, this particular thing as outlier, and we remove this data from our plot, right, from our data. So we remove that outlier, right? There, the linear regression, there are lots of algorithms that are sensitive to outliers. Okay, so you have to remove these outliers, which we'll study later on as well. So we'll remove this outlier by a box plot, where I'll summarize the concept. You take an order, you take out the quartiles, you take out the IQR, you take out the maximum and minimum value by this formula, which is out here, Q1 minus 1.5 times IQR, Q3 plus 1 point, this for maximum, this for minimum. Anything above this is bad, anything above this is outlier, anything below this is outlier. I hope that makes sense. Let's catch up in the next lecture to actually see the practical of it and how we actually do it to identify outliers in your data set. Hey everyone, welcome back to another video. So now what we'll do, we'll start off with EDA stuff and processing stuff which we eventually need for a project, and I'll make sure that you understand each and every concept in great detail. So you can actually read all of this thing which we have done it for you. But let's start off with we are done with the ingestion of the data. Now let's start off with this file. Don't know what's this file? Don't worry, we'll figure it out. The first line of the code states that we ingest the data from our data ingest file. So it goes in data ingest file, it ingests this class. So if you click over here, you'll be going to this ingest data class, and over here in this class you have the init method, which is a constructor, and then you have a method which is get data, where we ask for the path of the data where the data is present in your folder, and then we read the CSV. If it is a CSV file, we read that, okay, and then we return the data frame, right? So it goes into ingest data. It just imports that class. Then it goes in processing data. It goes in processing file, and then it imports the following columns, which we'll take a look in a bit. You have to just wait for a sec, right? Which we'll take a look in a bit. And then you have from feature engineering, there is another feature engineering file. We're importing some functions, which is important to us as of now, right? So now you see over here, we have ingest data, and we are what we are doing, we are simply instantiating a class, and then using that class, as we said, we are using the method of the class. If you see that method is get data over there. So using the method ingest data, which is the object, which is the blueprint of the class, we say that we get the data from the following from the following folder. So we go to OLS, we go to data, and then simply copy the relative path of it.
right? And then we import that, and then now once we have the data, now it's ready to start with some of the processing which is required as of now. But before processing, what I usually like to do, I usually like to go through all the basic data, see how's the data looks like, see some of the missing values if I have any, and talk about distribution, right? So let's before going on the distribution one, before going on a processing one, I would like to take a time to explore a bit of exploratory data analysis and all. So what was our project? Our project was to identify the number of deaths which was due to the cancer in a specified population for over a period of a time, typically 1 year. So mortality rates are nothing but a number of deaths occurred for a period of a time. In this case, we have given already. In this competition, you have to build a multivariate least squares competition to predict the cancer mortality rates for US countries. Right. The first step is, of course, we are going to import the libraries. Of course, sometimes I've imported in between as well, so I'll do it as we go along. So we import our libraries. As of now, we need pandas and numpy. We have PD as an alias so that we don't have to write pandas dot every time to use pandas. So we have PD where we can use this PD. Now, one thing which you're using over here, we are not importing that class just for sake of simplicity. I just added it. We can give it to any people. So just for simplicity. However, we can use that. We can simply import the from data ingest, and then we simply import the ingest data file, and then we simply make a ingest data, which is, I'm just going to comment it out, ingest data, which is ingest data, and then simply say data is equals to ingest data. So you simply have this to actually import the data, but as of now I just imported that because of simplicity, so that you could be on the same page rather than going over this. So if anyone is seeing ADS, they should be able to understand it very well. So now once we have the data, so now let me start running it. So before that, I would like to just tell you that we have to, over here, you have to activate your environment in Jupyter Notebook as well. In VS Code, we have this selecting of our kernels. But in VS Code, you can simply write like this. Source, and then you simply have the following command which we have used earlier. So now you see that we are using source, and then it is activating it. So you can simply use this as well. You can simply use this as well, source, and then you simply give the activate. It will be able to activate for that particular environment. However, you can change the kernel as well in your VS Code. If you have issues, if you're having issues over there, please let me know. I'm just deactivating because sometimes Conda, I have also a Conda installed, so I have to it's my system thing which I have to deactivate. Right, it doesn't really matter, it is a base thing, but I deactivate for a safer thing. But as of now, you just simply source, then you have which you have used source, and then you simply activate it. Okay, and then also this base also gets activated, but it may not be shown, but it is not going from here. It is my system things. I don't know what happens, but I think I need to uninstall this Conda. But never mind on that. But you can first of all activate that environment whenever you enter the project. First step, activate that environment, because that's what the project, right? Once you have activated the environment, now you should be able to run it. So let me run the first cell. I usually use VS Code because it's much more simpler. So it says that for VS Code, we are going to download. We have for this particular environment, we have to also download the IPy kernel. However, if you're using VS Code, you don't really need this. Okay, you don't really need to download every time. But I don't know, but yeah, for VS Code we have to. Now it runs. Now you see that it takes some seconds to run it, and then we simply say, "Acha, now let me import my data." So this is what your data looks like. Where you have the 34 columns and 5 rows. Where we are asking to show the 5 columns. You can also specify on it to 10 or 5. It is just show the top 5 columns. And over here, it says average ANN account, average deaths per year. This is a target variable, the death rate in that particular span, incident rate, median income, right? Power type, study recap, bind dink, which is and media range. So you see that this is something unusual. You have to work on this. So I'll come back. Like something you have NaN values. OMG, you have missing values available. You also have, you also have, if you explore the data, you also have, over here, which is the English, which is the categorical values, which is this text value. So how we are going to deal with that, right? Missing values, categorical values, in type of interval type of thing. How are we going to deal with this? Because we cannot just feed it to them, because model will make, because this acts as a string right now, so that model will not make sense. So there's a couple of things which you have to take care. Missing values, right? The first is missing values. Second is over here, which we see that this is something unusual. This is something unusual where you have the lists in every column, and then you have, text variable, okay, object variable. We can use simply data.info to take out things out here. To take out who geography is in a string, and then you have enough all values are float, target there is float, and then you can take out the null, and then it gives you good information. So now let's take out, so now once we are done with exploration, you can also take out describe. You can also write describe. So data dot describe. And then over here, when you do the describe, then what it does, for every column, it describes some of the useful statistical analysis. For average ANN, there are 3047 count with now the number of values in that particular column. What is the mean? Mean is 606. Is standard deviation 14 and 16. Minimum value in that column 6. 25% of the values, which is 76, where we see that there is this 25% of the value which is smaller than 76. 50% of the value which is smaller than 171, and 75% of the, and rest 20, and more than and 25% of values which are greater than 518, or we can say 75% of values which is lesser than 518. All right, and maximum value in that column is 385150. So you have now for every column listed out here. And then now once we have the basic things, now what we do, we simply go ahead and simply take out some of the because we have noted down three things. That bin wala thing, and then you have NaN values, right, and the categorical. So let's take a look what number of missing values which we have in which columns. So if we run this, we say that null values, we put the null values, and then we say data.isNull.sum. So what this gives, this gives when we print out null values, this should give this every column with the number of null values present out there. With the number of present null values. There are only 3 columns where your null values are present. There are only 3 columns where your null values are present. So we say that you print the null value, from the null values from that series. Take the null values whose null values are greater than 0. Right? So we simply print that, and then we say there are 3 columns: post, PCT, and over here. So now there are several ways to deal with missing values, which we'll talk about in later videos. So I'll give you a quick solution in this, but we'll also talk about there are several ways: KNN imputation, simple imputer, blah blah blah. So there are several techniques for dealing with missing values with their pros and cons, which we'll deal with in great detail. Then we have, now once we have this, let's worry about other things. Let's start exploring each and every variables. So once you have the basic missing values, exploration of the data, now let's go ahead and talk about how we can now you have to analyze each and every variables in your data to further analyze your data. So now you may be thinking, hey Ayush, how are you coming up with these things? The first step is in anything is to do a basic exploration. Okay? Have a template, basic exploration, where we talk about what are the number of is there any missing values, what is the data types available for every column, what is the maximum minimum values, what values are greater than this, what values smaller than this. And the next step should be to analyze each and every variable. Okay, each and every variable out here, that will give you a very good set of things. First is we are going to analyze our target death rate. We're going to analyze our target variable, right? Target variable, in which we say that plot.histogram, we are plotting the histogram, bins should be 20, color should be blue, and edge of the histogram should be black. And then we say on x-axis, label that as a death rate, on y-axis, label that as frequency, and then title should be histogram of the death rate, and then we show that plot. Show me the plot right now. That's what it is saying. And I'll talk about what is the interpretation of this. So when you actually take out the histogram of this target death rate, take out the histogram of this particular column, this will result in this particular histogram. So you may have high time in interpretation of it. So let's talk about interpretation of your histograms. The values which are grouped into bins along the x-axis. So the values are grouped along with bins. So you see over here on the values on the x-axis, they're grouped in bins. So we'll talk about the bins first of all. As of now, which you see over here in this histogram, it shows all the traits which are divided in the bins, and y-axis in the counties, the frequencies in that bin. Okay. So we say that 0 to 100 is I think 50 to 100, not 0 to 100. 0 to 100 is 50 to 100 is one bin, 100 to 150 is another. But over here you might have noticed that we have 20 bins as of now. But if you notice it very nicely, that this the range of this, you see the mouse right now. You see the mouse where I'm indicating. So this is 20 bins. So we say that in this particular bin, what are the number of frequencies? What are the number for this particular bin? What is the frequency? Right? For this particular bin, what is the frequency? So that's what it is telling, that it shows all the traits in x-axis with the bins. Over here we have 20 bins, 20, and then another 20, right? And y-axis is the counties in that bin. So for this particular bin, this will be the counties. We simply have this 100, we have this bounties. For this we have this much, which is 550 around for this particular, right? So for 150 to, maybe let's take an example of this particular bin. So we have this 550 type of thing. So now this is the simple interpretation of histogram which you've already seen. But now once we have the basic understanding of histogram, how this will help us, right? First, it helps us to identify how does it help us to understand a particular variable in terms of statistical format. First, it will help us to identify what is the center of the data, what is the spread of the data, and what is the range, and what is the shape of the data. Right. So let's answer these three questions. What is the center of the data? But before that, let's to note something. Number line spans from the minimum value to maximum value. The number line is broken into equally sized intervals. You see that all are equally sized. These are nothing but called bins covering the range of values. Over here, it is 150 to this will be we have 20 bins. So in this particular, we have all the values which lie in this range, right? Which lies in this range. Okay. Very said number line is broken equal, called bins, and every bin has the range of values in that. A histogram shows how frequent values occur in that particular bin. So in histogram, it shows how frequent the range of values occurs in that particular, how frequent on y-axis is for this particular bin, there is 680. That is the frequency, right? So that is the frequency. The height of each bar represents the number of values in the data set that fall within a particular bin, and when the higher number of thing is. And then you have y-axis, which is the count or number, which is to be discrete, which represents the amount of data falls in that frequency, of course. And the histogram makes it easy to see which values are common and which values are less common, or which range of values are less common in your data set. Okay. Yes. Now once we have that, let's go to some of the observations. So I've linked the resource, which is good for you. First observation is it is slightly positively skewed data set. So if it is not completely normal, it is very slightly positively skewed data set, right? And then there are outliers as well. Yeah. So you see that over here, you see over here, you see over here, you see over here. See these are out of distributions, and these outliers. Nice. So we got an idea. This is a skewed data set, or slightly, and you have the outliers. And this is also not a completely normal distributed. It is not completely normally distributed, and its mean is greater than median. In slightly positively skewed data set, your mean is greater than median, and you have 3 peaks in the data set. So you have bimodal data where you have 3 peaks in your data set.
right? For that particular range, this is the high, this is 1, 2, 3, these are 3 picks. That's why we say bi-model data. But the most important key takeaway, which I'm going to take from here, which I'm going to translate, is we have the columns which is slightly skewed, we have the columns which is normally distributed, we have the outlier in that column as well, right? However, we are not going to we will just take care later on about the outliers, but that is for this particular variable. So we do this for every variables, but that, for example, if you have 1,000 variables, how you going to do it? That's something is a talk on specifically. But I hope that this histogram gives you a nice sense about what exactly we're going to deal with the next. So next, what we're going to do, as we've identified we have outliers, we're going to use box plot to see whether we really have outliers in a great sense, right? So we're going to use that and then have a very nice understanding of that. And for every variable, we'll do the nice exploration, and then we'll learn about outlier detection, removing, and a lot of things to talk on. There's a very lot of things to talk on. So let's go to the next lecture and talk about that. So everyone, let's get started with our data processing techniques which we wanted to. So you will find a file which is data processing test and data processing. Data processing test is a file where we are testing all our data processing, our methods out there. So we'll try to go through step by step what exactly we are doing and why we are doing that. Right. So first of all, let's get started with what exactly things which you're going to use. First, we ingested the data, we get the data, we imported data using CSV file. And then what you're doing, you're finding the constant column. So this is not appropriate for every case. So basically this find constant columns, what this does, this function takes a data frame and returns the columns that contains a single value. So if your data frame, if your column has only one single value, that's the very bad thing which can happen, right? So it will find the columns which is constant, right? Which has the single values, which can indicate either of categorical variables or the variables which does not provide any sort of values to your data, right? So we find the constant values, constant which has that a columns that contains only a single value, either A111, either 222, or whatever. So constant columns, we make a list, empty list, constant columns, and we iterate through the columns data frame, the data frame.column, where we ask for the data frame as an input to the function, and then we iterate through the columns, and then we say that find the number of unique values in that column by using unique method. And then if that unique method is greater than 1, then append that particular column in this constant columns, which we are doing over here. And then we are returning at the end the constant columns, right? So that's the first step which we are doing over here. So it says the columns that contains a single value, and then print out the constant columns. And then let's try to run it. So what exactly I'm going to do is maybe go to run my interactive window. So I'll just run my interactive window. So we have OLS activated in this as well. So you see our virtual environment, which is OLS, is activated in this. Now, so we have that. Let's wait for a few seconds, then it should work really fine. So over here, which you're seeing in front of me, it is running the 13 lines of code which I've selected. You might use Jupyter notebooks, or you might run the whole notebook step by step. The way I like is interactive. You can also go online and search about Visual Studio Code interactive notebook. You will be able to find out. So if you go and then search out Visual Studio Code interactive notebook, then if you go and see, then you'll be able to see that Python interactive notebooks, where you can actually download each and everything and then run that thing interactively by selecting the number of cells. So now it says the columns that contains a single value is nothing. So you have a you have a column which has at least more than one value. So at least it has a good spread. So that's something which you don't have to worry about. Sometimes it may happen that the columns contain a single value, and then you want to take a look if your data set is too large enough. Now you go to columns which contain a very few number of values. So I've also written delete constant column. So what this particular method does, this drops the columns which are constant, but in this case we don't have any constant columns. Now we search for columns which is with few unique values, where we say that function takes in a data frame and a threshold as an input, like what number of constant values, and then return. So for example, some columns may have fewer number of values in that column. So we say that we simply say that we make an empty list, and then we loop, then we iterate through all the columns in a data set, and then we find the unique values for every data frame, and then we say if the unique value is smaller than threshold. So for example, you say that you want to take a look at the columns which has less than three unique values in that particular column, right? So if that is smaller than threshold, then it says that append that column. So you basically have the columns which has fewer unique columns. So it should also give you empty slide, which is saying if you print this out. So I can just print this out. It works like a Jupyter notebooks. So it says that there is no such columns with even few unique values with a threshold 10. Okay, with that threshold 10, you can change your threshold. So similarly, I have several methods as a template for you to make this work in your further projects, like find duplicate rows. So it may sometimes happen that you have a duplicated rows as well. So you can actually delete the duplicate rows by using these two methods, where you first of all find the duplicated rows by finding dot duplicated, and then you simply drop the duplicates by keeping the first duplicate. So you might have first duplicate, second duplicate, third, where the second and third are the same as first, then it keeps the first and drops the second and three, right? So you delete the duplicate, etc. So you have a couple of methods now here, but we are not using them. So now you have the basic things, which is just for us exploring things. There's a lot to left in data processing. Now we have all of this left. Now what we'll do some more sort of a basic feature engineering or feature construction. Okay, that's called feature construction, right? Feature splitting and construction. This whatever I'm going to teach right now is called feature construction, feature splitting. So let's do that in the next video. So now what we're going to do, we're going to talk about something known as feature construction and feature splitting in our data. So one thing which I would just want to highlight for you is if you see our data which we have, is let me just go to desktop, and then let me go to my OLS regression challenge, and then you have the data. Now let's go to data, and then let's open this data and then worry about two of the columns out here. The first column out here is our bend. We have seen where the columns were in terms of interval format. So you see bending, where it says that your column is an interval format 6194. So this is your lower bound and this is your upper bound, right? This is your lower bound and this is your upper bound, right? So you have this column. So it is of object type, and the model will not make any sense out of it if it is left alone. So what we need to do, we want to take the first element and you store the first element in another column, and take the second element and store that in another column. This is called the first lower bound, and this is called the upper bound, right? So what we'll do, we'll split out the values from this column into different columns by making different columns, right? So let's see how we are going to do it. So we're going to use so first of all, let me show you first of all what exactly that we are doing. We are using DF data frame, and then assessing that column and assessing the first value from that, and the first value is this. If you see the type of it, so type of it is nothing but your string, I guess. So if you see the type of it, it is nothing but a string. So now you have that string. Now you have to make the column so that it should make sense. Otherwise, the model will not accept it. So whatever you're seeing in front of me is over here. We are just ignore whatever we have imported as of now. Focus on this function. So this function is made in featureengineering.py file, and in this what we are doing, we are making a empty file bend-dink, where we are iterating in that column. So we are iterating for I in that particular column. So it will go through first value, second value, third value, etc. And then first of all, it will remove all the parentheses. My point is that it will remove the parentheses and the square bracket. So it is saying I.strip and then this particular parentheses and square bracket. So it will remove it. So if you see .strip function in .strip function in Python, if you see .strip function, .split, which helps to remove the characters from the beginning or the end of the string, right? So it strips out, it removes the white space and any sort of values which we wanted to remove. So it removes the parentheses and brackets. In this case, this parentheses and brackets. Now we have removed the parentheses and brackets. Now we have this. And
And then what it does, it split the string into a list. So we can actually split that string into a list when where you see. So it says whenever you see this column, split that string into a list by this. So when the program sees this particular column, it says, okay, this is the first element, and then splits these two differently, right? And then what it does, it converts the list to a tuple, considering that we should have unique stuff, and then it converts individual elements to float, right? So it from the tuple, it maps every individual to float. So each individual is mapped to float, and then finally convert that list to a tuple to a list. And then you append that particular that particular value into this. So if I could show you what exactly each steps looks like. So let me just show you each and every step. This should make much more sense, I guess. So let me just print each and every eyes whenever we actually go ahead and then see that, right? That should make much more sense for you. Let me just go to data ingest, data test, and then let's run it. First of all, we have to, save that. It will not work if we don't save it. So we have to save that feature engineering and then just save it first of all, and go to data test, and then now run it from here to there in an interactive window. It will take some time to run it. So now you see that for the first, it was this, then it converted into this particular thing, then it converted into this particular thing by removing all the parentheses, right now, by removing all the parentheses over there. So basically you can see now where I was data engineering. So you can see over here, we are first printing I with the removal of all the values out here, and then we are getting the value of I, which is, specified value, right? Which is which we wanted. Now you can simply what you can do, once you have the values, which is remove all the processing stuff, which is converted into a list, which you can see over here, which is converted into a list. Now that list can be added instead of those strings, right? And then what we do, we say that we make a new column, data, which is of lower bound, make a new column, and then we say that for I in that bin deck, take the first element in that list, and then we in upper bound we say that take the second with the zeroth first element in the lower bound zeroth, and the first bound first. So we say for each and every values, right? We also make a column called median, where we say lower bound plus upper bound divided by 2. That will give us median. And then we finally drop that column, which was useless in this case. So we simply drop this column bin deck, right? So this is how basically what we are doing. We're simply taking this value, putting this in one column named lower bound, taking this value, putting this in another column named upper bound, and then we are taking the median of both of this, like the first element plus second element divided by 2, and storing that in another column. That might be useful, right? So now this will start making sense. So what we did, we splitted the feature, we splitted the intervals, and then we used according to a statement, and then we dropped the columns which are useless. So now we have the information which is good. So this is what we did. Now if you go and see our data which we have, so let me just show you the data which we have. You should wait for a second. It's still opening. It's very big, to be honest. Yes. And then we'll go to categorical to column, and then we'll talk about categorical encoding in the next set of lectures. So if you see out here that spreadsheet, now if you see over here, you have something known as upper bound and lower bound. So let me just show you to you. First, lower bound. So that lower bound have this particular values, upper bound had this particular values, and median is this, right? So we removed that because that was not making sense because of interval. That was a string, and model will not make sense out of it. We made something like this, which will make sense to our model, right?
Now we have something known as categorical. So now another issue which we had, I just want to show it to you what issue which we had is this particular column. Where is that column? Data, and then we just going to show it to you. That's much more better. Yeah, so see this. Now we are done with this. Now you see the geography column. In geography column, we have the county and the state, right? County and the state. So both are the same point, right? So can't we split this feature again and then have county in another column and state in another column? That will make much more sense, right? So what we do, we simply say county. We split that with that comma because comma is there. So we split using the comma, and then we say that for every column in geography, and then we say that take the, in this case we asked to take the 0th element because this will be converted into a list now. Now we take the 0th one because it was split with the help of comma, so it will be converted into list, and then we take the first element. And then we take the first element and store that in a county column, and then we take the second element, which is of course worse because it starts from 0, 1. So let's take the second element and store that in a state column, and then we drop the geography. So now you have another column for Kitsap, for counties and states, right? So that is feature splitting and reconstruction. This is the process is called feature splitting and reconstruction. I hope that you got it very nicely. And that's it for this right now. So what I'll do in the next set of lectures is actually talk about, we have this something, now we have the columns which is splitted. Now how can we convert, how can we make use of the state and the counties, and how can we convert that, how can we make sense out of it by different methods of categorical encoding? That's also super useful for you to understand. Let's go back and let's go to the next lecture. So hey everyone, so now in this, what I'll try to achieve is try to give you a very nice complete our feature engineering techniques, which is till the previous lecture we have completed this categorical in geographical column we have converted the geographical column into two sets of column, which is county and state. What I'm going to do next is talk about one-hot encoding, which is so you have seen the data where we had the values, which is categorical. So now we had the two categorical values, which is this county and state. In county we have some other, and state we have some other set of values. Now we have to convert this into some sort of integer or numeric that should make sense to the model, right? That's your model should be able to interpret it, right? So now what we need to do, we need to you encode those categorical variables, right? So we'll learn about several other encoding techniques later on, but we'll encode those categorical variables or try to make sense out of that English. Otherwise it will give a good error because your model will not accept the English stuff. It will accept only the numeric, and you have to make in such a way that it should make sense. Okay, so what exactly I'm doing it over here, whatever you're seeing in front of your screen, is you have a categorical columns. In that categorical columns, you are selecting in that data type, so selecting the data types which are of object, and then selecting the columns. So basically what this categorical column states, that this is a list of categorical columns whose object is data type. So most of the categorical columns whose data type is object, right? So that's what we first of all select the categorical columns, and then what we do, we had the one hot encoder instance. We create an instance with the following parameters. So let's try to go ahead and then talk about what exactly one hot encoder. So I'm just going to go ahead and then talk about show you a very nice visual, a quick understanding of that. So whatever you're seeing in front of me is my screen. So see this, you have the categorical variable. You have a categorical variable which is color, and then in that you have red, blue, green, blue. So as of now, instead you have Washington, blah blah blah, right? So we in this case we have a categorical variable which is color. So what this one hot encoding will do, one hot encoding will create the three other the number of unique values in that particular column will be the equals to the number of new columns which will be created. And now for this, assume that color is for the example, in ID number one, we have color red, where it says color red is present but color blue is absent, green absent, and blue is absent, right?
Same goes with color blue. And then in first ID color blue is absent, but you see the color blue is present, so that's why it's 1. So basically what we are doing eventually is removing is converting that into a dummy variable type of thing. We're creating some sort of dummy variable for every values, and then we are seeing if that particular variable is available or not in that. Right. So I'll tell you a very nice example in there. So you can also go and see the other set of examples. So let us assume that you go and see this one. Assume that you have seen this example, and in this example you have island as categorical variables, and then for every categorical variables you have the columns created. For every means the unique categorical counts in that. So Biscoy, and then in Biscoy the first ID is 1 because it is present, but tungsten is not present, that's why 0 in the first ID. In the first ID, right? In see my mouse. So in the first ID Biscoy is only present. Then a second ID at the last column Dream is present, and the third we have second tungsten is present, right? So this is how we create new set of this is how we convert this particular one column to the number of a number of a column which is equal to the number of unique values in that particular categorical variable. And in that and how we do it, we have the particular ID, and then we see that ID is present in that particular column or not, right? So I hope that this makes sense. I'll be giving you a very, very nice example as well. So this is what the one hot encoding will do, which over here, what is this? Parse is equals to true, and then handle unknown is equals to true. So what is this variables? So handle unknown is nothing but, I think that there is a very nice set of, yeah. So handle unknown, which is the specifies the way. I think there should be some, yes. So when giving an input, if there is any unknown values comes in, so ignore that. For example, in that categorical variable, apart from red, blue, green, apart from this, some other, a violet color comes in, but that's not present in your data. So it is asking to ignore that part. Okay. And then sparsity, we are saying that as a false. We don't have a sparse data. Right. So now we instantiate, then we say fit transform, where it fits and transform. So basically fit the transformer to X and Y, which is to fit the data and then transform it. Like, first of all, fit the data, like have the all the things out here, fit the data and then transform it, like convert that into the categorical variables over here. Right, for all the category variables in your data set, and you have one hot encoded, which is the data set, which is one hot encoded. Now you convert that data into a data frame, and then you name that feature by getting the get features names out using the one hot encoder object, and then using get features names out by giving that particular categorical column. Right, you name that as a columns. And then what you do, you drop the categorical columns, which are now you have the geography. Now you don't need the English column. You already have the numeric converted encoded column. So you drop that, and then you concatenate the numeric which was there, and then the official data set. Okay. So I know it might make sense for you to maybe understand it, but let me just make you clear with things. So let me just open that OLS, and then let's go to processist. Let's go over there. It will take some time because it is a very huge data set now which is being created, and I'll explain you every part which is happening over here. So let's just wait for opening. Yes. So you're seeing in front of me, which is your first categorical column, which is that geography. That geography is now converted. So now you see that we have county. Abelia County, and that first ID it is not present. So every unique ID of that particular county, every unique value of that county variable is converted into the columns. Now, if the converted into a columns is now, if you see that if that Abelia is present in the first row or not, it says no, it's not present. But if you see, now this is there are so many unique values. That's why there's so many counties are created. So many variables are created, and that's the downfall of it. But we cannot do anything. That's what the one hot encoding says. Then you have state. Then you have state. I think it does not show full, but you have state, and for state as well, for state Washington, states Los Angeles, and etc. It is showing off as well. And then you see that it is mostly you see 0, but at some point you will see that there's 1 as well. There's this 1 as well, where it indicates that that particular county is present in that particular variable. Okay, I hope that makes sense. I don't want to repeat it once again. So this is how it got converted. This is a very huge data set which is being formed, right? There's a 1935 columns and only few rows, right? But we'll deal with that. So this is how one hot encoding is, where you convert our numeric to this one hot encoding. But we'll take a look at other encoders, like, you know, there are other encoders as well, where we'll take a look at that. And then now what you can do, you can simply say that one hot encoding, and then you simply encode the variables. Now you have that. Now you have also seen, now you have converted to the numeric. Now what you want to do, you want to fill out the missing values. So missing values in the data set. However, we'll be having another section of dealing with missing values. But currently what I'm explaining you see first is, first of all, we take the columns which we need to drop. Right? So here's my plan. What I'm going to do, if the missing values exceeds 50% of the whole data, then we say that remove that particular column, right? But if that is below 50%, we'll say that let's deal with it with our techniques which we have. So the first of all, calls to drop. First, the variable contains the columns which we have to drop. So we select the columns from the data frame where our null values, and where the null value is the mean of that null value, in that particular column, the mean is greater than 0.5. If that percentage is greater than 0.5, then we simply drop. If that for the particular columns, if that particular column in the data frame is, if the null values in that particular column is greater than 50%, we say that drop it, which is drop x is equals to 1 because it is a column. If this was a row, then we would have written x is equals to 0. Then if the values which are smaller than 0.5, the missing values are less than 50%, then we say that fill the missing values with that mean of that particular column. So for example, you have 1, 2, 3, 4 nan, and then 6, 7. So now you have only one value. So you fill this by the mean of all the values in that particular column, right? You have other methods too, simple imputer, Kn imputer. There are several other techniques for imputing missing values, which is a whole set of interview questions, but we'll deal with that in the next section. Like we'll study in detail, right? So we don't have to worry about that. Now this is something which is dealing with missing values. Now I hope that now what you can do, you can simply use this in one hot encoding, drop and fill, and then print out the shape, and then you can simply convert that. Now we have the process data, where what we did, we first ingested the data, we found basic values, which is converted that intervals to bins, categorical, some call it splitted the feature reconstruction, feature splitting, feature engineering of converting categorical variables into numeric, and then we simply dropped and filled the missing values. Now we have the perfect data to do the analysis on it, where now we'll deal with something known as outliers. So that something is the whole set of discussion for the next set of videos. So let's catch up in the next video. Tab tak ke liye, okay, bye. So now what we'll do, now we have done with the preparation of a data set. Now, once you're done with the preparation of the data set, now we'll go and explore some of the most amazing things in your data set, which is working or dealing with outliers. So this project, I would really like to focus on dealing with outliers. So let's go ahead and let's try to figure out a lot of things out here. Right. So in outliers, we have seen a very nice explanation of the outliers, but we'll talk about some of the methods for dealing with outliers, and I think this will be a very long video, so bear with me up, right? So first is what we're doing. We're taking out the box plot of our target death rate, where we say that I'm using Plotly. So I'm using Plotly, where we say that we're going to create a figure. In that figure, we're on y-axis, we should have the target death rate, and then it should have point, pose, jitter, box points to be outliers, etc. So this is I'm using Plotly to plot my box plots. So out here, you can see my first quartile, which is 161.2, and then my second quartile is 178, and my third quartile is 194, right? And then you have something upper fence. Upper fence is something which is your maximum, and then you have lower fence, which is this much. So whatever goes above this are are said to be an outlier, and whatever goes beyond this, whatever goes below the minimum, are said to be outliers. But this is what we have learned, right? But this is something which we will take a look at later on. But as of now, let's go ahead and let's talk about, let's analyze rather than a target column, right? Let's analyze other columns as well rather than that. So first of all, what I'll do is we have a column known as average ANN count, right? So this is a column in our data set. Now what we're doing is taking the mean of that column and then taking the standard deviation of that column, right? And then we're creating a histogram to visualize what is the distribution of that average ANN. And then we plotting the box plot using Plotly. So for line by line, I'll be giving a resources for learning Plotly, okay? So I suggest you to first of all learn Plotly because that's pretty much easy. So you can first of all, I suggest you to learn Plotly, where you are saying create a figure for that data, and then that data we going to have the box plot of this particular column, and it should be outliers zeta is equals to 0.3 and point post is equals to 1.8. However, you don't need to remember all of this. What I usually do, I just copy and paste things. So even sometimes I forget a lot of parameters. So eventually. So what I'm doing right now, I'm taking out why I'm doing this. First of all, let's understand why I'm doing this. The reason why I'm doing this, I want to identify outliers in my columns. So just for explanation sake of thing, I'm giving the tools how I go about learning more about how my individual variable looks like. How this average ANN columns is, what is the distribution, what is the mean, what is the standard deviation, what is the correlation coefficient, correlation with my target variable, what is the number of outliers present, etc, etc, etc. So in this is the step which I follow. This is a framework which I follow. Is the reason why we are doing this. We're going to summarize this. Summarize this column average ANN count statistically. So whatever you're seeing in front of me, we are printing the mean of that particular column, and then you're plotting the histogram. Bins is equals to 20, which you have seen in interpretation of the histogram. Then over here, and then you simply box plot it. And then over here, you calculate the correlation between the average ANN count and target death rate, which is we are saying correlation is equals to this particular column. This is assume that this is a vector dot correlation with whom? Target death rate, right? So we need to identify what is this direction, this strength between your average ANN count and the number of death rates in that particular country. So the correlation, it will be given by this, and then you create a scatter plot to visualize the relationship. So here's why I did. First of all, I did two basic statistical analysis of this numeric column, mean, standard deviation. I wanted to know the distribution. That's why I added a histogram. I want to know the outliers. That's why I added, box plot. I want to know the correlation between both of them. That's why I added this. Now you may think, are we going to do this for every column? If you wish to analyze any particular column, you should do it, right? If you wish to analyze, if you wish to know more about the data, you should do all of this stuff for each and every numeric variables, right? That will give you a better holistic understanding about data. So over here, and then you're plotting the scatter plot to visualize the relationship between average ANN count and target death rate. So let's first of all print this out from starting, then it will make more sense. So let me just run it eventually. So it will take some time to run it. So we'll just give it some time to run it. I think yes. Plotly, no module name Plotly. So basically it is saying the Plotly is not installed. So let me quickly install Plotly. So Plotly install pip, and then I'll just install Plotly by using pip install Plotly, by making a nice pip install Plotly. Let's wait a few seconds to getting it installed. I think it gets installed. So once it gets installed, we'll just run this. You should wait for some time. Whoops. It is saying a minimum MIME type of rendering requires the NB format 4.2, but it is not installed. Interesting question. So let's go and search for it. So this is how you should search. Currently I don't know the solution to this problem. Okay. Now let's try to debug it. So it is saying that there's something to do with this format, right? There's something to do with this format. I think that you have to update your kernel. You have to upgrade your kernel. You have to upgrade your Jupyter notebook. That's why it was saying. You can simply go and then simply run it, and then you will see that it will work completely fine. Then you see that it will work completely fine. So let me run this out, and then you see that, and then you first of all restart the kernel. So you have to also restart the kernel, to be honest. Restart, because once you install the libraries, you also have to restart so that it makes sense. Yes, now we are done with that. Now what we do, we simply have this. So let me just first of all run it out. So it says that what it says that for a particular average ANN count, you have mean of average count, standard deviation, histogram. You see it is positively skewed. It's not normal. It's a positively skewed data set where most of the data lies between your 0 to 5,000. There are some outliers also present. You can see that there are a lot of outliers present. You see that this is your upper fence, this is your lower fence, and in this upper fence you have 117 is the upper fence. So whatever values above this are outliers, and whatever values below the 6 are outliers. But you see that most of the values lies between. You see these are the values which are OMG. These are outliers. And then correlation between the target is negative correlation, where one increases then other decreases. So it is saying that the negative correlation, what it is, one increases and other decreases. Right. So as assume that so now you see over here, now this is scatter plot, where on x-axis we have average ANN count, on y-axis we have a target death rate. You see that there is some sort of giving a very nice stuff, but you see over here that but let's interpret it. So it is saying the mean of average ANN count is 606, which tells us on an average there were 606 cases of cancer diagnosed annually per county. Right? 6 and average. The standard deviation tells how spread out your data is. It indicates it is quite spread. 14 to 16 is quite spread, with counties having relatively low numbers of, some counties having a relatively low number of cancer diagnoses annually, and some counties very relatively high. That's why the standard deviation is high, because the spread is high in this case. And this is further confirmed, which you can see that this is further confirmed in your histogram or box plot. You see the correlation is minus 0.14, which tells us the strength and then strength of a linear relationship. Correlation of -1 indicates that the perfect linear relationship, which means that one increases then other variable decreases. A correlation of 1 means that there is a perfect positive relationship between both of them. Right? So this is a very correlation about how can we interpret it. So if in this case, if one increases, then other decreases. But it does not imply causation. Please see my lectures initially on correlation does not imply causation. But only thing which I want to tell is this is how you can visualize or summarize your particular variables by dealing with all of these shit things. You have several missing values as well. I think you have several missing values. However, we are going to import the process data to deal with anything, literally anything, right? So you can actually ignore this as of now. So what you're going to do, we're going to import our process data. But now over here, you will be a bit shocked to see the outlier detection. So let's try to learn about outlier detection in the next set of lectures on how we can utilize several tests for outlier detection, how we can eventually utilize other things like skew, how can we perform outlier detection, skewed data sets, how can we remove it, right? How can we remove our outliers from the data set and how can we use several trimming, capping, there's several other techniques for dealing with it. We'll deal with that, and then at the end we will just save it, and then we'll go to model building, which is super duper easy part in this, where we simply have our model to eventually train a model. But the most important part of this project would be the outlier, dealing with outliers and working with data. So let's meet in the next lecture talking about things which you have not imagined. Tab tak ke liye, bye bye.
So hey everyone, what I'll do today is talk about outlier detection, which is the most important lecture till now, which you're going to deal with today, is the most important lecture, and we'll try to achieve talking about outlier detection using z-score method. We'll try to achieve outlier detection using IQR, interquartile ranges. We'll also try several other techniques and how can we what is trimming, what is capping, etc. in these sort of lectures. So let's get started actually with all of this. So whatever you're seeing in front of your screen is for normally distributed data. So first of all, we'll try out outlier detection using z-score. And over here, first of all, we import our process data, the one which we process very nicely, and then we take a look at the head of this, and then we take a look at the tail of this. So let's try to print out our head of the data, and then let's print out first of all head of the data, and we print out the head of the data. This is how it looks like, but I think we want this to be in a form of, rather than printing, let's print out something like this. It should look like this, where you have 5 rows, 9 out of 4 columns. Right? Because why this is 9 out of 4 columns? Because every value of that categorical value has become a new categorical column. Now for z-score, we are going to use z-scores. We have studied z-scores in our probability lectures, so please go there and review it back. So z-scores are, and we are going to use z-score for outlier detection, right? We are going to use z-score for outlier detection. So basically what we are saying over here is that there's one condition for z-score, that your particular column or data should be normally distributed. So we first of all want to select the columns which are okay normally distributed. Okay, it is not like hi-fi and all. So you can go and see over here as well. How do I know if my distribution is Gaussian? If you want to go in math depth, but as of now we don't need to go in it. You can just use tests like normal tests from SciPy to understand it. So first of all, we select the numerical columns. Because why we want to select the numerical columns? We want to select the numerical columns only because we want to deal with numerical columns. And then you have Gaussian columns and non-Gaussian columns. So we make a 2 empty list, and then we say for column numerical columns, we are taking out the stat and p value for normal test which is conducted on that particular column, and then we're printing out statistics and p-value. And if now our significant is alpha is 0.05, so if a p-value is greater than that alpha, we append our column in that. So what we say, we reject our null hypothesis, and then we say, okay, that if the significance of that particular column is greater than 0.05, we say that the particular variable is the Gaussian variable, and otherwise it is not Gaussian. So we run it, it will take some time to run it. So you see that we ran it. Now if you take a look at the length of the Gaussian columns, there is only one column which is normally distributed. There is only one column which is normally distributed, which is PCT public coverage. Now in this, let's check with that's really Gaussian columns out here. So when you subplot it, and then here's the explanation of this code. So what you're doing, you're creating a subplot with 10 by 10 size. So this is whatever figure is created is of 10 height and 10 width, using a subplots function from the Matplotlib library. And there's n rows and n columns parameter. So you see there is something known as, this is how, so you have, and what is the number of rows and what is the number of columns. So if there is more columns, which are Gaussian or normally distributed, we most likely go with this, specify the number of rows and columns. And there's only one column and one row because there is only one value of Gaussian columns. And then we could use for loop to iterate over the columns. There is only one column in the Gaussian column. That's why we just iterate once time, and then we plot the density function, density plot of that function, right? Density plot of that function. The x parameter is set to axis, which allows the plots to be displayed on the same plot, and the subplots parameter is set to true, which specifies that each iteration of the loop, it should create a new plot. right? That should create a new plot. That's why subplot is equals to true. And then the ShareX parameter is set to false, which means that each plot should have its own x-axis. So each plot should have own axis. That's why ShareX, which is sharing the x-axis, should be false, right? And then we tight layout. Tight layout means to automatically adjust to fit nicely within the figure. So it should automatically adjust so it fit nicely on the computer. Then we run it. Now we see that this is the only column which is normally distributed, Now what we're gonna do? Now we're gonna take. Now we have the column. Now we have only the column right now. So if we print, now we're gonna take the whatever data present in that column, right? Because we want to identify outliers in that particular column, right? So we are going to take out the data from that column, and then we're gonna describe that data. So when you now you have the Gaussian data. If you print out the Gaussian data, so you have only one column, PCTI, which is Gaussian, because we want to process data and then we just have taken the Gaussian columns out here, right? So it is just giving the columns which are Gaussian. So now we have the Gaussian data. Now we can perform our outlier detection on this. And basic info, which is mean, standard deviation, count, 25 percentiles, 50%, etc., which is the good statistic which we'll use later on. Then what you're doing, we are taking out the basic info so that which we'll be using in our info, which is mean, standard deviation, minimum and maximum. And then what you're doing, and then over here, now here the part comes. As I told you that we need to identify the highest and the lowest, right? Highest allowed and the lowest allowed, and we'll be using the z-score in that, right? So what eventually we are doing? We are using z-score for eventually taking out, highest and lowest. So what you're doing in this case, we are taking that particular column, and then for that mean, because this is a basic info Gaussian, taking the mean of that plus, that's the maximum thing, plus 3 times the basic info, then the standard deviation. Okay, this is currently we're using z-score. That's why we have this formula. Why this 3 can be changed? We even to know the values which go outside of that. So if you go and see z-score outlier detection, z-score outlier detection, let's go to this. So you can see that anything which goes beyond this 3, then that's outlier. Beyond -3, below -3, that outlier, and beyond 3, that's also outlier, right? So the formula was this, but you can see over here, anything z-score, anything below -3, anything above 3, above standard deviation 3, they are outliers. Right, so if you see over here that there's the nice, any z-score greater than +3, which is standard deviation, or -3 is considered as a less than standard -3 is considered as an outlier, right? So which is pretty much same as the standard deviation. This is also called the standard deviation method, some people call it, but we're not going to call that. So we are going to take out for PVC column, not for inset, for this column, right? This is the highest allowed. So anything which goes above this, anything which goes beyond below this. So this is for +3 values and -3 standard deviation. So anything which goes, this is the top of the +3, and this is the value of the top below of the -3. So we say that highest allowed in that column is 59, which is the +3, which is the z-score in this is +3, and is in this case a -3. Lowest, where we subtract it. And then what we're doing, we are saying key in process data, now we are going to print out. So we say the process data. So you can see out here that what exactly we are doing, we are using the function uses Boolean indexing to select only rows in the data frame where the values in the column are either greater or greater than the highest allowed or less than the lowest allowed. And this results in the new data frame operation. And this is called the data wrangling. And in this case, you have processed, and then you go to that particular column, and then for loop iterate to every rows, and then say any rows which is greater than that, print out, or any rows which is more than this particular value, print out that. And that prints out very nicely your columns. And there's only 5 rows which are acting as an outlier. There's only 5 rows which are acting as an outlier. So what we do, we make a function where we make a function that checks, that deals with outliers, that checks whether that function is outlier. Just we implement the advanced version of it where anyone can put, column name, and then he'll be able to get your the data frame, right? So over here you have deal with outliers. So it deals with outliers where it returns the data frame which is the outlier data frame in that particular column. Okay, it is for that particular column. So it is highest allowed, lowest allowed, as we talked about, and then the data frame is where we select the columns, the rows where the values are greater than highest allowed, and select the rows which are smaller than lowest allowed, and then we return the data frame. Okay. Now we wanna get the columns from a data set. So we have the Gaussian columns. So now you have the Gaussian columns where all our columns which are normally distributed. As of now, we have the Gaussian columns which are, there is only one column in that which is normally distributed. But we wanna go forward and talk about there might be other columns as well when you're working on a project, right? So you iterate through every column in that Gaussian columns. And then you say deal with outliers. You call that function, and then you say what is the data frame you have is Gaussian data, which you have right now is the Gaussian data where we have only one column. So you have to also convert that to Gaussian data, which should be the Gaussian data. And in that Gaussian data, you have these columns, this particular column, because we're iterating to Gaussian columns, and the basic info which we wanna give, right? The basic info which we have to give. As of now, we have already taken out all these three, and when you take out the shape. And if that shape is greater than 0, then we see that colors have the outliers. So as of now, as we expect, PCT public coverage has outliers. Okay, so now if you print out this data frame, so let's print out the data frame eventually. So you see that we have the data frame, which is of 5 rows and 5 rows column. So you have this particular data frame. Okay, in that particular column, you have this value, which is acting as outliers, But over here, you see process data is showing all the values, but we are interested in only this particular, columns. So we just remove those trimmed those values from our original. So we remove this outlier, this outlier, which means removing whole rows. So there are a couple of methods while dealing with outliers. First one is trimming. Second one is capping. Trimming is a technique which is used to handle outliers in a dataset, which means that outliers are values that are significantly different from majority of the values in a dataset. When dealing with outliers, the goal is to identify or remove them in order to more accurate representation of the data. Otherwise, there are algorithms which are prone to this thing. So trimming means removing the values that are removing the outliers, simply removing. That's called trimming. Trimming means removing the outliers. When it is useful, when it is easy to implement, to be honest, and for interpretation of it provides a simple way to handle outliers without having to make any sort of assumption. It's just about removing like any missing values. So here's what we do. We go to now we have the calls that have outliers, right? And then we print the data frame where it has the outliers, right? Where we can clearly see. Then we iterate through all the columns which has outliers. Then we go to highest allowed and lowest allowed, and when it trimmed data. Trimmed data, what does it mean? Trimmed data, which means we go to the process data, right? And then we say that, and then we say that. Yeah. So over here we say that particular column is more than highest allowed, or I think this should be or that particular is smaller than lowest allowed, is greater than lowest allowed. So if that happens, remove the column, right? It is a trim data. We are only selecting rows which satisfies these two conditions, which we already seen, which is greater than values and smaller than values, right? So if you see the process data dot shape, you have 47. So I think we have to have this both the conditions, right? We have to add this both of the conditions to further successfully do it. Where now it removes all the values which are satisfies these both condition. It has to satisfy with this both condition, right? Now that's trimming. Trimming means removing of the outliers by your data wrangling conditions, where we say if that particular value in that particular column is greater than highest allowed for that particular column, we remove that. And then if that particular is less than that lower allowed, then remove that as well. Capping is another technique which is used to handle outliers, which means that to handle outliers by replacing the values that are farther away with the maximum or minimum value. So we just remove the values of that particular one with the maximum or minimum. So you can see that highest, and then we create a copy, and then we say that in that we lock LOC, we go to the values in that particular column, as we saw that column in this case a public PC2 average, then go to this column and then go to the if there's anything which is greater than highest allowed, and then we simply go to that column is equals to the highest, that's a maximum, and the same goes for minimum. So we simply have this capped data where we simply remove our our outliers with a maximum or minimum accordingly. You can see anything which is greater than highest allowed is going to be replaced with the maximum. Anything which is smaller than lowest allowed is going to be replaced with the lowest allowed. Now we have the capped data. Now you can see that this capped data will not have any such outliers in this, right? And obviously you can see we are not removing any rows, we're just capping it. So this is useful when you don't want to lose of your information. Okay, I hope that really makes sense. Now I hope that you understood everything which I wanted to teach about outliers. And in the next video, what you're going to do, I think it's pretty much understandable from now on, but I'll again make it for those who didn't understood again. So I'll make another lecture on outlier detection if there is a skewness in your column. So folks, welcome to the next lecture on many of you have requested me to work to actually complete this stuff, and that's why I'm just going to complete this. And you might have questions around like why the hell on outlier detection, like first of all we have used we have separated our normally distributed data. So you might be seeing over here we have separated our normally distributed data. For example, in this which we had outlier detection, I think there should be one, which is outlier detection using on normally distributed data. So what we were eventually doing in this approach is we were trying to from our whole data we were trying to extract columns. We were trying to extract columns which are normally distributed. Okay, so for example, there are several columns, and from that we were trying to extract columns which are normally distributed. And if you don't know about normal distribution, please see the lectures on normal distribution, which are prepared in a very nice way. So then we use some tests to determine, we use some statistical tests to determine whether that is whether that variable is normally distributed or not. And we use the thing which is p-values to identify that particular variable is a normal distributed or not using the certain test. However, you don't need to go in depth about that. How do we identify? That is for more like who wants to go in depth, but usually in interviews they don't ask like in depth all of these things, but it's good if you know about that. But that's something for statistics majors and all, but not for I guess for machine learning. So now we have analyzed only one column. So the reason why we are categorizing it first is for example, for normally distributed, we use z-score for outlier detection for normally distributed data, right? But there are several columns which are not normally distributed, as well as they are they follow other distributions. So what should we do? How should we handle? Should we go to every individual variables and then identify what is there in what is the outliers in that particular column, or what we do, there is something called as IQR, interquartile range, which we use that for outlier detection. IQR for outlier detection. So let me just tell you the IQR for outlier detection. Yeah, so we use outlier for IQR for outlier detection, and then that IQR works on skewed data. Skewed means positively shifted or negatively shifted. We have already talked. We have already had a talk on this. Please make sure that you actually go towards it. Now coming back to one of the questions which may arise, like a student asked me, like, hey Ayush, how can we identify which columns to test whether that column has outlier or not? Just I'll let you know one thing is that this is very a big problem. This is a big problem in like you can't just go to every variable and then do things according to your own pace. Each one column might follow normal distribution, and another column might follow skewed distribution, right? So they have two different distribution, and normally there is z-score works, and on skew there is other method works, right? So that's a defined set of rules which you already have. And what we do is simply classify in different categories, and then we apply the required outlier detection techniques for the same. And mostly our data has the skewed data. So first of all, what we do, you might have seen our data has 1900 columns. Our data has 1900 columns. So what we do is we simply say that why they have 1900 columns, because we have encoded our categorical data. That's why it went from small amount to large amount. So first of all, we identify columns which are categorical, because they are of course skewed, right? They are of course at one side or another side. So we don't want to touch them because they're categorical. So we separate the categorical values. What we do, we simply say calls to remove. We simply make a list, and then we iterate through our data columns, and then we say what is the number of in that particular column. We say if the unique number of values in that column is less than 10, which means they're categorical. However, there is only two unique values if they're categorical, but still for a safe journey, I just added 10. And then I added calls to remove append. Now I'm just using that list to drop that. So there is 1870 columns which we are going to drop because they're categorical columns. That's a nice strategy. You might have other strategies to remove the categorical column, because now they are not string type or object type. They're numerical type, and you deal with nicely to numerical types data. But make sure that you don't apply the basic processing like remove one single values or few unique values. Don't apply that, because you have to know that this is the categorical data. Right, that's for numeric, not for categorical. Now over here, the code defines, as you can see that over here. Now what we do, we identify the skewed columns. As I said, now we have the normally distributed. Now we identify the skewed columns. So whenever you try to solve for outlier detection, I did recommend you to do a couple of things. Is normal distributed data and skewed data, right? So there are different distributions which I might study, right? Binomial, uniform, etc. I suggest to take out to research on that. Okay, this is the distribution. This is distribution of my data. What outlier detection techniques which I can apply to that? So currently I have chosen skewed data. Skewed distribution, and skewed you might have it is shifted positively or negatively anyway, right? So we identify that sort of data, and then what we do, we simply say that over here we have a function that takes in the processed data frame and then the columns. So what does that columns means? The columns in the data, right? So columns in there, that's it. We make a list, and then we iterate through columns. We take out dot skew using dot skew method. We just take out the skewness score, and if that skewness score is greater than 1, or if that skewness score is -1, then we append that particular column in that skewed calls. And if that does not passes this condition, then we don't append, right? So you might have questions like how exactly skewness and all works. I did recommend to see out the reading materials which we have released for you. Please see that. That's the best thing which you can do right now. And then you will simply run this one, identify skewed columns, giving the data for skewness and the data for skewness columns. And you have total number 16 columns which are skewed data, right? And then what you do, you simply make it just like you created the Gaussian data, you create the skewed data. And then what you do, you simply create to see the distribution. So over here, we subplotted it where we said, where we have, I think 16 columns. So you have to subplot 16, right? So what we do, 4 by 4, 16. So we can have 4 by 4 plots to plot every 16 variables.
which you can see, and I've written the explanation of the code for the same. Please see that, which you can see now. If you just maintain it, let me just say plot image, output, open it, please. Yeah. So first of all, see this. This is the distribution of average ANN count. This is the distribution of average depth. So you have 1, 2, 3, 4 columns, 1, 2, 3, 4 rows, and you have all the 16 variables which you had. Now you can see that they are skewed data, which you can see over here, positively, negatively, and you can see this is negatively, this is positively, this is slightly positively, negatively. I'm sorry. I think I did wrong. This is slightly positively, and this is negatively, positively, and you can actually see that we have positive and negative. If it is going from this side, then this is negative. If this is going to this side, this is positive, right? So and then you tight layout so that it adjusts automatically, and then you show it. Now you can see that you're confirmed. Okay, these are my columns just skewed. And then what you do, you simply box plot so that you see that they do have outliers by using this particular code where you're saying figure, where you're giving the column and the box plots outliers. And then your title is box plot, what were the number of columns to be added, and then you say go to, and then you apply this function to each and every variable for that particular data, for skewed columns, and then a column, and then skewed columns where you have the skewed data. And here you can see that OMG, we do have the skewed, we do have outliers. So you can see maximum, and then these are the information which are of outside the way, and this is, you can see outside the way, right? And we have seen the interpretation of the box plots as well. Now you can actually see that this is also the outside the way. These are the variables, etc. So we have this. Now, how can we deal with this? What we can do? Let's take a particular column from this. Let's take a particular column. I'm going to take the skewed column, which is for an example as of now, study recap, and then we take out the quantile range, 25th percentile, the 25th percentile, and then we take out 75th percentile. Okay, we take a 25th percentile, and then we can take out 75th percentile, which is the Q1, quartile 1 and quartile 3, and then we take a IQR from that. Okay, and then we have upper limit, like the maximum value which we should have, and anything goes above this are outlier, and lower limit, which is minimum and things. So you can see plus minus over here, we are multiplying this, and this is the standard deviation, upper limit and lower limit. And then you can simply say the process data, where you just trim the data out here, where you just say take out the columns here which are outlier, which you're saying are upper limit, or they're of lower limit, they are below the lower limit. Upper limit for this particular column is 209, and lower limit for this is -125, and these are the columns which 504 rows in that particular column has outliers. And then you simply apply this, and then you simply apply this column where we just had listed this particular all the code into a sort of function, a define and column for that particular column. Is checking the quantiles, Q1, Q3, IQR, and then upper limit, lower limit, and then taking out that. And then what you're doing, you're iterating through all columns and then applying this function on that, giving the process data and that particular column. And then you simply have the then you simply have the columns which has the outliers, right? Now you have the columns which has the outliers. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All 16 variables have their outliers. So what we do, first of all, we take out trimming. There's two approaches we have to talk: trimming and capping. Trimming, removing. Capping means updating my values, like what values, updating my outliers with the maximum and the minimum, right? So if that is maximum, then if the value is above the maximum, then we update that with maximum. If the value is lower than minimum, then we update that with the minimum. You might be clear if you have seen the previous lecture. Otherwise, I'm not going to repeat once and once again, right? So going to this code on trimming, we first of all identify what rows to remove, and that can be done by this data wrangling or the data extraction, where you're saying in that particular column, if that is greater than upper limit, and if that is smaller than lower limit, then these are the rows to remove. And then this is a trimmed data, where we actually talk then trim our whole data, and over here we are capping it. Here we are capping it out there, and over here this is just an example as of now, just to showcase. We'll convert that to a function right now, and then we simply lock LOC to identify the rows, and then we identify the rows where your upper limit for that particular column, right? For that particular column, for that the upper any value in that particular column is greater than upper limit, update that with upper limit, and any value below that lower limit, update that with lower limit, which is the minimum value. You see that your data is maintained the same, but over here your data is trimmed. Capping means you see over here again the same thing. You have converted the code to over here, and over here we will cap, will not remove. Cap, by removing we'll lose whole lot of information. That's why we are capping it over here. And now you can see we are simply say go to that particular column, row in that particular column. If that is greater than upper limit, for that particular column, update that with upper limit, and if that is smaller than lower limit, update that with lower limit. Okay. I hope that you're getting. And then we apply this capping, this function on every variables who have outliers. And then we see that we have the data without trimming. We are just going to cap it. And then you can now box plot on cap data. Now your cap data has that. Now if you box plot on that for every columns, now you see there are no outliers, and that's hooray. You won it. You won the challenge. I hope that you get it. And then we say now we are going to use the cap data only. We are not going to use something. Then we save our capped the data into something else. Okay. I hope that you got one point. There is one assignment related to it. There are lots of things to try out. You can actually try out outlier detection using percentile method. That's your thing. Now I think we are mostly done with the outlier detection. On regression model, let's talk about in the next set of videos around a regression model, and then we'll actually talk about that in great detail. Let's go in the further video and let's talk about that. Cool. So we'll come to now we have done with the data part, and my whole point from this project is to tell you about data stuff. Now we'll just go and quickly review, because we have already talked a lot on how to build regression model and all, and that's not my point on talking in this project. My point was different, to teach you several techniques, feature engineering, collection, and all techniques to actually go forward with it. Now what we'll do, we'll try to model it very basic, just to let you know, we have already tried it out, and then now in the assignment you'll be given to model it accordingly. So I'm just going to give you a very small baseline, and as an assignment you'll actually further update this stuff. Now which you're seeing in front of me is we have the first function, but ignore all of that. Let's go to over here. So what I did, instead of classes or everything, I just created functions, right? I just created functions so that it is easy for you to understand. But usually I suggest you to work with classes. First of all, we are importing our cap data from the cap data which we saved. So you can actually use the df.2csv and give that particular path. You'll be saving that your file. And then if you go to the data folder, you have a cap data over there. And cap data is where you have dealt with missing values and everything out there, outliers and everything. Now what you will do is you simply first is you have this particular thing where you have the correlation. First of all, you have the read it, and then the second thing which I really like to do is identify the correlation among numeric features. Identify the correlation among numeric features, and right now it has 1900 columns, and it will take so much of time. And the reason why I want to identify the numeric correlation because there is one assumption which you have saw that they should not be correlated too much. If they're correlated, then they're not providing any sort of information to the output variable. And when I apply my correlation techniques, and not in every project you have to do this in exploratory data analysis part, where you are understanding the correlation between variables. This should be done in an EDA part. Right, I'm doing it right now because I think it's much for me. I think as of now, I've just added over there just to make sure that we are on a page, right? Like why we are using this. We are using just to know that we can ignore our highly correlated correlation coefficient and then see our result, right? So I just added over there for a sake of learning, but this is a part of your EDA. So you have a correlation among numeric features where you're given the data frame and the columns of the data frame. And then in numeric column, you select all the columns that are numeric. And then to To be honest, every column is numeric in this right now. And then you take out the correlation. It builds a correlation matrix with, we have already talked about correlation. Please, we don't want to get it, but I'll tell you a small stuff. So let me just go to correlation matrix, and then let's talk about that a bit. So this is a correlation matrix. So I'll just open that in another tab. So this is a correlation matrix, and in this correlation matrix, you find heat map like this. You find heat map like this, where on over here on y-axis you have the variables, on x-axis you also have the variables. The correlation between the same columns is 1. They are highly correlated with each other. But the correlation between survived and p class is negative. The correlation between survived and this variable is this much. The correlation between survived. So you have the matrix for every. We are taking out the correlation between every variables out there. Right. So it takes out the correlation, and then it has the empty set, and then what we are doing, we're going to, for I in range, for that correlation, all the correlation, and then we go to J, and then we are saying if the correlation of two variables, if the correlation between, for example, survived and p class is greater than 0.8, is 80%, greater than 80%, we simply append that. It's highly correlated with each other. Right? We simply append that. We simply append that column so that we could know that they're highly correlated features. So you're seeing that when I ran that method, by applying this. So basically, what you're seeing over here is I had the columns, and then over here I had the columns, and then over here you can see correlation among numeric features, capped data and capped data dot columns. So I've just given the capped data and then columns of that capped data. And then I was able to take out the correlation features, and these were the most highly correlated features among themselves. And now what we can do, we can first of all remove the columns from the data first of all, but I don't really like removing it. So what I'm doing is I'm making a list where I'm telling call in capped data dot columns if the call is not in highly correlated. So we are just saying key for every column in your cap data, which is your data which you have imported, for every column, make sure give me that column names, but also make sure that these are not in these highly correlated. If the call also not in this. So this is a list comprehension which you might have learned in your Python programming language. And as said, please see the resampling methods for this. I'm not going to explain a single word right now. Please see the resampling method. What we are doing is dividing our data into training and testing. I've already uploaded lectures on resampling. Please go and see that first before coming to this. Split the data, and then we train our model, LR model. I'm not going to go with this. We are adding the constant. Why we are adding the constant? Because we have to multiply with that bias term, that 1, x0 is equals to 1. So we are adding 1 to every rows, so that whenever b0 multiplies with 1 only. Right, which is the bias term. And then we have adding the constant, and then we have LR model. We are training OLS from the stats model API with the Y train and X train with intercept. And then we simply taking out LR.summary, and then it is printing out the summary, and then you have the same goes for significant variables. So what we are doing, we are identifying the significant variables. So now let's talk about that. Like I'll talk in a bit, but let's run this whatever we have as of now. So just to make sure that we're on the right page. So it will take some time to run. We'll just chill out right now. So it will take some time to run. And so we should just stay calm, stay nice to whatever is going to happen right now, because the columns are super high, and first of all, it might be not as much valuable to deal with that categorical, but to have those categorical columns. So the correlation between categorical columns. So I'll be giving you a very nice article which talks about correlation between categorical columns, which tells you whether that and we'll also worry about what are the variables which are significant enough to make our model better. Right? We cannot go with these much variables, to be honest, because it will lead to several other problems as well. So first of all, let's go with this. Now if you see over here, it printed out the columns which is of highly correlated. So if you see out here that we print out the highly correlated features, and then now it goes and training of the model. So it is training of the linear regression model, and it will take X-train and Y-train, this training out, and then it is going to print out the summary. So let's try to take out what exactly summary looks like. Oops. Yeah, this is the summary, and this summary is too big because you have 1900 columns, bro. You understand, your 1900 columns, and to be honest, the most of the around 99% are of encoded columns. That's why in this case we have to remove some of them. So first of all, see that we have dependent variable, the thing in which we want to predict R square, adjusted R square, F statistic, number of observations, residuals, you have moral covariance type. And then for constant, which is the bias term, we have the beta 0 is 94, then standard deviation, the T and the P value for that, average, and for every variable you have this much information left. For every variable you have this much information left, and there is so much of information, and it is not feasible to go through every information. So what I do, I just go through what are the features which are numeric, which are important, which are not categorical as of now. So what I'm doing, I just go through, you can go through numeric and then talk about some things. But before that, what I can do is talk about things which is, we can take out the significant variables. We have learned about that. So let's do one thing. Let's print out the significance variable. So let's print out the variables which are only significant enough. So from 1900, we got to 144 columns which are significant enough. We have done a lot of tests. We're using P values. You can take out the significance of a particular variable. So we using T statistic. We are taking out the significance of each and every variable over here. So we are using lr.p values, and that P value is this particular thing. T is greater than this particular information. T statistic, T test which we are using right now, this particular thing which you're seeing right now, P is greater than that. So we are using for that if P value is smaller than P value threshold, and threshold is 0.05. Okay, I hope that you're getting me, that we are taking on the only columns which are greater than that, so that so the values which are smaller than 0.05, so that we can reject our null hypothesis and say that okay, these variables are important. So we have only 144, 1900 to 144. We have reduced the complexity of the model. Understanding what I'm trying to say? Now what you're doing, you're simply training the model now with significant variables. Though the reason why we are removing this, I'll tell you the reason why we are removing this. But first of all, you'll get to know. First of all, let's run this. You'll get to know. You got an error. What you got an error? In that significant variables, you also have the constant column. Or constant means constant which has 1. Right. So what I'm going to do, I'm just going to remove it as of now. There is actually a lot of fixes right now, but I don't want to extend that. You can fix it by your own. So what you can eventually do, you can create actually in X-train as well. You can create a constant column as well, so that it appears that. So you can actually what you can do. Let me do one thing right now. I think that's something which we can eventually do. X-train, and then just go ahead and then add X-train and then constant. I guess what we can eventually do in this, you can add the significant constant columns rather than removing that. So I think which we can go and then add significant vars, and then significant vars we can add constant. Yeah, so you can actually do this, but however, that significant add should be having your favorite, that should be having constant columns. Or you can do, you can simply have this sm dot add constant, and then you can simply add that constant as well over there, right? So it is very easy to do things. You can actually go to X-train dot add constant, and then the constant will be also added, right? So you can actually go over there and then simply add sm dot add constant, right? Sm dot add constant, because in X-train it is not added, right? So we can actually go ahead and then add the constant out here, sm dot add constant, and then we simply have this X-string. So it adds the constant. You can actually use for loops and all to also add it, but this is the best way to actually do that rather than removing that. So rather than removing that, you can actually add this, and then once you add this, so let's run this. So you might be having a nice set of information. So now it is complete. Now you run this. You should be able to see a very nice set of info. So now let's go and let's print out the summary, which you can see. So now if you run this,
Now if you run this, you have less information as compared to the previous one. You have just only few set of information to go forward to. So yeah, this is the one, and then you can also see the R square is 0.68. However, it is decreased, but it is a model which we looked for, right? Or however, it reduced the complexity of our model, right? Our complexity of our model. The more important is not to get the accuracy, but also the robust model, the model which is able to perform in most of the cases and very nicely. So this was it for the project, and I hope that you really liked this particular project, and you'll be given assignments for the same for rest of the things which you have to do in the project. Now you can get started with making your own projects. I have tried to explain each and everything from very scratch. Now I suggest to watch resampling methods video, regularization videos, which is going to come. So please watch that, and thank you for the lectures.